Hi, I'm Allison.
And I'm Jeff.
Welcome to the first lecture of Statistics, Making Sense of Data.
The purpose of this lecture is to introduce you to the course and to some of the first data sets that we'll be examining.
This course is an introduction to the science called statistics.
The goal of statistics is to use imperfect information, our data, in order to infer facts, make decisions, and make predictions about the world.
Statistics is the science of collecting, organizing, describing, analyzing, and interpreting data.
It has applications to virtually every area of our lives, from business to health and nutrition, politics and education.
Early in the course, we'll look at descriptive statistics, which is about summarizing data using numbers or plots.
Later on, we'll work towards statistical inference, using data to make conclusions or decisions.
While statistics is a science, we can also talk about a statistic. A statistic is a number or value measured within some particular context. In order to carry out sensible and meaningful statistical procedures, it is important to understand the context.
We need to understand which data were collected, how and why these data were collected, on which individuals or entities the data were collected, what questions we hope to answer from the data, and what group we want to make conclusions about.
One of the data sets we'll look at in the first few lectures is the 2012 salaries of the New York Red Bulls soccer team, which is a team in the MLS, the top North American professional league. MLS players' salaries are released multiple times per year by their players' union. The salaries that teams in the MLS pay their players are governed by some rules, of which 3 are of particular note. Firstly, there is a minimum salary. Secondly, there is the designated player rule. Because of this rule, teams can attract a limited number of international stars, paying them high salaries regardless of the salary cap. And for the third rule, there is that salary cap. That is, there is a maximum total amount a team can spend on player salaries, excluding their designated players. We'll investigate how these rules are reflected in some data, which is the salaries of the 25 New York Red Bulls players in May 2012.
Another source of data for us will be facts and figures for different countries and territories around the world. For example, we will consider the life expectancy for each country, the average number of years a newborn child would live if current mortality patterns were to stay the same. These data were assembled by gapminer.org, using such sources as the United Nations, the Human Mortality Database, the Human Life Table Database, and more. Life expectancy serves as an excellent measure of a country's overall health and well-being. We will investigate how a country's life expectancy is related to various other factors, like which region of the world the country is in, and the country's average wealth, i.e. its GDP per capita, and what fraction of adults in the country are infected with HIV, and so on. Studying these data will allow us to draw statistical conclusions about how different factors influence a country's well-being.
A third data set we'll investigate arises from the problem of estimating the age at death from skeletal remains. This is a common problem in forensic anthropology, and anthropologists have devised several different methods for estimating age. In adults, these methods often rely on examination of the wear and deterioration in certain bones. Developing improvements to these methods is an active area of research. Catherine Merritt, a biological anthropologist at the University of Toronto, is examining how the accuracy of several of the existing methods is associated with physical characteristics, specifically focusing on body size. She has used a number of methods to estimate the age at death of several hundred skeletons of known age so that she can assess the accuracy of the estimated age. We will look at a randomly chosen subset of 400 of the skeletons Catherine has investigated for 2 of these age estimation methods. The first, the method of Dagonji et al., uses aspects of the first rib to arrive at the most likely age at death. The second method we will look at later, the Suchy-Brooks method, is the most commonly used method for age estimation and uses the pubic bone. The Suchy-Brooks method classifies the age at death into one of 6 age categories by comparing the pubic bone to reference bones selected as representative of various stages of deterioration. A possibly important distinction between these two aging methods is that the pubic bone is part of the pelvis, which is a weight-bearing part of the human skeleton, while the ribs are not weight-bearing. For each of these methods, we will look at the error in the age estimation, that is, the number of years the estimated age differs from the actual age at death. We will also investigate whether this error differs between the two methods, and also whether the error in age estimation varies with body mass index or sex.
In the weeks ahead, we'll use these and other data to illustrate the basic concepts of the science of statistics.
We will learn the fundamental techniques in order to collect, summarize, interpret, and analyze data of all types.
By the time you finish this course, you'll know how to draw sound statistical conclusions about the world around you.
So let's get learning some statistics so we can understand these data. In statistics, we're confronted with lots of data, and we need to try to make sense of it all. For example, here is a list of the life expectancy, the number of years that people live on average, for 197 different countries and territories around the world. Look at all these numbers. How are we going to make sense out of all this? One way is to try to summarize it, try to come up with a few numbers which give us a sense of what the data are all about. As a first step, we can try representing all of these life expectancy values as points on a graph. Well, it still looks kind of like one big jumble of numbers, giving all the life expectancies from Afghanistan all the way to Zimbabwe. Is there any way that we can make better sense of this? Well, for starters, we can rearrange them so that they're in increasing order, from the smallest life expectancy up to the biggest life expectancy. That looks a little better. Now we can start to see a few things. For example, we can see that the country Sierra Leone has the smallest life expectancy of just 47.8 years. Meanwhile, the country Japan has the largest life expectancy at 83.4 years. All of the other countries have life expectancies which are somewhere in between. We can also learn a little more. For example, we can look for the country which is halfway along, halfway between the first country and the 197th country. That's the 99th country, which in this case is the country Egypt. And Egypt has a life expectancy of 73.2 years. So we say that the median life expectancy is equal to 73.2 years. It means that half the countries have a life expectancy which is smaller, and half the countries have a life expectancy which is larger. So now we know about the minimum and the maximum and the median. But there's more that we can say too. For example, if we look at the country which is 1/4 of the way along in the graph, then that turns out to be the small island nation of Sao Tome and Principe. And it has an average life expectancy of about 64.7 years. This is called the first quartile, and we can say that 1/4 of the countries have a life expectancy which is less than 64.7, and the other 3/4 have a life expectancy which is more. We can also go 3/4 of the way along the graph. This brings us to the Netherlands Antilles Island Collection, which has an average life expectancy of about 76.7 years. This is called the third quartile, and it tells us that about 3/4 of the countries have an average life expectancy which is less than 76.7 years, and 1/4 of them have a life expectancy which is more. So now we know the minimum, and the first quartile, and the median, and the third quartile, and the maximum. This is a lot of information, but it's also a lot to keep track of. If we want, we can combine all of these numbers together into a single display which is called a box plot. The box plot is illustrated here. We can see that it has a big box between the first quartile and the third quartile with a line which indicates the median. It also has extensions on the bottom and the top which represent the minimum and the maximum values. So we can see by looking at this box plot what is the minimum value, the first quartile, the median, the third quartile, and the maximum value. In this way, we can summarize a lot of information about these life expectancies using just 5 numbers. So now let's try working out an example together. Suppose here are the grades from my seminar class last semester. There were 9 students, and these are the grades that they received. How can we figure out the quartiles and median and so on for these grades? Well, for starters, let's rearrange them into increasing order. First we'll find the smallest number, then the second smallest number, and the third smallest, and so on. That way we get 9 numbers in order. Now we can see right away that the minimum grade was 68, and the maximum grade was 93. What about the median? Well, there's 9 grades, so we want the one which is halfway between the first one and the 9th one, and that's the 5th one. So the median grade is the 5th one, which is equal to 79. What about the first quartile? Well, for that, we want the grade which is 1/4 of the way from the first grade up to the 9th grade, which in this case would be the 3rd grade, which is equal to 74. For the third quartile, we want to go 3/4 of the way along from the first grade to the 9th grade, and that's the 7th grade, which is 88. In that way, we found the minimum, the first quartile, the median, the third quartile, and the maximum value. If we want, we can also make this into a box plot. Again, to draw a box plot, first you draw a big box which goes from the first quartile up to the third one. You put a line in where the median is, and then you put extensions to show the minimum value and the maximum value. In that way, we've made our own box plot. Now, let's try one more example of computing the 5-number summary. This one will be a little different for a reason that we'll see. Suppose that there are just 6 students' grades, which are the numbers indicated here. In this case, we can still start by arranging them from the smallest up to the largest. So we can still easily see that the minimum value in this case is 68, and the maximum value in this case is 93. But now what about the median? Well, that should be the number which is halfway from the first number up to the 6th number. In this case, that's the 3.5 number. Well, there is no 3.5 number. But no problem. We can just take the number which is halfway between the 3rd number and the 4th number, and that gives us a median which is equal to 81. Now what about the quartiles? Well, the first quartile should be the number which is 1/4 of the way along from the first number up to the 6th number. In this case, that's the 2.25 number. Well, there's no such number, but we can take the number which is 1/4 of the way from the 2nd number up to the 3rd number, which in this case is equal to 75. So we say the first quartile is 75. Similarly, for the 3rd quartile, we need the number which is 3/4 of the way from the first number to the 6th number, which in this case is the 4 3/4 number. Well, there isn't one, but we can take the number which is 3/4 of the way from the 4th number to the 5th number, and that equals 88.5. So now we've been able to compute all the numbers, just being a little more careful. Another way to see this is to draw a graph. If we graph all the numbers from smallest to largest and put a straight line in between them, then we can say right away that the median is the number which is halfway along the graph, the first quartile is the number which is 1/4 of the way along the graph, and the third quartile is the number which is 3/4 of the way along the graph. So, in this way, we see that no matter how many numbers we have, we can still compute their minimum and their first quartile and their median and their third quartile and their maximum.
Hello. In this video, we'll continue to consider some summary measures we can use when exploring a data set. This time, we'll go to the data provided by our anthropologist.
Here we're trying to estimate age at death from skeletal remains, and in this video we'll in particular consider the method of de Ganji et al. We're interested in how well this method works, so we'll consider the difference between the estimated age based on the skeleton and the actual age at death for the 400 skeletons in our data set. We'll begin with a look at a box plot of these data. Although there are some positive values, we can see that most of the observations are negative. In fact, because the third quartile is negative, we know that more than 3/4 or 75% of the data are negative. So the method of de Ganji tends to underestimate the age of death. It's also possible with this method to be way off from the actual age. Note that the minimum value is -60, meaning for one of the observations the estimate was 60 years younger than the actual age. We may want to investigate how unusual this value of -60 is. A modified box plot is one way to do this. Modified box plots were designed to detect unusual observations. To draw one, we first calculate the interquartile range, or IQR. This is the difference between the third and first quartile. For these data, the third quartile is -5 and the first quartile is -23. The difference is 18, so the interquartile range is 18. We then locate the inner fences, which are designed to contain most of the data. The inner fences are the values that are 1.5 times the IQR beyond the first and third quartile. For the lower inner fence, then, we calculate the first quartile, -23, minus 1.5 times the interquartile range, 18, which gives us -50. Similarly, for the upper inner fence, we calculate -5 plus 1.5 times 18 and get 22. In a modified box plot, the whiskers extend to the observations that are closest to the fences but still within them. Values outside the fences are indicated individually and are worthy of some attention, particularly isolated values that are far outside the fences. We can see that our minimum value of -60 is outside the inner fences, but there are also other observations beyond the fences, so perhaps an underestimate of 60 years is part of the range of values that might be observed with the de Ganji method. Here's a quick summary of how to construct a modified box plot. It can help us both summarize the data and detect some possibly unusual observations. Here's the 5-number summary again for our data. The median is a measure of the center of the data. Another common statistic used to capture the center of the data is the mean or average. We'll introduce a bit of mathematical notation here. The Greek letter capital sigma is used in mathematics for a sum. The mean is the sum of the data values divided by the number of data points. Suppose we have n data points. For our example, n is 400, the number of skeletons. Let's represent our data values as x subscript 1, x subscript 2 through x subscript n. The subscript is an index for the position of the data value in the data set, and n is the number of data values. The mean is given the symbol x with a bar over it, and the formula for the mean is the sum, sigma, of the x's from the first observation to the last, divided by the number of data values, n. For the differences between the estimated and actual ages for our 400 skeletons, n was 400, the median, as we saw, is -13, and the mean for these data is -14.2. Notice that the mean is more negative than the median for these data. This happens because the mean is pulled down by the unusually large negative observations we observed here. We say that the mean is not a robust statistic. That is, it is not resistant to extreme observations. In contrast, the median is a robust statistic. Changing the values of the extreme observations does not change the value of the middle observation. Suppose we wanted to limit the influence of the extreme observations on the calculation of the mean. One option is to use a trimmed mean. To find a 10% trim mean, delete the largest 10% and the smallest 10% of the data, and then take the average of the remaining observations. For these data, we remove the 40 largest and smallest data values, and the 10% trim mean is negative 13.8. Note that the trim mean is closer to the median than the mean, as the trim mean is more robust to extreme observations than the mean. As an illustration of the robustness of the median and trimmed mean versus the mean, let's look at a smaller data set. Here are the salaries in US dollars announced in May 2012 for the 25 players on the New York Red Bulls, a soccer team in the MLS. I've put them in order from smallest to largest. As is typical in the MLS, a few players have very large salaries, while most of the players have salaries more in line with the average American. In particular, the salaries of Rafael Marquez and Thierry Henry, who had the largest salary in the MLS, are much larger than the salaries of their teammates. You can see just how unusual Marquez and Henry are by looking at a modified box plot. The box needed to be very compressed to fit them on the screen. Let's do some calculations. Since there are 25 salaries, the median is the 13th value in the ordered salaries, which is about $112,000. For the mean, we sum the salaries and divide by 25 to get approximately $518,000. We can see that the mean is much larger than the median because it is influenced by the large salaries of Marquez and Henry. If we want to remove their influence, we can use a trimmed mean. 8% of 25 is 2, so an 8% trimmed mean would remove Marquez and Henry, as well as two players earning $33,750. The trimmed mean is the average of the 21 remaining salaries and is about $128,000, which is a value that is much more representative of the salaries of the rest of the team. Here's a summary of the measures of center or location that we've discussed. The median and the trimmed mean are robust against extreme observations, while the mean is not.
In the previous lectures, we've learned how to summarize the data and how to compute its center or location or central value. Now we're going to consider something related but a bit different. We're going to consider the spread of the data, that is, how far does it seem to be away from its central value? To begin, let's consider again that data about the life expectancies of 197 different countries and territories. We already computed some things about this data. In particular, we learned that the median life expectancy is equal to 73.2 years. It's also not hard to compute that the mean life expectancy is equal to 69.9 years. So these are two different measures of the location or the central value of the data. But now we say, what about the spread of the data? How far does it seem to be away from these central values? Now, one way to think about this is to consider the data's box plot, which we saw already and which is shown here. The box plot shows us various summary statistics, the minimum and the first quartile and the median and the third quartile and the maximum. So the simplest way to think about the spread of the data is to look at its range, that is, just take the maximum value minus the minimum value. In this case, the range is equal to 83.4 years minus 47.8 years, which is equal to 35.6 years. So this tells us that all of the data can fit into an interval which is of length 35.6 years. Another thing we can do is look at the interquartile range, or IQR, as we've seen previously. The interquartile range is found by taking the third quartile minus the first quartile. In this case, it's equal to 76.7 years minus 64.7 years, which is equal to 12.0 years. So we can also say that for this data, the interquartile range is equal to 12.0 years. This means that the middle half of the data can fit into an interval which is of length 12.0 years. So now we can summarize the spread of the data either by the range or by the interquartile range, and those are both nice ways to summarize the spread. But they don't take into account all of the data values. They just take into account certain summary values. What if we wanted to use all of the deviations of all of the data values from their mean? Well, we could just try adding up all of the deviations of all of the values from their mean. But that would always add up to 0 because the positive deviations would exactly cancel the negative deviations. We could also try adding up the absolute values of all of the deviations of all of the data values. That would make sense, but it would be very hard to work with. It turns out what's the best and most useful thing to do is to add up the squares of all of the deviations of all of the data values from their means. Now in the end, we don't really want the sum, we want a sort of an average. So it turns out we'll want to divide this by n minus 1, by one less than the total number of data values. That gives us a formula for the variance of the data. Finally, if we want to undo all those squares that we did, we can take a big giant square root. So once we take a square root of 1 over n minus 1 times the sum of the squares of all the deviations from the mean value, that gives us what's called the standard deviation. It's a bit complicated, but it turns out to be a very important measure of the spread of some data. Now you may be wondering, why did we divide by n minus 1 instead of just dividing by n and taking an ordinary average? Well, it turns out that dividing by n minus 1 is the best thing to do. In fancy language, it gives us an unbiased estimator of the population variance. All we need to know is it's a smart thing to do. Intuitively, we can think that the first value doesn't tell us anything about the spread. It's only the remaining n minus 1 values which say something about the spread, and that turns out to be sort of why we need to divide by n minus 1. In any case, often n will be large, and then it doesn't really matter if you divide by n or by n minus 1. So now we understand how to take not just the range and the interquartile range, but also the variance and thus the standard deviation of some data to figure out their spread. Now let's try working out an example by hand. Let's go back to those 9 student grades that we saw earlier. We already know in this case how to identify the minimum and the first quartile and the median and the third quartile and the maximum grade. This means right away we can compute the range by taking the maximum value minus the minimum value. We can also compute the interquartile range by taking the third quartile minus the first quartile. What about the variance and the standard deviation? Well, for starters, we have to compute the mean by adding up all 9 of those numbers and dividing them by 9, which is the total number of numbers. That gives us the mean value. Then we have to add up the squares of all the deviations from this mean value, divide it by 8, which is the number of numbers minus 1. That gives us the variance. And then finally, we need to take a square root in order to get the standard deviation. So in this case, in addition to saying that the range of the grades is 25 and that the interquartile range is 14, we can also say that the standard deviation is equal to 9.3. We'll be working more with these different measures of spread as we go along. For now, let's consider one last example. Let's consider again those salaries of the soccer players on the 2012 New York Red Bulls soccer team. We already computed that the median of these salaries is about $112,000, and the mean is about $518,000, which is a lot higher. We also considered trimming the data and said that if we eliminated the two highest and the two lowest salaries, then the median would stay exactly the same, but the mean would be a lot less, now just about $128,000. Let's stick with this example and see what it tells us about measures of spread. Here's a chart which shows for both the original data and the trim data various quantities. We can see that the range changes tremendously from over $5 million with the untrimmed data to just $268,000 with the trim data. One thing we can consider is whether that measure is robust or resistant to outliers. Certainly the answer is no, because the range changes tremendously if we remove a few outlier values. The interquartile range, on the other hand, is rather different. It's 150,000 for the full data and 146,000 for the trim data, almost the same. So we can say it is resistant to outliers. It is robust. Finally, we can consider the standard deviation that we just learned how to compute, and it's kind of complicated. We can also see that for the original data, the standard deviation is well over $1 million, but for the trim data, it's only $84,000. This says that the standard deviation is also not robust or not insensitive to outliers. So where does that leave us? We've now introduced 3 different ways of measuring the spread of data. First, we have the range, which is just the maximum value minus the minimum value. It's quite simple and often quite useful, but it's also not robust, and it's very sensitive to outliers or extremely large or small values. We also have the interquartile range, which is much more robust and in some ways a better way to measure the spread of data. Finally, we have the standard deviation, which is not robust to outliers, and it's quite complicated to compute, and yet it's going to turn out that that will be an extremely useful measure of spread for us. So there you have it, 3 different ways to measure the spread of data.
In this video, we'll look at histograms, which are another way to picture quantitative data. And we'll learn some vocabulary we might use to describe the features of the data that we might see in the histogram. In particular, in this video, we'll focus on the shape of the data. The pattern of the values of data is called its distribution. A histogram is useful for visualizing the distribution. We can see whether the data tend to be close to a particular value or maybe multiple values, whether the data varies a lot or a little about the most common values, whether that variation tends to be more above or below the common values, and whether there are unusually large or small values in the data. Let's start with a histogram of life expectancy for the 197 countries and territories for which a 2011 value of life expectancy was available. The first step in constructing a histogram is to divide the data values into intervals or bins that are mutually exclusive so that they don't overlap, and exhaustive so that we don't miss any of the data. Bins are usually equal in size, but they don't have to be. The life expectancies range from about 48 to 83 years, so we've defined our bins to capture every decade from 40 to 90. The first bin includes countries with life expectancies at least 40 but less than or equal to 50. The second bin includes countries with life expectancies at least 50 but less than or equal to 60, and so on. The cut points are the values that define the bins, in this case 40, 50, 60, 70, 80, and 90. The vertical axis in our histogram is the frequency or count of the number of data values in each bin. We draw touching bars for each bin up to the frequency of that bin. Note that we can't read the actual data values from a histogram. From our first bin, we know that there are 9 countries or territories with life expectancies greater than 40 years and at most 50 years. But as an example, we can't tell from the histogram what the exact value of the minimum life expectancy is. The width and number of bins in a histogram can be any convenient value. However, It is possible to dramatically change the appearance of a histogram with the choice of bin size, particularly when the number of data values is small. As an example, if we change the bins to cover only a 2-year span, the life expectancy histogram appears to be more noisy, with more variation in the frequencies among bins. The tails of a histogram are the bars in the far left and right where the extremes of the data values are. Life expectancy has a longer left tail than right tail, corresponding to countries or territories with relatively low life expectancies. Here are a few examples of the range of shapes of distributions we can see in histograms. The histograms vary by the number of peaks and whether or not they have a peak, how symmetric they are, and how long the tails are relative to each other. From a histogram, we can get lots of information about the data. We can learn the peak of the distribution. If there is one peak, where it occurs is called the mode, corresponding to the most common bin of data values. We can learn the number of peaks or modes. A distribution can be unimodal, meaning it has one peak, or bimodal, having 2 peaks, or multimodal, having multiple peaks. A uniform distribution, in which all data values occur about an equal number of times, is an example of a distribution without a mode. From a histogram, we can also get an idea of the extent of spread in the data. We can also see the extent of symmetry in the distribution of the data. Histograms can be symmetric, which can be the case in unimodal distributions, distributions without a mode, or multimodal distributions. Left or negatively skewed, meaning it has a long left tail. Right or positively skewed, meaning it has a long right tail. We can also see deviations from the overall pattern, such as gaps in the data. Outliers are data values that are separated from the rest of the data because they are much larger or much smaller. Let's go back now and describe the life expectancy data from its histogram. There is one peak, so the distribution is unimodal. The mode is between 70 and 80 years. There is a much longer left tail than right tail, so the distribution is left skewed. And there are no outliers. We can see some of these features in the box plot of the life expectancies. I've rotated the box plot to be horizontal for ease of comparison with the histogram. Note that the median is in the right half of the box, and the left whisker is longer than the right whisker. This is typical of left-skewed distributions. We can also see these features in the 5-number summary. The difference between the third quartile and the median is smaller than the difference between the median and the first quartile. And there is less distance from the center, or median, to the upper extreme, or maximum, than from the center to the lower extreme. Also, in left-skewed distributions, the mean is less than the median, since the mean is pulled down by the values in the long left tail. Let's look at the histogram for another set of data, the differences between the estimated ages using the Lagrange method and the actual ages at death for our 400 skeletons. The distribution of these data is unimodal, with the peak between -10 and -20 years. Although there may be a few more values in the extremes of the left tail than in the right tail, the distribution is quite close to symmetric about the peak. And there are no outliers. Comparing the histogram and the modified box plot, we see that the box plot is also quite symmetric, with the median near the middle of the box and the whiskers of similar length. The data values outside the fences are not outliers here, since they are not separated from the rest of the data. This symmetry can also be seen in the 5-number summary. The distances from the median to the first and third quartiles are similar, as are the distances from the median to the minimum and maximum. The mean is a little less than the median because of the small lack of symmetry in the tails that we noted, but the mean and median are still quite close to each other. Note that the mean and the median both occur in the modal bin here. We can also look at the histogram for the 2012 salaries of the New York Red Bulls soccer team. The key feature of these data is the large gap between the salaries of the 2 players with the highest salaries, Marquez and Henry, and the 23 other players on the team. The salaries of Marquez and Henry are outliers. If we remove Marquez and Henry from the data, we can look at the distribution of salaries for the remaining 23 players. Players' salaries are bounded from below by a minimum that is imposed by the league. The resulting distribution of salaries is right-skewed. The box plot shows this skew with the median slightly to the left of center of the box and a right whisker that is much longer than the left whisker. We can also see this lack of symmetry in the 5-number summary, with larger distances from the median to the 3rd quartile and maximum than from the median to the 1st quartile and minimum. As well, we have a mean that is larger than the median. The 3 examples we just looked at all had unimodal distributions. That's because unimodal distributions are by far the most common. We'll now summarize what we've seen about the relative location of the mode, median, and mean in unimodal distributions. If the distribution is symmetric, the mean, median, and mode are all approximately the same. For a left-skewed unimodal distribution, the mode is typically larger than the median, which in turn is larger than the mean. And for a right-skewed distribution, the mode is typically less than the median, which in turn is less than the mean. Earlier, we looked at these 4 examples of some of the shapes of distributions that we can see in histograms. For the symmetric and right-skewed distributions, we can see the overall features of the shape in both the histogram and in the box plot. For the bimodal distribution, the box plot fails to capture the 2 peaks, so this is a situation where a histogram can be more useful than a box plot. Unimodal and symmetric distributions of data, with histograms that have roughly a bell shape, are very common for a reason that we'll see in coming lectures, and are very important in work that we'll be doing later in the course. For data with this shape, the standard deviation is an important measure of spread or variability. The empirical rule tells us how the frequency of data values is related to the standard deviation. In particular, approximately 68% of the data values are within the range from the mean -1 standard deviation to the mean +1 standard deviation. About 95% of data values are within the mean ±2 standard deviations, and 99.7%, almost all of the data values, are within 3 standard deviations of the mean. As an example of how well the empirical rule works, we can look at the difference in estimated age from skeletal remains and actual ages at death, which we saw has a unimodal and symmetric distribution. For these data, the mean is -14.2 and the standard deviation is 14.1. 1 standard deviation on either side of the mean is the range from -28 to 0, which covers 273 of the 400 data values, or 68.3%. 2 standard deviations on either side of the mean is the range from -42 to 14, which covers 380 or 95% of the 400 data values. And 3 standard deviations on either side of the mean is the range from -57 to 28, which covers 397 of the 400 data values, or 99.3%. We can see that this is very close to the 68, 95, 99.7% that we expected from the empirical rule. Although it was derived from properties of symmetric and unimodal distributions, the empirical rule works surprisingly well in other situations. Let's see how it works for the life expectancy data, which is left skewed. I won't show all the calculations here, but the mean for these data is 69.9 and the standard deviation is 9.7. It can be shown that 128 of the 197 countries and territories in our data, that's 65%, are within 1 standard deviation of the mean. 186, or 94.4%, are within 2 standard deviations of the mean, and 197, all of the countries and territories, are within 3 standard deviations of the mean. We can see that even for this left-skewed distribution, we are very close to the 68, 95, 99.7% of the empirical rule. In this video, we've seen how to use histograms to picture the shape of a distribution of data values. In future videos, we'll see why this is such an important step in any data analysis.
In the lectures so far, we've been considering various kinds of data, and all of the variables have been what we call quantitative variables. Variables represented by numbers that can be larger and smaller and so on. Now we're going to discuss other kinds of variables, which are called categorical variables. And they're variables that just aren't represented by numbers, and we'll see how we can think about them. For context, let's remember that life expectancy data that we looked at before. This gives the number of years that people live on average in 197 different countries and territories around the world. Because these data were represented by numbers, it meant that we could compute things. We could talk about, for example, the minimum value and the maximum value. We could talk about the median. We learned about the quartiles. We used that to draw a box plot. We also computed things like the mean value and the standard deviation. We could plot things like histograms. We could talk about if they're skewed or if they're symmetric. We could talk about the extreme values of the data. These are all things that we can talk about if we have quantitative data. But there's other kinds of data too. So let's go back to that data about life expectancies and think about where it comes from. Each of those countries and territories is represented somewhere in this map. Now the data that we got also divides up the world in terms of different regions. And the way they divided up the data, they talked about the Americas, North, South, and Central, as one region. They talked about Europe and Central Asia as another region. They talked about East Asia and the Pacific as another region. They talked about South Asia as a fourth region, and the Middle East and Northern Africa as a fifth region, and finally Sub-Saharan Africa as the sixth region. In that way, they divided up the map into 6 regions. Now, that gives us some data too. If we want, we can make a list. Here's a list of those 197 different countries and territories, and for each one, which of the 6 regions it belongs to. Well, once again, it's just a jumble of text. How can we make sense of it? Let's start by considering what we did for the quantitative variables, things like the minimum and maximum and median and quartiles and box plots and mean and standard deviation and so on. Can we use these for a categorical variable like the region? No, we can't. The reality is hardly any of these things make any sense anymore for a categorical variable. So what can we do? Well, one simple thing we can do is just count. We can say how many of those 197 different countries and territories are in each of those 6 regions. Well, here's the count that we get. We see that there's 39 in the Americas, there's 50 in Europe and Central Asia, there's 30 in East Asia and the Pacific, there's 8 in South Asia, there's 21 in the Middle East and North Africa, and there's 49 in Sub-Saharan Africa. So now we have a table of numbers, and that's okay, but there's other ways we can represent it too. One nice way is what's called a bar chart. And a bar chart, as illustrated here, just presents a separate bar for each of the different categories, in this case each of the 6 regions, and for each one the height corresponds to how many elements are in that region. So in that way we've represented the counts as a nice looking little chart. Now if we prefer, instead of representing the counts, we can represent the relative frequencies, which is just what fraction of the countries and territories are in each of those 6 different categories. That's illustrated here. It looks exactly the same, except that we've divided by the total number, so now the heights of the bars actually add up to 1. Another way that we can illustrate that same data is with a pie chart, as illustrated here. A pie chart considers a round circle or a pie and chops up slices of it in proportion to how many of the data fit into each of the different categories. In this case, how many of those 197 different countries and territories fit into each of the 6 different regions. Now, pie charts say pretty much the same thing as a bar chart. We won't use them as often, but some people like them. In fact, some people have fun with them. Here's a cute little pie chart showing the amount of pie somebody's eaten or not, taking pie a little too literally. And here's another one that I think is quite cute, where they illustrate sales of Girl Scout cookies by actually making a pie out of pieces of the different cookies. Very clever. Anyway, the important thing is to understand that when you have a categorical variable, you can illustrate the counts by using either a bar chart or the relative frequencies or a pie chart. So that's pretty much all we can say for now about categorical variables. We'll get into them more in next week's lectures when we discuss the relationships between different variables. But for now, let's consider one more example. Let's go back to that skeleton data we had before from the anthropologist. Remember that this had various information about 400 different skeletons that had been studied. Well, we already talked about things like the estimated age at the time of death, or the difference between the estimated and the true age at the time of death. And those were quantitative variables, so we could talk about the minimum and the maximum and the median and box plots and quartiles and mean and standard deviation and all those things. But what about some other variables? For example, each of those skeletons has a sex. Is it male or female? Well, for that data, it turns out that 281 of them are male and 119 of them are female. So that's a categorical variable. You can't take the maximum or the minimum or the mean, but we can draw a bar chart. And here's a bar chart showing the sex of those 400 skeletons. If we want, we can also show the relative frequencies. Or if we prefer, we can make it into a pie chart. Another example of a categorical variable for these skeletons would be the mass category. That is, each of these skeletons, the people at the time of death, were categorized as being of normal weight, or underweight, or overweight, or obese. Now, in this case, 225 of the 400 skeletons were classified as normal, 74 were classified as underweight, 81 were classified as overweight, and 20 were classified as obese. Again, we could just make a table, but we could also display that as a bar chart, or if we prefer, the relative frequencies, or if we prefer, we could make a pie chart. In this way, we can illustrate the categorical variables, not in as much detail as the quantitative variables, but we can still say something about them. As we move forward and discuss the relationships between different variables, it will become more and more important to understand the categorical variables as opposed to quantitative variables and how they all fit together.
Now that we've seen a few data sets and some of the summary statistics we can calculate and plots we can create in order to get an understanding of our data, we'll now summarize some of the features of data in general. An observational unit is the person or thing on which measurements are taken, for which a number of different terms are commonly used. Examples of observational units that we've encountered already include country or territory in our life expectancy data, skeleton in our anthropological data, and soccer player in the data of salaries of New York Red Bulls players. When we talk about a variable, we're talking about a characteristic that we've measured on an observational unit. In our life expectancy data, this includes, of course, life expectancy as well as region of the world. In our anthropological data, variables include age at death, sex, BMI, the estimated age at death, the difference between the actual and estimated age at death, which is an example of a variable calculated from other variables, and the salary of our soccer players. An observed value, or observation, is our data. It is the actual value of a variable for one of the observational units in a dataset. Data are arranged in rows and columns, with one row for each observational unit and a column for each variable. Many different file formats are possible for data, such as spreadsheets and comma-separated values. If you explore the data files used in this course, you'll find that we're supplying the data in plain text files, with spaces separating the observed values of the variables. Note, as here, that categorical variables can be coded multiple ways, including as numbers. Here, a sex of 1 indicates a male and 2 a female. It's not a quantitative variable, however. As we've already seen, variables can be of various types. A variable is quantitative if it takes on numerical values for which arithmetic operations make sense. For a quantitative variable, saying that one observation is twice as large as another has a practical meaning. If one soccer player's salary, say, is twice that of another, that has a clear meaning. Similarly, saying one soccer player's salary is $10,000 more than another player's has a clear, mathematically precise meaning regardless of how much each soccer player earns. This is characteristic of a quantitative variable. Some examples of quantitative variables we've seen include life expectancy, the actual age of a skeleton at time of death, the estimated age for that skeleton, the difference between those two ages, the estimated and the actual age, and salary of the soccer players. A categorical variable records into which of several categories an observation falls. As we saw in a previous video, we treat categorical variables with different summary statistics, such as relative frequency, than we use for quantitative variables. Some examples of categorical variables we've seen include sex, which is categories male or female, BMI, when we consider it as the standard classifications of underweight, normal, overweight, and obese, and region of the world, which had 6 categories in our data. And finally, there are ordinal variables, which have a natural order. Unlike quantitative variables, the differences between two values of an ordinal variable may not be meaningful. Sometimes ordinal variables are treated as quantitative, but when doing so, we need to be careful if a quantity like, say, the mean, truly makes sense. However, the median or middle value typically does make sense for an ordinal variable. An example of an ordinal variable we've seen is the BMI classifications, since underweight is less than normal, which is less than overweight, which is less than obese. Another example of an ordinal variable is the response to a Likert item on a questionnaire, where the respondent gets to choose from strongly disagree, disagree, and so on up to strongly agree. In earlier videos, we talked about outliers and their effect on calculations of summary statistics. In the New York Red Bull salary data, there were 2 players whose salaries were much larger than every other player's salary on the team. This happened as a result of the designated player rule. This is the defining feature of an outlier, that it is separated from the rest of the data. Outliers shouldn't be ignored or routinely removed from the data. It can happen that an outlier is a mistake. In a data set of ages, say, an age of 555 is clearly impossible and was likely a typo. Cleaning data by correcting errors like this is an important first step when dealing with a new data set. It's important to try to find out the reason for unusual observations. When outliers are not mistakes, they might be the most interesting feature, and removing them would remove an important aspect of the data. But, as we've seen in previous videos, they can sometimes have an overly influential effect on summary statistics that are not robust, and they must be treated with care in the analysis. It's not unusual to report findings both with and without outliers. Sometimes a data set can include missing values. Observed values can be missing for a number of reasons. In the anthropology data set of age estimates on skeletal remains, we've been looking at estimates of age at death that were taken using the Degangi method, and the data we're using is a random subset of skeletons chosen from those for which the first rib, which we need for the Degangi estimate, was intact. It's possible for any skeleton that the first rib might be missing or damaged so that a Degangi age estimate cannot be made, and the age estimate for the skeleton would be missing. Sometimes the fact that a data value was missing tells us something about what it would have been had it been observed. Imagine a scale for measuring a person's weight that only goes up to, say, 100 kilograms. Any larger subjects who were part of the study using this scale would have had a missing value for their weight. Not including them in the analyses would bias the results by, for example, having a mean weight that was smaller than the actual mean weight would have been had the larger subjects been included. Or imagine a study where some subjects dropped out because they weren't doing well. Carrying out analyses without these subjects would make us think that the subjects as a group did better than they actually did. These types of situations require a lot of care. For our skeletal remains, we don't expect that a missing first rib has any relation to the age of the skeleton at time of death or to any other features of the skeleton such as sex or BMI or to the estimate we would have got. It may be reasonable then to assume that excluding skeletons for which we have a missing value for the Taganji age estimate doesn't have any effect on our analyses, and we can continue to work with the dataset without them. But anytime we encounter a dataset with missing values, we must consider carefully why they were missing and whether the fact that they're missing might bias the results of our work.
Installing statistical software R for Mac OSX. We will begin by opening a web browser like Safari and navigating to r-project.org. This will be the main website for the R project, and we will choose to download R. When selecting a cran mirror, choose from a location that is closest to you. For us, it will be here at the University of Toronto in Canada. We will choose to download R for Mac OSX and select the latest version of the R software. You can see the progress of your download in the top right-hand corner. Once the software has finished downloading, you will want to double-click on the downloaded package and follow the on-screen installation instructions. You will have to agree to the terms of the software license agreement, choose to install for all users of the computer, and finally click on Install. You will need your administrative password to allow for the installation of the software. Once the software is successfully installed, we can close this window and open the R software. In a Finder window, navigate to Applications and scroll down to find R. You have the option of using R or R64-bit. On newer softwares, R64-bit is recommended. This is the R console where we will type all of our commands. We are now ready to start using R. Installing statistical software R for Windows. We will begin by opening a web browser and navigating to www.r-project.org. We will choose to download R, and when selecting a cran mirror, choose from a location that is closest to you. For us, it will be here at the University of Toronto in Canada. Choose to download R for Windows and select Base if this is your first time installing R. Finally, we will select to download the latest version of R for Windows. Choose to run the downloaded file and monitor the progress of the download. Once the download is complete, run the downloaded file and choose your setup language. When following the setup wizard to install R, you can choose the default options. The installation is now complete. We can close these windows and open R. This is the R console where you will type in all of your commands. We are now ready to start using R. The 5-number summary R tutorial. In the 5-number summary lecture, we saw Jeff create many graphs to try and visualize different data sets. In this tutorial, we will learn how to create these same graphs using the R statistical software. To get started, in the R console, we will change our working directory. We will navigate to Miscellaneous, Change Working Directory, and we will choose the folder that will contain all of our data sets. This tells R where all of our data sets are located. Alternatively, we can set the working directory with the command setwd, and in brackets you can specify the path to the folder. The first data set we will work with is the life expectancy data. We will name this data set data and read it in using the command read.table, specifying in brackets the name of the file. Note that you don't need to specify where the data set is located because R will automatically look in the working directory. By just typing in the name data, we can see the 197 countries and their respective life expectancy. Note that the second column is the one that contains the actual life expectancies. We can define a new variable, lifeexp, to refer to the second column of our dataset. This way we have direct access to all of the life expectancies using just one variable name. First, we will produce the scatter plot of all of the life expectancies with the command plot. This plot is created with R's default options. To obtain the plot that Jeff created, we can change the label of the x-axis to country and the label of the y-axis to life expectancy. And we can change the limit of the y-axis from 0 to 86. Next, in the plot command, replace lifeexp with sort lifeexp to create the plot with the data sorted. To create the box plot, we can use the command boxplot, again with the y-axis labeled and the limit of the y-axis set. It is also useful to produce summary statistics for this dataset to follow along with Jeff's explanations. We can do this using the summary command. The next data set we will work with is the grades of Jeff's seminar class. Since there are only 9 observations, we can simply type them in. We will name this data set grades and input the observations using the combined command C. With the sort command, we can obtain the sorted grades, and the summary command will give us all of the summary statistics needed to create a box plot. We can also create the box plot using R with optional arguments to rename the y-axis label and change the limit of the y-axis. For the reduced grades dataset, with only 6 observations, we will choose to type them in again. And, like in our previous example, we can obtain the sorted grades and the summary statistics. The final graph we will produce will contain the sorted grades, with a line in between them. We will use the plot command again, choosing to plot the sorted data, and we will add an optional argument type equals to b, which tells R to plot both points for each observation and lines connecting them. Now try a few of these examples yourself and see how easy it is to create beautiful graphs in R. The Center of the Data R tutorial. In the Center of the Data lecture, we saw Allison produce graphs and summary statistics for 2 datasets, the skeletal remains dataset and the salaries of the New York Red Bulls. In this tutorial, we will learn how to use R to reproduce her results. Let's take a look at the skeletal remains dataset we will be working with.
Notice that our dataset has variable names on the first row and a lot more variables than we need. Our main focus will be on the variable DG difference, which is simply the difference between the actual age and the estimated age of each skeletal remain. In R, we will set the working directory with the command setwd to specify where our data is located. We will name our dataset skeleton, read it in using the command read.table, and specify using header is equal to true that the first line in our dataset contains variable names and not actual data. It is good practice to view the data by just typing in the variable name skeleton, just to ensure that we have read in the correct dataset. It also allows us to check that we have the correct number of observations, 400 in this case. To have direct access to all of the variables in the dataset simply by variable name, we can use the command attach skeleton. We can now refer to our variable of interest, the differences, by just specifying the name DG difference. We can create a standard boxplot of the data using the command boxplot, specifying the variable we want graphed DG difference. The range is equal to 0 argument specifies that the whiskers should extend to the most extreme observations. The y-axis can also be relabeled to be more informative. For the modified boxplot, we can use the same command as above, removing the range is equal to 0 argument. Without that argument, the whiskers are extended to the first observations within the lower and upper inner fences. To construct your own boxplot, it would be useful to obtain summary statistics with the command summary, which will display the minimum and maximum observation, the first and third quartiles, the mean, and the median. To double-check your work for the calculation of the mean, it would also be useful to obtain the sum of the data and the number of data values. We can do this with the sum and length commands. Then, the mean is just the sum divided by the length. We can also just use the command mean of the differences. For the 10% trimmed mean, we can specify in the mean command with the argument trim is equal to 0.1 that we wish to trim the top and bottom 10% of the observations. For the second dataset, the salaries of the New York Red Bulls, we will name our dataset NY salaries and just copy and paste in the 25 observations. To notice the extreme observations, we will produce a modified boxplot, choosing to graph the salaries in thousands of dollars. So the variable we will graph is NY salaries divided by 1,000, and we will label the y-axis accordingly. We can also obtain the median, the mean, and the 8% trimmed mean of the salaries. Note that for the 8% trimmed mean, we require an extra argument trim is equal to 0.08. Try working through some of the examples above and investigate for yourself the measures of centrality, such as the mean or median, and the effects of the extreme observations through the use of boxplots. The Spread of the Data R tutorial. In the Spread of the Data lecture, we saw Jeff introduce 3 different methods that can describe the spread of the data. Let's see how we can use R to help us understand these methods better. To get started, we will read in the life expectancy dataset and name the second column with the actual life expectancies life EXP. We are now ready to work with this variable. Jeff began with a boxplot of the data. We can reproduce this boxplot with the y limit set from 40 to 90 to get a closer look at the data. And to follow along with his lecture, we can produce the summary statistics as well. The first measure of spread we learned was the range, and we can see from the summary statistics, as well as from using the range command, that the data ranges from 47.8 to 83.4. We can do a simple subtraction of the minimum life expectancy from the maximum life expectancy to obtain the range of 35.6. The second measure of spread we learned was the inner quartile range, or IQR, which was the difference between the third quartile and the first quartile. We can do this directly with the IQR command to obtain an IQR of 12. For the next measures of spread, the variance and standard deviation, we will work with the 9 grades dataset from Jeff's seminar class. When calculating the measures of spread, it is useful to have the summary statistics to be able to calculate the range and IQR. For the variance of the grades, we can use the command VAR to obtain 87.3, and for the standard deviation, we can use the command SD to obtain 9.3. Note that the standard deviation can also be obtained by taking the square root of the variance. Sometimes it is helpful to carry more decimal places, but you might have noticed that all of Jeff's answers are rounded to 1 decimal place. We can, of course, do this in R as well with the round command, specifying that we would like to keep 1 decimal place. In Jeff's final example, he considers again the salaries of the New York Red Bulls and tries to assess the robustness of the new measures learned by comparing the measures for the original data and for the 8% trim data. We know that the 8% trim data would require us to remove the first 2 and the last 2 observations. Let's load the data in R and produce the trim data. We will call this trim data NY salaries trim. We will first set it equal to the sorted salaries, then we will specify that we wish to keep every observation from the 3rd to the 23rd in square brackets. Just to double check, we know that we started with 25 observations, so the trim data should contain 21 observations. First, we will produce the summary statistics for the original salaries, storing them each with appropriate variable names. We will combine them all under one variable, origin. Similarly, we can do this for the trim data, making sure to indicate in the variable names that the statistics produced refer to the trimmed data. We can now combine them into 2 columns with the command cbind, so they are easy to view side by side, and we'll rename the rows for reference. This allows us to see all of the summary statistics produced over the last few lectures and compare them easily to see which are robust to extreme observations. Do note that in the lecture video, Jeff uses approximated statistics, whereas we use the actual calculated statistics. Either way, the lesson remains the same. The median and IQR are robust, but the mean, range, and standard deviation are not. The shape of the data, our tutorial. In the shape of the data lecture, Allison explored the distributions of the data sets we are now familiar with through the use of a new graphical measure, the histogram. We will produce histograms for the life expectancy dataset, the skeletal remains, and the salaries for the New York Red Bulls. Again, we will read in the life expectancy data and name the second column with the life expectancies life exp. Let's investigate R's default histogram. With the command hist, we obtain a basic histogram of the data. Notice that R automatically chooses how many bins to create, gives the histogram a main title, and names the x-axis after the variable name. We can change a few of these options to get a better looking histogram that is easier to read and more informative. We can now specify that we would like the histogram to contain only 5 bins, with the argument breaks is equal to 5. Then we can change the label of the x-axis. And finally, we can change the title of the histogram. It is always advised to go through the trouble of renaming the axes or the main title, because although life_exp is a variable we know very well, to a casual reader this variable name can be very confusing and oftentimes misleading. What happens when we change the number of bins? As Allison pointed out, it might not be a good idea to do so, since increasing the number of bins can sometimes make the histogram look more noisy, and it will definitely make it harder to determine its shape. For comparative purposes, we can also reproduce the horizontal box plot of the life expectancies, with the extra argument horizontal is equal to true. Our final investigation into the shape of this dataset will be with the 5-number summary. Here we can follow Allison's reasoning as to why the data is left skewed. We can also see right away that the mean is less than the median, which should also be a clear indication. For our second dataset, the skeletal remains, we can follow a similar pattern in our investigation. First, we will begin with a histogram of the differences, DG difference, allowing R to set the default number of bins, but renaming the x-axis. And again, we will want to compare the histogram with the horizontal box plot. Finally, with the use of summary statistics, we can see that the data is fairly symmetric. Our last example will use the salaries of the New York Red Bulls. For the histogram, we will want to use the salaries in thousands of dollars, so we will graph NY salaries divided by 1,000. We will also specify, with breaks is equal to 24, that we wish to have 24 bins, so that we get a better sense of where the data lies. But even with so many bins, we still can't get a good grasp on the shape of the data because of the two extreme observations on the far right. To remove these two outliers, first we will create a new variable NY_salaries underscore outliers removed, and set it equal to the sorted salaries from observation 1 to 23. This will remove observations 24 and 25, which are the highest two salaries. The histogram of this new variable, in thousands of dollars, shows more clearly that the data is in fact right skewed. The horizontal box plot confirms this as well, and so do the summary statistics in the 5-number summary. As a final note, sometimes depending on the data, the summary command will have the resulting statistics accurate to a specific number of digits. You might have noticed that our mean of 119,900 does not agree with Allison's mean from the lecture of 119,904. We can specify in the summary command how many digits the answer should be accurate to. In our example, since the highest salary with the outliers removed has only 6 digits, we can specify digits is equal to 6 in the summary command. And for a more accurate answer still, we can choose to be accurate to 7 or even 8 digits. Categorical Variables, our tutorial. Today, Jeff introduced a new type of variable, a categorical, or otherwise known as a qualitative variable. We saw variables of this type appear in the life expectancy dataset as well as in the skeletal remains dataset, and you were able to have a better understanding of these types of variables through the use of bar charts, relative frequency bar charts, as well as pie charts. Let's take a closer look at these new graphical measures. First, we will work with the life expectancy dataset, focusing on the new categorical variable region. We can obtain the table of counts by region with the table command. This tells us, for example, that 39 of the countries are in the Americas. For future use, we will store this table under a new variable called counts. We can also obtain the relative frequencies with a simple calculation. We will store these under a variable called relative frequency, and we know that to calculate it, we can divide counts by their total. Finally, to ensure that our new variable region is properly labeled in each graph, we will store the names of the regions in the new variable region names in the order that they appear in the table of counts. We are now ready to start plotting. We'll start with a bar chart, which can be created with the bar plot command. We want the bar heights, which is the first argument, to be the counts for each region. We will choose the colors of the bars using a rainbow command, specifying that we need 6 different colors for our 6 different countries. And we will set the names for each category with the names.arg argument, specifying that the names to use are stored under region names. You'll notice right away that not all of the region names have made it on the graph. This is simply a sizing issue with R. We can try to stretch the graph to be able to fit all of the region names. Similarly, with the bar plot command, we can graph the relative frequencies we created. Notice that the graph seems to look the same, but in fact the y-axis changes to reflect not the counts, but the relative frequencies. A pie chart can be created with the pie command, specifying the counts, the colors, and the labels. For Jeff's next example, the skeletal remains, after reading in the data, recall that the command attach allows us to use the variable names that are part of the dataset. Our first categorical variable of interest is the gender of the skeletons. So, similar to above, we will generate the counts or frequencies for each sex, the relative frequencies, and create the name variable. For the names, it's useful to know that males are indicated by a 1 and females by a 0. Now we can produce the bar chart, the relative frequency bar chart, and the pie chart. Do note that the color argument requires only 2 colors in this case, since we have only 2 categories, male or female. The second categorical variable of interest for the skeletal remains dataset is the mass category, or BMI category. This variable is stored in the dataset under the variable name BMI. Try to apply the techniques learned in this tutorial to the BMI categorical variable and see if you can recreate the bar chart, relative frequency bar chart, and pie chart that Jeff displayed in the categorical variables lecture.
In previous lectures, we've seen various different kinds of data, including different kinds of quantitative variables, things like those life expectancies in those different countries and territories around the world, or things like the estimated age differences from those skeletons. We've also seen some categorical variables, things like which region of the world are those countries and territories in, or what's the sex of those skeletons. In this lecture, we're going to get a first look at how to consider the relationships between these different variables. Relationships, in some sense, are at the heart of statistics, and we're going to study them a lot. For now, we're going to begin with a simple introduction. To start, let's again consider those 197 different countries and territories around the world and their life expectancies. We've already studied these numbers, and we know how to summarize them with the 5-number summary, or with a box plot, or we computed things like their mean and standard deviation and so on. But we also said for each of these countries and territories, they fit into some region around the world, and we divided the world into 6 different regions. Now we want to ask, what's the relationship between these countries' life expectancies and the region of the world that they're in? For starters, let's consider comparing 2 specific regions. Let's consider comparing East Asia and the Pacific with sub-Saharan Africa. Now, we might think that maybe life expectancies tend to be larger in East Asia and the Pacific as compared to sub-Saharan Africa. So let's see if we can figure out if that's true. Well, we can start by looking at the countries and territories in each of those 2 regions. Now, in the East Asia and Pacific region, there are 30 countries, and their median life expectancy and their mean life expectancy are both approximately 73 years. In sub-Saharan Africa, there are 49 different countries and territories, and their median and mean are both pretty close to 56 years. So right away we can say that the sort of center of the data is quite a bit higher in East Asia and the Pacific as compared to sub-Saharan Africa. But that's not necessarily the whole story. For example, if we look at the minimum value out of all the life expectancies in East Asia and the Pacific, it's only equal to 62.48 years. Whereas if we look at the maximum life expectancy in sub-Saharan Africa, it's equal to 77.65 years, which is a lot more. So it means that the highest life expectancies in sub-Saharan Africa are certainly a lot higher than the lowest life expectancies in East Asia and the Pacific. Let's consider a little further. If we look at the first quartile of the life expectancies in East Asia and the Pacific, that works out to just under 69 years. If we look at the third quartile of the life expectancies in sub-Saharan Africa, then that works out to a little over 59 years. So in other words, the first quartile in East Asia and the Pacific is quite a bit higher than the third quartile in sub-Saharan Africa. This provides some pretty clear evidence that most of the life expectancies in East Asia and the Pacific are indeed larger than most of the life expectancies in sub-Saharan Africa. We can see this a little more clearly if we make box plots for each of the two regions and put them side by side. Here we see a box plot for the life expectancies of the countries and territories in East Asia and the Pacific, and right next to it, a box plot for the life expectancies of the countries in sub-Saharan Africa. And looking at these two box plots, we can say that sure enough, most of the box plot for East Asia and the Pacific is quite a bit higher than most of the box plot for sub-Saharan Africa. So this tells us that, yeah, we were pretty much right. It seems that for the most part, life expectancies in East Asia and the Pacific are indeed higher than life expectancies in sub-Saharan Africa. Now let's consider another comparison. Let's consider comparing again East Asia and the Pacific, this time to the South Asian countries. Well, in this case, the South Asian countries have a median and a mean, which are both pretty close to 67 years, which is a little bit less than the 73 years for East Asia and the Pacific. So maybe life expectancies are a little bit lower in South Asia than in East Asia and the Pacific. Well, we can also look at other information. For example, remember the first quartile in East Asia and the Pacific was just under 69 years, whereas the third quartile in South Asia is over 70 years. So it means that in this case, the comparison isn't quite so clear-cut. On average, maybe it's true that the South Asian life expectancies are a little bit lower than the East Asian and Pacific life expectancies, but the quartiles don't completely order themselves in the way that they did before. Again, we can see this more clearly by looking at a box plot. Here's a box plot for East Asia and the Pacific as compared to South Asia, and we can see that sure enough, each of the quantities of the 5-number summary are a little bit higher for East Asia and the Pacific as compared to South Asia, but just a little bit, and the box plots kind of have a lot of overlap to them. So this is a case where we might say there's a little bit of an effect from region, but we're not sure how significant it is. Later on, we'll get into statistical tests that in a case like this will allow us to compute whether the difference is just the sort of thing you might expect from the fluctuations of different countries, or whether it really does illustrate a fundamental difference between the regions. For now, we can say that East Asia and the Pacific appears to have slightly larger life expectancies overall as compared to South Asia, but it's not so clear-cut. Let's also consider comparing East Asia and the Pacific to the Middle East and North Africa. Now, this is a case where the medians and means for both regions are all very close to 73. So if we just look at the center or location of the data, we'd say these two regions are pretty comparable. But if we look at a box plot and see them side by side, we notice something interesting. Sure, the medians are almost exactly the same, but there's a lot more spread in the data for East Asia and the Pacific. For the Middle East and North Africa, the data is mostly concentrated quite closely around the median. Indeed, the interquartile range is only 2.15 years for the Middle East and North Africa, whereas it's 8.86 years for East Asia and the Pacific. Now, if we look at a modified box plot instead of the two regions side by side, then we can see a little more. Most of the Middle East and North Africa data is indeed concentrated very closely around the median, and that's why the quartile boxes are so small. But we can see by those little circles outside the extensions that there's a few countries in the Middle East and North Africa which have very high life expectancies, and a few countries which have very low life expectancies. So we see that in this case, the center of the data is pretty comparable, but actually the spread of the data is quite different. If we want, then we can do a box plot of all 6 regions all side by side. Looking at this box plot, we can see that Sub-Saharan Africa does indeed appear to have the smallest life expectancy of all 6 regions, and South Asia appears to be a little bit lower than the others, and the other 4 all appear to be fairly similar. Now for another example of considering the relationship of a quantitative variable and a categorical variable, let's return to our old friends, the skeletons. Remember that we have a data set of 400 skeletons. For each one, we have the difference in the estimated age at death as compared to the actual age at death. That's a quantitative variable. We also have some categorical variables, like, for example, the sex of the skeleton, whether it was male or female. Now we can ask, is there a relationship? That is, does the sex of the skeleton have an effect on this difference? Well, we know what to do now. Let's go straight to considering side-by-side box plots of the difference in ages for the male skeletons as compared to the difference in ages for the female skeletons. Looking at the box plot, we can see that the two sides are fairly similar, but they're not identical. And the female side, the values of the box plot are just a little bit lower, a little bit more negative. So it suggests that just maybe there was a little bit more negative differences in the estimated versus actual age for these skeletons when they're female as opposed to when they're male. Again, we'll have to see later whether this relationship is actually significant or not. Finally, there's another categorical variable that we've considered with these skeletons, namely their mass category, whether they're underweight or normal or overweight or obese. Well, let's consider all 4 of those cases and consider a box plot which considers the skeletons in all 4 of those classifications altogether. Once again, we can see that they're all fairly similar, indicating that there's not a huge relationship between the mass category of the skeleton and the difference in the estimated versus actual ages, but there might be a little bit of an effect. For example, we can see that the underweight ones are slightly more negative looking at the box plot. So it suggests that just maybe the differences are slightly more negative for the underweight skeletons as opposed to the other ones. Again, is that a significant change? We'll have to learn about that in subsequent lectures when we get more into the theory.
We've seen how we might examine the relationship between a categorical and a quantitative variable by seeing how the summary statistics and shape of the quantitative variable differ with the different values of the categorical variable. In this video, we'll now look at how we might examine the relationship between 2 categorical variables. Recall that when we refer to the distribution of a variable, we're talking about the pattern of the values in the data for that variable, showing the frequency of occurrence of the values relative to each other. For categorical variables, the distribution is given by the counts or frequencies, or the relative frequencies, of the observations for each of the categories of the variable. In an earlier video, for the anthropology data of measurements on 400 skeletons, we saw the distribution of mass or BMI classification and sex. Now, what if we're interested in looking at these two categorical variables together? Our anthropologist is interested in learning about how the error in age estimation is associated with the body mass index. But it's important to also consider the effect of sex here. If, say, the error in age estimation also differs with sex, it will be important to understand if the body mass index classification differs with sex for these observations. As another of the first steps in understanding these data, we should investigate the joint distribution of body mass index classification and sex so that we can learn things, such as, do we have equal numbers of females and males who are obese? Or are there equal numbers of males and females in the underweight category? And so on. We can see the joint distribution of BMI classification and sex in a contingency table, sometimes called a cross-tabulation, or a two-way table since we have two categorical variables here. In the contingency table, we classify our 400 skeletons two ways, by BMI classification and by sex. The table contains the counts or percentages of the number of observed values for males for each of the BMI classifications and for females for each of the BMI classifications. We can see from the table that 46 or 12% approximately of the 400 skeletons are underweight males, 28 or about 7% are underweight females, and so on. For a graphical display of the joint distribution, we can plot the frequencies in either side-by-side or stacked bar plots. I've constructed them so that the height of each bar is the number of skeletons in each body mass classification for each sex. From the side-by-side plot, it is clear that there are many more skeletons in our data that are males with body mass index in the normal range than skeletons in any other category. And for the female skeletons, we can also see that normal weight is also the most common of the BMI classifications. However, by looking at the total counts of the bars for males in the stacked bar plot, it is clear that there are many more males than females in our data. In fact, there are more than twice as many males as females. So although the normal weight bar is taller for males than it is for females, it is difficult to judge from these plots if a greater fraction or proportion of the males tend to be normal weight than the fraction of females who tend to be normal weight. And we need to do some more work to make a fair comparison. The marginal distribution of a categorical variable can be thought of as the distribution of only one of the variables in a contingency table. We can see it in the margins of the table by taking the row or column totals. To understand whether the BMI classification is the same for both sexes, we need the distribution of BMI classification separately for each sex. This is known as a conditional distribution.
Given that a skeleton is male, the conditional distribution is the distribution of BMI classification just for males. And similarly, we can look at the conditional distribution of BMI classification for females.
The relevant quantity that we need for the conditional distribution, and we can calculate it from the contingency table of counts, is the column percentage. That is the percentage that each count in our contingency table is of the total number of observations in each column, which we can find using the marginal distributions for the column totals. Note that for both males and females, the conditional distribution proportions sum to be 1. Graphically, we can compare the conditional distributions of BMI classification given sex by plotting the column percentages in stacked bar plots. From these plots, we can see that the proportions of underweight and obese skeletons are higher in the females than males, and the proportion of normal weight skeletons is higher for males than females.
We say the two variables in a contingency table are independent if the conditional distribution of one variable is the same for all values of the other variable. As we've noted, the distributions of BMI classification seem to differ between males and females, so it seems that BMI classification and sex are not independent for these skeletons.
We can also look at the conditional distributions of sex given BMI classification. These are the row percentages, or the proportion each count in the joint distribution is of its row total. We can see that each row in this case sums to be 1. And here, for example, we can see that 62.2% of the underweight skeletons are male.
We'll now go to another example, the result of a study to test the efficacy of a new vaccine for HPV. HPV, or human papillomavirus, is a common sexually transmitted infection that can cause genital warts and some types of cancer, most notably cervical cancer. People infected with HPV often do not have any symptoms and thus are unaware that they are at risk of transmitting the virus to others. This results in an environment in which the virus can spread readily. In the US, for example, it is estimated that 20 million people are infected with HPV, and 90% of these people are unaware of their infection. In response to the spread of the disease, vaccines have been developed and are currently being adopted widely. In Toronto, for example, an HPV vaccine is now administered free of charge in school to all girls in grade 8. There are many types of HPV. We'll only look at protection against HPV-16, the most common type that is associated with 55% of all cases of cervical cancer. We'll look at data from the Patricia study, a large study in 2004-05 that recruited over 16,000 women from 15 to 25 years old in 14 countries. The women were randomly assigned to receive either the HPV vaccine or a hepatitis A vaccine in a 3-dose regimen, and were then followed for 3 years to assess their health. In our data, we'll only include the women who received all 3 doses of the vaccine. While there are multiple outcomes we could consider, such as markers for cervical cancer and other consequences of HPV infection, we'll consider simply whether or not a subject contracted a persistent HPV infection in the 3 years of the study. Here are 4 tables that we can construct from the resulting data. Let's look at these 4 tables to see what we can learn. In particular, which numbers indicate whether or not the vaccine seems to prevent infections? The first table is the contingency table of counts, classifying subjects by whether or not they received the HPV vaccine and whether or not they acquired an HPV-16 infection. In this table, we can see that the Patricia study was large, with over 12,000 participating subjects receiving all 3 doses, and with approximately equal numbers, just over 6,000, receiving the HPV vaccine or the other vaccine. Of those who received the HPV vaccine, 23 acquired an HPV-16 infection by the end of the study period, while 345 subjects in the other group acquired an infection. In the joint distribution of proportions, we see that 3% of the subjects acquired an infection, with 2.8% of those in the group who did not receive the HPV vaccine. In the table of row proportions, we see that, of participants who received the HPV vaccine, only 0.4% acquired an infection, while in the group of patients who did not receive the HPV vaccine, 5.7% acquired an infection. And in the table of column proportions, we can learn information such as, of the subjects who acquired infections, 6.2% were in the group that received the HPV vaccine, and 93.8% were in the other group. Because the question of interest is, does the vaccine work at preventing HPV-16 infection? In this case, the row proportions, or the conditional distribution of infection status given whether or not a subject received the HPV vaccine, gives the most direct interpretation. An infection rate of 5.7% versus 0.4% certainly seems to be compelling evidence that the HPV vaccine is effective. In later videos, we'll examine whether a difference this large could have happened just by chance or if it's statistically significant. Let's look at one more example from a report on the findings from a 20-year follow-up of a large-scale study of thyroid and heart disease carried out in England in the mid-1970s. We're showing a subset of the data containing measurements on 1,314 women who were classified at the beginning of the study as current smokers or having never smoked. And we're interested in the 20-year survival status for these women. Looking at the contingency table for these data, the column proportions tell an interesting story. Of the smokers, only 24% had died, but of the non-smokers, 31% had died. Does this study show that smoking might lead to a greater chance of surviving 20 years? Of course, there's a twist here. Let's look at the column proportions for the tables of smoking and survival status broken down by age grouping. Although age is a quantitative variable, it is sometimes given in groups to illustrate a point. As we can see from both the tables of survival by smoking status broken down by age grouping, or from the side-by-side bar chart, for all age groups except the 25 to 34-year-olds, the opposite conclusion is reached. That is, the death rate is higher in the group of smokers than in the group of non-smokers. How did this happen? Age is related to both smoking status and survival. The stacked bar chart shows the age distributions for smokers and non-smokers. The non-smoking population includes more older women. When the study was started, few of the women over age 65 were smokers. But, of course, many of them, since they were at least 65 at the start, had died by the end of the 20-year follow-up period. Moreover, this study could potentially underestimate the harmful effects of smoking, since the observed small percentage of older smokers could have happened because smokers tend not to survive to age 65, so there were fewer smokers in the older age groups to enroll in the study. This is an example of Simpson's paradox, in which conditional distributions within subgroups can give the opposite conclusion to conditional distributions for the combined observations. Age here is a lurking variable. We need to always watch for lurking variables which, if taken into account in our analyses, might affect our conclusions. In some upcoming lectures, we'll talk about data collection and how to design a study to mitigate the effects of lurking variables.
In previous lectures, we've discussed the relationship between different variables when at least one of them was a categorical variable. Now we're going to consider the relationship between two different quantitative variables. To get an example, let's go back again to our map of the world and to different facts and figures about the different countries and territories of the world. We've already considered the life expectancy in the different countries, and we've already considered which region these different countries and territories are in. Now we're going to consider two more variables. One is the average wealth of the country, or the GDP per capita for the country, measured in constant 2,000 US dollars for comparison. And later we're going to also consider the HIV infection rate, that is, what percentage of adults in those countries are infected with HIV. Now, you might think that the more wealthy a country is, the higher the GDP per capita, that might mean the higher the life expectancy as well. So how can we examine this relationship? Well, life expectancy and also the GDP per capita are both quantitative variables. One thing we could do if we want is we could convert the wealth variable into a categorical variable by just breaking up all the countries and territories into 4 different categories. That is the poorest quarter of the countries and territories, and the second poorest quarter, and the third poorest quarter, and finally the richest quarter. That gives us 4 different values for a categorical variable. And then we already know how to examine the relationship of that categorical variable with a quantitative variable like life expectancy. Namely, we can do the side-by-side box plots. So here we see box plots for the life expectancy of the poorest quarter of countries and the second poorest and the third poorest and the richest. And looking at it, it does seem pretty clear that the poorest quarter of the countries, for the most part, have the smallest life expectancy, and the richest quarter of the countries, for the most part, have the highest life expectancy. So that suggests there's a relationship. But in a way, we haven't used the full information of the wealth variable. We've just divided up all the countries into 4 different groupings. So what if we wanted to use the full quantitative variable of the wealth, of the GDP per capita? Well, one thing that we could do is produce a scatter plot, as is shown here. In the scatter plot, each of the countries and territories gets a little dot where the horizontal axis illustrates the wealth, that is the GDP per capita, and the vertical axis illustrates the life expectancy. Now, if we look at it, it looks like just a crazy collection of dots, but we can start to see some patterns, and it does look like the countries with the highest wealth, the highest GDP per capita, also tend to have the highest life expectancy. We'll learn later how to fit a line of best fit through a plot like this, and if we put the line of best fit in, we can see that sure enough, it's moving upwards to the right, which is an illustration of the positive relationship between these two variables. The higher the wealth gets, the higher the life expectancy gets too. We can also compute something called the correlation between these two quantitative variables. Now, the correlation has a kind of complicated formula that's written here. It has to do with the products of the values of the data minus their means, and then we normalize it by dividing by the square root of the sums of the square deviations. So it seems kind of complicated. Well, one way to get some intuition about it is if the variables yi were actually the same as the xi, that is, if these two different quantitative variables were actually the same, or if they just differed by some sort of a positive linear relationship, as shown here, then the correlation would be equal to 1. To plus 1, and we'd say we have a perfect positive correlation between these two variables. On the other hand, if the yi's were the negatives of the xi's, or more generally had a negative linear relationship, then we could work out that this correlation would actually be equal to minus 1, and we'd have a perfect negative correlation. All the other correlations would be somewhere in between minus 1 and 1, and they would illustrate the extent to which the variables either increase together if the correlation is positive, or one increases and the other one decreases if the correlation is negative. We should also remember that correlation, like lines of best fit, only captures the linear aspects of the relationship between two variables. In some of the examples we're considering here, there are also nonlinear effects which aren't captured by the correlation or the line of best fit. So what about for that life expectancy and the wealth of the countries? Well, in that case, we can compute the correlation. And we see here that it is indeed positive, and it is indeed pretty high. It's not 1, but it's getting up there. So this shows that, yes, indeed, there is a clear positive relationship between the wealth of a nation and the life expectancy of a nation. For another example, let's consider that variable of the HIV infections, specifically what percentage of the adults in that country have HIV. In this case, we might expect that the more HIV, maybe the worse off the country is and the lower the life expectancy is. How can we test that? Once again, we have two quantitative variables, in this case, life expectancy and the percentage of HIV infections. Once again, we can do a scatter plot. In this case, the scatter plot shows on the horizontal axis the percentage of HIV infections of adults in each of the countries and territories, and on the vertical axis, the life expectancy of that country or territory. Well, once again, we see the dots are kind of all over the place, and it's a little hard to make sense of it, but once again, we can see that there is some sort of a relationship. Indeed, in this case, we can see that the countries which have the highest percentage of HIV infections sure enough tend to have the lowest life expectancies. So this suggests a negative relationship, as we might have expected, a negative relationship between HIV infections and life expectancies. We can also compute the correlation coefficient, again, as we did before. And in this case, when we work it out with that complicated formula, or get the computer to do it for us, we see we get quite a negative value for the correlation as shown here. So this illustrates that, as we might have expected, when a country has more HIV infections as a percentage of adults, it probably tends to have a lower life expectancy too. We'll come back to these relationships later on. For now, let's look at one final example, this time with our old friends the skeletons once again. In this case, remember, one of our main variables was the difference between the estimated age of the skeleton at death and the actual age of the skeleton at death. We might wonder, what other variables is that influenced by? Well, one is the body mass index, or the BMI, of the person at the time of death. We might think that if the person was heavier, had a larger BMI, maybe that made it harder to estimate their age, or maybe easier, or maybe it made the estimates tend to be too large or maybe too small. We might not be quite sure, but we might think there's some relationship. Well, now we know how to test it. We can once again draw a scatter plot. And here's a scatter plot where the horizontal axis is the BMI, the body mass index, and the vertical axis is the difference between the estimated age minus the actual age at death of the skeleton. Looking at this scatter plot seems maybe the most confusing of all because there's dots all over the place. Well, once we learn how to do lines of best fit, then we will be able to see that in this case, the line of best fit is sloped slightly positive. So it means that when the BMI gets larger, then the age difference tends to get slightly larger. We can also once again compute the correlation coefficient, or let the computer do it for us. In this case, we get a correlation which is equal to 0.136. So it's not large, it's fairly close to 0, but it is a little bit positive. So once again, it suggests that when the BMI gets larger, then the age difference also gets a little bit larger. Now we'll return to issues of relationships between variables throughout the rest of the course. But for now, we can see that using such concepts as scatter plots and correlation, we have our first understanding of the relationship between two quantitative variables.
The goal of statistical work is to make rational conclusions or decisions based on the incomplete information we have in our data. This process is known as statistical inference. In inferential statistics, we want to be able to answer the question, if I see something in my data, say a difference between two groups or a relationship between two variables, could this be simply due to chance, or is it a real difference or relationship? If we get results that we think are not just due to chance, we'd like to know what broader conclusions we can make. Can we generalize them to a larger group or even perhaps the whole world? Or perhaps our results support a theoretical model. And when we see a relationship between two variables, we'd like to know if we can say that one variable causes the other to change, or if we just think that the two variables are associated with each other. Whether or not we can answer these questions, the methods we use to do so, and the correctness of the conclusions that we can make all depend on how the data were collected. In this video, we'll look in particular at how to collect data to ensure that we can make generalizations from our data to the group that we're interested in. A fundamental feature of data is that they naturally have variability associated with them. We've seen how we can picture the nature of that variation in box plots and histograms, and how we can quantify it with summary statistics such as the interquartile range and the standard deviation. In the process of statistical inference, we can imagine that we have a real world where we have our observed data, and a theoretical world where we have scientific models that we think give plausible explanations for how our data arose, and statistical models that explain the variation in the data. The inferential process connects what we've observed in the real world to what we can say about the theoretical world. Often we're interested in making conclusions about a particular group, which could be all people, or all Canadians, or women aged 15 to 25, or whatever else we're studying, such as countries or skeletons. The group we're interested in making conclusions about is our population. When we collect data about the entire population that we're interested in, this is called a census. Most countries carry out censuses on all people living there every few years in order to better understand them. But in most situations, taking a census is impractical because it is too time-consuming or expensive. Sometimes it's also impossible. In some situations, such as testing a manufactured product, it might be necessary to destroy the item in order to study it, and a census would then be impossible. When we can't conduct a census, we often collect data on a sample from our population, and our goal is to make conclusions about that population. In this case, our population corresponds to the theoretical world that we're interested in. Our statistical model can be used to describe the variation in the data in the population, as well as how statistics we calculate from our data vary from one sample to what we would have had if we selected another sample. A typical example of this is a poll. Our population is all people living in an area, and we're interested in what they think about an issue, or how they would vote if an election was held that day. A poll would ask a sample of the people in order to make conclusions about the opinions of all of the people, or the population. Recall that a statistic is a value calculated from our observed data. Typically, a statistic is chosen to estimate a feature of the theoretical world or the population. The feature of the theoretical world or population is called a parameter. We use statistics to estimate unknown parameters. We want our statistics to be appropriate estimates of the population parameters. That is, we want to be able to generalize what we observe in our data to our population. In order to do this, the sample needs to be representative. Even a sample of a small number of observations, if the sample is representative, can give good estimates of parameters regardless of the size of the population. The key to selecting a sample that is representative is to use randomization. Using random selection ensures that we don't systematically exclude or over or underrepresent any part of the population. There are multiple methods of collecting a random sample. The simplest is a simple random sample. In a simple random sample, each possible sample of size n from the population is equally likely to be the sample that is chosen. You can think of selecting a simple random sample as putting all members of the population into a hat, mixing them well, and randomly and blindly picking the sample from the hat. More complicated methods include stratified sampling, in which we take simple random samples from subgroups of the population. Typical subgroups for stratified random sampling include provinces or states when taking a sample of the people in a country, or genders or age groupings, and so on. Stratified sampling is sometimes more convenient, ensures that the characteristics of each subgroup can be examined, and can give more accurate estimates if there is less variation in a subgroup than there is in the whole population. Cluster sampling is useful when it is easier to select groups instead of individuals from a population, and is often a less expensive way to get a random sample. As an example of cluster sampling, if our population is, say, all students in an area, it may make more sense to randomly select schools than students and take our measurements on the students in the selected schools. Cluster sampling is useful if each cluster is representative of the population. For the purposes of this course, we'll stick just to simple random samples. Many samples that are used in studies are not random samples. In a systematic sample, the population is put in some order and then, for example, every 5th or 10th or 100th unit is selected for the sample. This is fine if the ordering has no meaning and if we randomly pick which observation we start selecting on, but it can sometimes lead to samples that are non-representative because there is some structure to the list, such as hidden repeating patterns. In a convenience or volunteer sample, our sample is the units that are available or choose to participate. This almost always results in an unrepresentative sample. Say I wanted to learn about the views in the general population of the importance of statistics, and I asked the students in this course, since I can conveniently reach you, for your view of statistics. However, your view is not likely to represent a population that also includes people who have never taken or do not want to take a statistics course. If a sample is not representative, it can introduce bias into our results. We say that a sample is biased if it differs from its corresponding population in a systematic way. This can result in statistics that are consistently too large or too small. Bias can occur because of the way the sample was selected, or because of the way the data were collected from the sample. If the sample was selected in such a way that we miss or underrepresent part of the population, we have selection bias. For example, imagine a phone survey that only calls landlines. We would miss everyone that only has cellular phone service. Measurement bias or response bias occurs because the data are collected in a way that elicit a response that is off from the true value in a systematic way. Response bias can occur because of improperly worded questions that may lead the respondent to give an opinion for or against a contentious issue, or because a question asks about a controversial issue for which people may not want to give their true opinion. Measurement bias occurs because the measuring instrument is faulty in some way. Often people who were chosen as part of a random sample choose not to respond to surveys. Non-response bias occurs if the individuals that do not respond differ in a systematic way from those that do respond. For example, suppose working parents tend to be too busy to answer surveys. Then their views will be underrepresented, which is an example of non-response bias. There are many examples of non-representative sampling that have led to resulting data that are not reliable or representative. A classic example is the Literary Digest poll of the 1936 U.S. presidential election. Literary Digest got responses from 2.3 million people, a huge sample, and based on these responses, they predicted a 3-to-2 ratio of votes in favor of the Republican candidate. However, his Democratic opponent won. So what went wrong? The people surveyed either subscribed to the magazine or owned a car or a telephone. In 1936, this was only wealthy people. This is an example of selection bias. Moreover, this survey was voluntary response, which typically overrepresents angry people or people who want to change, so non-response bias also comes into play in this example. Another example that caused a lot of controversy in Canada, including the resignation of Canada's chief statistician, was related to changing a survey from mandatory response, which ensures there is no response bias, to voluntary response. In 2010, the Canadian government decided to replace the mandatory long-form census questionnaire, which was sent to a random sample of 1/5 of Canadian households, with the new voluntary response National Household Survey, which was sent to a sample of 1/3 of households. Some more households got the survey, but now it was voluntary response. Many groups, including provincial governments, religious, charitable, and business organizations, and the Statistical Society of Canada, opposed the change. These groups argued that voluntary response will lead to non-response bias. For example, one could imagine that recent immigrants may be less likely to respond, and thus they would be underrepresented in the sample. Yet part of the purpose of the survey was to identify the need for social programs, some of which would benefit recent immigrants. Statistics Canada has since cautioned that the results of the voluntary survey are not comparable to results from the previous mandatory response survey, and caution must be exercised when evaluating trends. If our goal is to collect sample data that we can use to generalize about a population with no bias in our result, we need to select a random sample. In upcoming videos, we'll discuss how the method we've used to collect our data can affect the strength of the conclusions that we can make. When carrying out a study, if we observe an interesting relationship between two variables, and we've concluded that it doesn't seem to be just due to chance, we might want to ask the question, does changing one of the variables cause the other variable to change? In this video, we'll begin to investigate whether or not we can answer that question. Here's a headline that concerned those of us who love eggs. Can they really be as great of a cause of heart disease as smoking is? Or maybe it's possible that people who eat a lot of eggs also tend to eat a lot of fatty foods, and so there are other dietary factors that contribute to heart disease rather than the eggs. Another recent headline reported on the negative effect on IQ of teenagers smoking marijuana. But maybe it says more about who smokes marijuana than the actual effects of the marijuana. For example, socioeconomic status has been blamed as a potential alternate factor contributing to the drop in IQ. If we want to be able to make causal conclusions about one variable causing another, we need to control how the data were collected. Let's start with a general paradigm for our study. For simplicity, we'll assume that we're interested in comparing just two groups, and these two groups are in two different situations. There is a particular variable called the response variable, or outcome, that we're interested in comparing between the groups. This could be cardiovascular disease risk, depending on whether or not one eats egg yolks, or IQ in pot smokers and non-pot smokers, or error in age estimation between males and females, or life expectancy across 2 geographic regions, or infection rates for a vaccinated versus a non-vaccinated group. An explanatory variable is any variable that might explain differences that we observe in the response between the groups. An important concern when planning a study and analyzing the resulting data is the possibility of confounding variables. Confounding variables affect the response and have different values in the different groups we're comparing, so that it is impossible to tell if differences between the groups are due to the group composition or due to the confounding variables. To avoid having confounding, again, we need to collect the data carefully. Here are some ways we could collect some data. We often hear anecdotes about how a change in diet or environment has resulted in miraculous improvements to an acquaintance's health. For example, a close family member of mine eliminated gluten from his diet, and subsequently he lost weight. So, should all of us looking to lose a few pounds eliminate gluten? Not based on the strength of the evidence provided by this anecdote. It's a story about only one person, and I can tell you that this person happens to drink a lot of coffee, and he's had to avoid all the pastries in the coffee shop since giving up gluten. So we can't make any general conclusions based on an anecdote. 2 other and better methods of data collection are observational studies and experiments. The advantage of an experiment over an observational study is the strength of the causal conclusions we can make. I've ordered these methods of data collection from worst to best in terms of the strength of the conclusions. We'll talk about experiments in more detail in another video and focus on observational studies for the rest of this one. In observational studies, as the name implies, the data are measurements of existing characteristics of a group or groups of individuals. The goal is typically to make conclusions about a population based on the sample of individuals we've observed, or to compare a measurement on individuals between different groups. Because existing characteristics are being observed, the investigator has no control over which group an individual belongs to. In contrast, in an experiment, the investigator imposes some kind of intervention on the individuals being studied, perhaps assigning some to one group and some to another. Experiments are the gold standard for making causal conclusions, but for now, we'll focus more on potential issues with observational studies. Let's look at an example of an observational study and discuss why we need to be careful when stating the conclusions of the study.
The study we'll consider was published in the New England Journal of Medicine in May 2012. It was about the relationship between coffee drinking and mortality. Headlines in the New York Times and the Toronto Star reported that coffee may help us live longer. The Washington Post, in contrast, was a little more reserved. So, should we be pausing now for a coffee break? Here are a few details about the study. In 1995, the researchers collected data on over 400,000 men and women aged 50 to 71 and then followed them until 2008. By then, over 52,000 of them had died. They asked the question, did the amount of coffee these people drank affect how much longer they lived? The study is an example of an observational study. Subjects weren't told how much coffee to drink, they just did what they would do otherwise. In all observational studies, we have to be careful about interpreting our observed associations. Here, our explanatory variable is the amount of coffee drank, and the outcome is how much longer the subjects lived. Suppose the coffee drinkers tended to live longer, so there's a positive association. It may be tempting to say coffee causes long life, but there are other possible reasons why an association between coffee and longevity may have been observed. In observational studies, there are at least 5 mechanisms that could result in an observed association between the outcome and the explanatory variable. What we'd usually like to show is that changes in the explanatory variable cause the outcome to change. However, sometimes the outcome causes the explanatory variable to change. This is known as reverse causation. In our coffee study, maybe people with chronic health conditions who are more likely to die tend to purposely avoid coffee. It's also possible that the relationship is just coincidence. Another possibility is that both the outcome and the explanatory variable result from a common cause. Then the observed association is not because the explanatory variable causes the outcome to change, but because the common cause causes both to change. Whether a subject had diabetes is a possible common cause for the coffee study. Perhaps because of dietary restrictions, diabetics drink less coffee, and diabetics also tend to have shorter lives. And finally, there could be confounding variables. Confounding variables vary with the explanatory variable, so we don't know if we can attribute changes in the outcome to the explanatory variable or to the confounding variable. One of the many possible confounders in the coffee study was smoking. Smokers tend to drink more coffee, so smoking status is associated with our explanatory variable. And smoking also has a causal effect on our outcome, length of life. We can't fully understand the effect of coffee on length of life unless we adjust for smoking. Imagine if a study showed that coffee drinking was associated with shorter lives. Could we blame it on the coffee or the associated smoking? In observational studies, even when we observe an association, we can't conclude that the explanatory variable has a causal relationship with the outcome. There are at least 5 mechanisms that can result in the association.
As we saw in a previous video, in the example with Simpson's paradox, there are also variables that can be lurking, sometimes also called hidden variables. A lurking variable is a variable that is not accounted for in the analysis, but it affects the association being considered. In the previous video, we saw the effect of age, which was associated with mortality, our response, and also with smoking, our explanatory variable. And when age was considered in the analysis, it reversed the nature of the association between smoking and mortality. Lurking variables can be confounding variables, as in this smoking, age, and death example. They can also be the source of a common response, or just another variable that, if we had considered it, it would change the nature of the relationship we're looking at. In the coffee study, method of preparation is a possible lurking variable. We can't say if differences in the composition of espresso versus filtered coffee affect the protective effects of coffee, and thus would influence the relationship between coffee drinking and length of life. Controlling for confounding variables is a difficult part of the analysis of any statistical study. In another video, we'll talk about the use of experiments to mitigate the possibility of confounders. In this video, we'll introduce some of the ideas behind using experiments to collect data. Experiments are the gold standard, allowing us to make causal conclusions. They allow us to consider questions such as, if I observe fewer infections in a group that wasn't vaccinated versus a group that was, can I conclude that it was the vaccine that caused the lower infection rate, or could it be something else? Or say a new teaching method results in better learning outcomes. Can I definitely attribute the improvement to the new method? We'll start by introducing some of the vocabulary that is used in experiments. The outcome, or response variable, is the variable that we are interested in, measured on each of the individuals or entities participating in the study. It is sometimes called a dependent variable because we are typically interested in how it depends on the values of the other variables, which are the explanatory variables. Explanatory variables, or predictors, or independent variables, are variables that we believe affect the response. The key feature that separates an experiment from an observational study is that in an experiment, the researcher manipulates the explanatory variables to see the effect on the response variable. An example of an experiment that we've already seen is the Patricia study to examine the efficacy of a vaccine at preventing infections with HPV. In the Patricia study, we were interested in whether or not the subject in the study acquired an infection, so that is our response variable. Response variables can be categorical or quantitative. In this situation, we have a categorical response variable with 2 categories. Yes, the subject acquired an infection in the study period, or no, they did not. In this example, the explanatory variable is also categorical. We believe that getting the vaccine affects the chance of getting an infection, and the explanatory variable is the vaccination status, with possible values yes or no. In an experiment, the investigator observes how a response variable behaves when he or she manipulates one or more explanatory variables. Since there are only a finite number of values of the explanatory variable that the researcher can possibly study, explanatory variables in experiments are typically categorical and are called factors in this setting. The values of a factor that are studied in an experiment are its levels. In our HPV vaccine example, the factor is vaccination status with levels yes or no. A particular combination of values for the factors is called a treatment. When there is only one factor, as in the HPV study, the treatments are the levels of the factors. But it's also possible that an investigator might want to simultaneously manipulate two explanatory variables to see the effect on the response. As an example, imagine a study comparing two drugs, we'll just call them drug A and B, each at two different doses, high and low. Then in this situation, we have two factors, each with two levels, but four different combinations, drug A in high dose, drug A in low dose, drug B in high and low dose. So in this case, there are four treatments. In experiments, the participating subjects or individuals are called experimental units. Sometimes treatments are given to groups of people or things, like all of the students in a class receiving a new teaching method, or all of the plants in one pot receiving a new type of fertilizer. The experimental unit is then not the individual student or plant, but the whole class or pot. Using this vocabulary, the key feature that separates an experiment from an observational study, again, is that in an experiment, treatments are imposed on experimental units by the researcher so that the effect of the treatments on the response can be seen. Extraneous factors are factors that are not of interest in the current study, but are thought that they might affect the response. They need to be controlled to rule out the possibility that the extraneous factor is causing any observed differences in the response. To control for an extraneous factor, we have a couple of different options. The first option is to hold it constant. Say we think that the HPV vaccine might work differently on males and females. We can then make the decision to say study only females. If we think it might work differently in different age groups, we could choose to study only one particular age group. This limits the generalizability of the study, but it also eliminates the potential of having the extraneous variable confound the results. The second method of controlling for extraneous factors is to use blocking. A block is a group of experimental units that are similar in the extraneous factor, and all treatments are randomly assigned to experimental units within each block. If we wanted to study the effects of the vaccine, and we wanted to include different age groups which might have differential response, we can treat age group as a block and randomly assign treatments within each age group. So in each age group, we have subjects who both receive the vaccine and do not receive the vaccine. But what about extraneous factors that can't be controlled? And even more of a concern, what about the extraneous factors that haven't been identified, just because we missed something, or perhaps because there are potential extraneous factors, maybe a genetic mutation, that hasn't yet been studied, so we don't know that it's an extraneous factor? The solution is to use randomization. By randomly assigning individuals to treatment groups, we can ensure that any differences that exist between the groups in any possible extraneous variables are just due to chance. And the fact that we expect to see some differences due to this chance variation is part of our statistical model. After randomization, when we average out this chance variation, the treatment groups are essentially the same. Once we have a randomized experiment to compare treatments, we have a study for which, if we observe differences among the treatment groups, we can conclude that it was the different treatments that caused the difference in the response. The idea here is that we've eliminated any other differences between the groups. So if the response variable is different, the only explanation is the different treatments, and cause and effect conclusions can then be made. There are three fundamental principles of experimental design. Control the identified extraneous variables by blocking or holding them constant. Randomly assign experimental units to treatment groups. And use replication. We haven't talked about replication yet. And here I'm not talking about replicating an experiment to check whether a result found in one study also holds when you do another study. While this is an important part of the scientific process, we're currently only talking about single studies. So what I mean by replication here is that we need to apply each treatment to more than one experimental unit. Having replicates allows the researcher to estimate variability in the measurement of the response, which we can't do if we only have one observation for each treatment, and ensures that the treatment groups are more comparable in values of the extraneous factors by having the opportunity to have different values of the extraneous factors within each treatment group. The word control also has another meaning in experiments. Experiments often have what we call a control group. If the goal of an experiment is to show that a treatment affects the response, you need to have at least one other group for comparison. It's possible that the simple act of studying an experimental unit causes it to change. Studying at least two groups undergoing the same experiment allows us to compare them under the same circumstances. A comparison group in a study could get a different treatment or no treatment. It is called a control group if it either does not receive a treatment or receives the current standard treatment if there is one. The control group is itself a treatment group, and if there is only one factor, control is considered a level of the factor. So the only way to establish a causal relationship is to carry out a randomized, controlled experiment. So why would anyone carry out a study that's not an experiment? The answer is simple. It's just not always possible for ethical or practical reasons. If we want to study the effect of smoking on human mortality, we can't randomly assign some people to smoke a pack a day and some people not to. That would be unethical. For studies on humans, we need to have sufficient doubt about the benefit of a treatment that we do not feel that we are unfairly exposing some of the subjects to an inferior treatment in order to carry out an experiment. If we're interested in how the explanatory variable GDP affects the response of life expectancy for countries, we can't manipulate the GDP of a country, so carrying out an experiment is not practically possible. Let's look at one more example of an experiment. This story is slightly adapted from a project presented by two Montreal students at the 2011 Canada-wide Science Fair. This project was the winner of the Statistical Society of Canada Award for Excellence in the Use of Statistical Methodology, which they won for their excellent example of a well-designed experiment. The students were interested in ischemic preconditioning, which is a technique to create resistance to loss of oxygen through loss of blood supply to tissues. Ischemic preconditioning works by applying brief episodes of restricted blood flow in order to protect against damage from a subsequent longer-term episode. The students were interested in whether a similar technique could be used to improve sports endurance. They provided ischemic preconditioning using a blood pressure cuff. They applied a pressure of 20 pounds to some of their subjects and, for comparison, minimal pressure, nominally 0 pounds, to other subjects. They also compared applying the pressure for 10 minutes versus 20 minutes. So there were a total of 4 treatments, the 4 combinations of the 2 pressures and the 2 lengths of time applied. Each treatment was applied to 10 teenage males, so there's our replication. Since there are 4 treatments, there were 40 participating teenagers, and these are the experimental units. They were chosen to be of similar athletic ability. After application of the treatment, the length of time the teenagers could stay in a wall squat position was measured. This is the response. Note the use of a control group here. The students needed to know if ischemic preconditioning worked, so they gave a sham treatment of 0 pounds to some of their experimental units, some of whom got 0 pounds for 10 minutes and some for 20 minutes. Moreover, to control for extraneous factors, only a specific group of people were studied, namely male teenagers of similar athletic ability, chosen because they participate in sports at school. Although this wasn't done, another way they could have controlled for extraneous factors was to use blocking. For example, they could have enrolled both athletes and non-athletes in the study and assigned the 4 treatments to subjects within each of the athletic groups. Another of the principles of experimental design is randomization, and the 40 experimental units were randomly assigned to which of the 4 treatments they received. This ischemic preconditioning experiment also illustrates some other characteristics of excellent design, which should be used when appropriate and possible. The students use blinding. Blinding, if it can be used in an experiment, reduces the potential for bias, since people don't know if a treatment is in place or not. Subjects can be blinded, meaning they don't know which treatment they received. The person measuring the response can also be blinded if he or she does not know which treatment was given to which participant. Experiments can be single-blind, meaning only one type of blinding was used, or double-blind if both types of blinding were used. The ischemic preconditioning experiment was single-blind. Subjects did not know which treatment they received. And they used a placebo. People often show change when participating in an experiment, whether or not they receive a treatment. This is known as the placebo effect. For this reason, the control group is often given a placebo, which is something that is identical to the treatment received by the treatment groups, except that it contains no active ingredients. So the subjects aren't aware of whether or not they're receiving a treatment. In our ischemic preconditioning experiment, the placebo was the application of 0 pounds pressure to some of the experimental units. Randomization plays 2 key roles in data collection. This table summarizes those 2 roles. By using random sampling, we get a representative sample and ensure that we can generalize our results to a larger group or population free of any selection bias. Later on in our inferential procedures, we'll use a statistical model that accounts for the random variation that causes our sample to differ from other samples that we could have possibly chosen in another random selection. Randomization also plays a key role in experiments. Randomly assigning experimental units to the treatments they receive eliminates the effects of extraneous factors, allowing us to make causal conclusions. While the extraneous factors may vary from treatment group to treatment group somewhat, randomization ensures that these differences are due to chance variation only and not any systematic difference that could confound our interpretation of the effect of the treatment. So if we want to make causal conclusions that we can generalize to an entire population, we need to randomize both in our selection of our experimental units and in assigning treatments to experimental units.
Relationships between quantitative and categorical variables are tutorial. With the help of the categorical variables introduced last week, Jeff explored a new concept today. How do we describe the relationship between the quantitative variables we were familiar with and the new categorical variables we learned? Let's take a look at a graphical measure for exploring these types of relationships, namely the side-by-side box plot. In the life expectancy dataset, let's first rename the columns with the command callNames and attach the dataset so that we have access to the variable names. Our main purpose will be to compare a quantitative variable life expectancies, or life EXP, amongst different levels of a categorical variable, region. If we wish to do so, we will need to somehow separate our dataset into the different regions. Now there are 2 ways to do this. The first way is to index into the dataset. So after the dataset name, we can specify in square brackets that we wish to obtain all the rows, that's the first entry,
for which region is equal to EAP, or East Asia Pacific. Notice the double equal sign when we are checking for equality. We need an extra comma after this to indicate that we wish to keep all columns. Another way to achieve the same results is to split the dataset by region with the split command. This is fairly straightforward by specifying the dataset name and the variable region which you would like to split it by. This will create 6 new datasets, each corresponding to a different region. To work with a particular region at a time, like the East Asia Pacific region, we can specify with a $sign which region we would like to use. We will choose to use the first method in this tutorial, but I encourage you to try using the second method as well. Our first goal will be to produce summary statistics for the life expectancies of 2 different regions, East Asia Pacific and the Sub-Saharan Africa. So let's define 2 new variables, life EAP and life SSA, to indicate these 2 subsets. And for good measure, let's take a look at them again to make sure we got what we wanted. Now we can produce summary statistics for these 2 regions, of course remembering that the second column in these subsets of the dataset contain the actual life expectancies we're interested in. If we are interested in whether there is a difference in life expectancies between the East Asian Pacific region and the Sub-Saharan Africa region, we can produce side-by-side box plots. We will again graph these using the boxplot command. We will specify that we wish to graph the life expectancies for the East Asian Pacific subset and for the Sub-Saharan Africa subset. We will set ranges equal to 0 for an unmodified boxplot, set the color of the borders of the box plots with the border argument and the rainbow command. And finally, we will set the names for the 2 box plots in the order that they were entered, and give the box plot a main title. If we wish to produce side-by-side box plots of life expectancies for all of the 6 different regions, we can do this with a much simpler command. The first argument in the boxplot command will be lifeexp tilde region. This will indicate that we wish to split the life expectancies by the different levels of region. The splitting is done automatically. No need to create different subsets. Jeff also showed side-by-side box plots for the age difference in the skeletal remains dataset. He considered whether there was a relationship between sex and age differences, as well as mass category and age differences. Try to duplicate his results with the tools learned today. Relationships between 2 categorical variables R tutorial. In our last R tutorial, we saw a graphical measure for describing the relationship between a quantitative and categorical variable. Today, Allison discussed the relationships that can occur between 2 categorical variables. In this R tutorial, we will learn how to obtain the distribution of 1 categorical variable, the joint and conditional distributions for 2 categorical variables, and we will learn how to plot side-by-side or stacked bar plots. Let's remind ourselves about the skeletal remains dataset. Our focus today will be on the 2 categorical variables, sex of the skeleton and its BMI or mass category. A quick housecleaning issue we should address before starting. When a categorical variable is read into R, by default the categories are recorded in alphabetical order. This means that any table or graph we produce for the BMI variable will have the categories in the following order: normal, obese, overweight, underweight. Of course, we know that there is a much more logical order to the categories, that is, underweight, normal, overweight, and obese. We can change the order of the levels in R with the factor command, specifying explicitly what order the levels should be in. We can similarly relabel the sex variable, indicating the levels, 1 or 2, and the labels, male or female. Let's first obtain the distribution of the BMI categorical variable with the command table. Recall that the relative frequencies can be obtained by dividing each entry in the table by the total sample size, 400. We can combine the frequencies and relative frequencies for better viewing. Similarly, we will do this for the sex categorical variable to obtain its distribution. For the next few examples, we will need to install a new package called Gmodels. Packages in R are like tool belts. They each contain specific tools that we can use depending on our needs. We will navigate to Packages and Data, Package Installer, and click on Get List. Now we can search for Gmodels. Select the package, select Install Dependencies, and finally Install. You'll notice the process of the installation in the R console, and once it has finished installing, you will see the prompt again. We will need to load this new package by saying library gmodels, so that we may use some of the commands contained in the package. We now have access to a new command called crosstable. This command generates the joint distribution and conditional distributions for two categorical variables. Let's create these for the BMI and sex variables, choosing to suppress some of the output with the argument prop.chi² is equal to false. First, we'll note that there is a legend specifying the contents of each cell. For example, if we extracted the first entry in each cell, we would get the joint distribution, or the contingency table, of sex and BMI. An easier way to see each of the nested tables is by typing in joint, the saved cross table. Here we can see the first table is the contingency table. The second table is the conditional distribution of sex given BMI. The third table is the conditional distribution of BMI given sex. And the last table is the contingency table displaying relative frequencies. We will save the contingency table with the counts to be able to construct the side-by-side bar plots. With the bar plot command, we will specify the counts that need to be graphed. We will specify that we wish the bars to be beside each other, with the beside is equal to true argument. We will set the colors and labels for the X and Y axes. It's useful to have a legend for these types of graphs, so that we know which colors indicate which categories for the BMI variable. Let's build our legend with the legend command. The first argument specifies the position of the legend, here at the top right corner. The second argument specifies the names. Note the order is identical to the order we have set for the levels of BMI, starting with underweight. The third argument specifies the plotting symbol. In our case, 15 is a little square. The fourth specifies the colors. Here note that you must use the same colors as you did in the bar plot command, otherwise the colors won't match. Try to play around with some of these different arguments to create a plot that looks visually appealing to you and is descriptive for your audience. For the stacked bar plot, we just need to change beside is equal to false, and we obtain the bar plots stacked on top rather than beside one another. Recall that from the crosstable command, the prop.call nested subtable gave us the conditional distribution of BMI given sex. Using this table, we can create stacked bar plots, which will give us a visual representation of the proportion of each BMI category for males and separately for females. For the Patricia example, we don't have the actual data, but we do have the contingency table. That is the counts for the number of women measured on two variables, treatment group and infection status. Let's enter these manually into R using the matrix command. We will enter these row by row, starting with 23, 6,140, 345, 5,673. We will specify by row is equal to true, and that the number of columns is equal to 2. For completeness, we will set the names of the rows and columns appropriately. This will make our tables and graphs easier to read, since they will automatically be labeled. Recall with the cross-table command, we can obtain the 4 tables that Allison discussed in the lecture. The frequencies, the joint distribution, the conditional distribution of infection status given treatment group, and the conditional distribution of treatment group given infection status. In Allison's last example, we have a 20-year follow-up study on survival rates between smoking and non-smoking women, and to obtain the data, we will need to install a new package called SM Practicals. Again, we will navigate to Packages and Data, Package Installer, and click on Get List. Now we can search for SM Practicals, select the package, select Install Dependencies, and finally install. We will load the package with Library SM Practicals. To see the dataset, simply type in smoking. Notice that the data is already aggregated by 3 categorical variables: age group, smoking status, where 1 indicates a smoker and 0 indicates non-smoker, and current status, alive or dead. Now all you need to do is pick out the numbers that you want, depending on the variables you're interested in looking at, and enter them into a matrix like we did in the Patricia example. See if you can recreate the bar plots that shed some light on the Simpson's paradox that's present in the dataset. Relationships between 2 quantitative variables R tutorial. In this R tutorial, our focus will be on creating descriptive statistics and graphs that help us explain the relationships between 2 quantitative variables. In today's lecture, you saw Jeff introduce scatterplots and the correlation, which measures the strength of the linear relationship between 2 quantitative variables. Let's take a closer look at the new data for the countries and territories around the world. We have now added 2 quantitative variables, GDP and HIV infection rate. In R, we will rename the columns of our dataset to reflect the new variables introduced. Jeff began to investigate the relationship between GDP and life expectancies using a scatterplot. We can create the scatterplot with the plot command, inputting the first variable, GDP, which will be on the x-axis, and the second variable, life_exp, on the y-axis. We will make sure to properly label each of the axes and give the plot a main title. And despite the complicated formula, R can easily calculate the correlation between GDP and life expectancy with the command cor. Note that it doesn't matter which order the variables are written in, unlike the plot command, where the order governs which variable is on which axis. Jeff also looked at the scatterplot between HIV infection rate and life expectancy, and found the correlation between the 2 variables to be negative 0.566, indicating that countries with a higher HIV infection rate tend to have a lower life expectancy. As a final example, Jeff also revisited the skeletal remains data. He presented a scatterplot of age difference versus BMI, and saw that with a correlation of positive 0.136, there seems to be almost no linear relationship between the 2 quantitative variables. Try to create these plots yourself with the plot command, and calculate the correlations with the cor command.
Hello and welcome back. So far in this class, we've been concentrating on the data itself. We've talked about how to collect it and how to summarize it with things like the quartiles and the median and so on, how to compute things like the mean and the standard deviation and the interquartile range and so on. But it's been pretty focused on the data itself. Now we're going to try to take a step backwards into the more theoretical side of statistics and look at the theoretical world as opposed to the data or the real world. In order to motivate things, let's consider again one of the examples that came up previously, namely when we considered life expectancies for different countries around the world, and we compared them by what region of the world they were in. In particular, remember when we compared East Asia and the Pacific compared to South Asia? Well, for these two regions, we could compare things like the quartiles and the median and the minimum and the maximum, and we could summarize this using the side-by-side box plots, which we did, and we saw from there that it appears that East Asia and the Pacific is a little bit higher overall compared to South Asia, but it was pretty close, and we didn't know if that was a significant difference or not. Well, how can we try to make sense of that? One thing we can do is try to put it in a broader theoretical context by pretending that the East Asian and Pacific countries are actually samples from some theoretical or imagined population of an infinite number of the kind of countries that are in East Asia and the Pacific. And similarly for South Asia, we can imagine that the data we have actually comes from a bigger sample. Now, in this case, there is no bigger population because really there's just those countries in East Asia and the Pacific, and there's just those countries in South Asia, but nonetheless, we can imagine things and try to make a theoretical model that way. We'll come back to that later, but that's going to come up a lot for us. For example, we can also consider our case of the skeletons. Well, for the skeletons, we had various data about the age differences and the body mass index and other things like that, and they were all good data, and that's the real world or the data side of things. But we can also imagine that these 400 skeletons are representatives of some big population of all the skeletons that are out there, or all the skeletons that we might consider, and we can try to draw inferences and conclusions about the entire skeleton population, the theoretical world, by using the data that we have in the real world. Similarly, for the HPV vaccine, we said, well, we have, for example, there was a study that looked at thousands of young women and measured what happened to them when they got the vaccine. But still, these young women are a representative sample from all the young women all around the world. So in all these cases, we consider the real world with the actual experimental data, and we also have the theoretical world, which is the theoretical modeling that we're trying to do. In order to make all of these ideas more concrete, let's do our own experiment right now. I have here an ordinary Canadian $2 coin. It's got heads on one side and an animal for tails on the other side. I'm going to flip it 10 times and let's see what result we get. Ready? Here we go. First flip, tails. Second flip, heads. 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 Tails. Heads. Tails. Tails. Heads. So there we go. We flipped the coin 10 times and we got a total of 6 heads out of 10. So what does this mean? Well, from the theoretical perspective, we can say in the theoretical world, the coin is symmetric. It's equally likely to come up heads or tails every time. So theoretically, we should expect to get 5 heads out of 10. And yet, from the experimental world, from the data that we got, we can see that the real world value was 6 heads out of 10. So what does this mean? This means that we don't always get exactly 5 heads out of 10, and we're going to learn to study the relationship between how many heads we might expect, like 5 out of 10, and how many heads we actually get, which in this case was 6 out of 10. Let's do a second experiment now too. I have here a cap from a beer bottle. Now it's red on one side, and it's kind of silver colored on the other side. I'm going to now try flipping this 10 times. In this case, the theoretical value, well, I don't know. I've never flipped a beer bottle cap before. I don't know if the true probability of coming up red versus silver is 50-50 or some other probabilities. All we can do is do the experiment. So here we go. Ready? First flip, red. Second flip, red. Silver. 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 Red. Red. Silver. So in this case, the data from the real world said that there were just 4 reds out of 10 flips, or 40%. Now, from the theoretical world, we don't know how many times it's supposed to come up red because we don't have experience with flipping beer bottle caps. So, what can we conclude in a case like this? We're going to find out as we move forward that in order to understand the relationship between the results in the real world and the underlying values in the theoretical world, we're going to have to learn a little bit about the subject of probability theory, and that's what the rest of this week's lectures are going to be about. In the previous lecture, we learned that in order to make true statistical inferences, we need to learn a little bit about the theoretical world, about probability theory. So to get some of the basic ideas, let's again consider that case where I was flipping a coin that was either heads or tails, and let's suppose I'm going to flip it twice. So we do an experiment which involves flipping a coin twice each time we get heads or tails. Well, what can we say about an experiment like that? First of all, we can say that there are 4 possible outcomes to this experiment. Namely, we could have gotten heads and then heads, or heads and then tails, or tails and then heads, or tails and then tails. So we have 4 possible outcomes. Now in this case, because the coin is symmetric, it's equally likely to come up heads or tails each time, we can say that each of these 4 possibilities have equal probability, have probability 1/4. So we can say the probability of heads heads is 1/4, and the probability of heads tails is 1/4, and so on. So now we know the possible outcomes and the probabilities. Well, we can also start discussing various combined events. For example, suppose I say, well, to keep it simple, what's the probability that in this experiment I end up with a total of 2 heads? Well, that's easy. The probability of 2 heads, the only way I could have gotten that is if the outcome was heads heads. So the probability is the same as the outcome of heads heads, which we know is 1/4. Or you can also call it a 25%. What about the probability of getting exactly 1 head? Well, 1 head we could have gotten if the outcome was heads and then tails, or if the outcome was tails and then heads. So that probability is 1/4 plus 1/4, which equals 1/2 or 50%. Similarly, we can compute other probabilities. For example, the probability of getting some outcome, well, that's the probability of heads heads plus the probability of heads tails plus tails heads plus tails tails, which adds up to 1 or 100%, as of course it must, because we're always going to get some outcome. Or we can think about, for example, a random quantity. Like, for example, we can let y stand for the total number of heads. Then we know that, for example, the probability that y is 2 is the probability that we got 2 heads, which means we got heads heads, which has probability 1/4. And the probability that y equals 1 is the probability that we got either heads tails or tails heads. And that probability, as we know, is 1/4 plus 1/4, which is 1/2 or 50%. So we say, okay, in this way we can compute random quantities and their probabilities based on the different outcomes. So now let's try to make this a little bit more general by giving the basic rules of probability. So we can say that in any probability experiment, we have a collection of possible outcomes, which is normally written as a capital S, and it's called the sample space, and it's the set of all possible outcomes. For example, in the experiment I just described, it's the set of heads, heads, and heads, tails, and tails, heads, and tails, tails. So that's the sample space. Then we can say that an event is any subset of S. So for example, it could be the event that we get exactly one head. That would be an event because it's a subset of all the possible outcomes. It's a subset of the sample space. Now we can say that any event A has a probability which is written P of A, and it's some number in between 0 and 1. Or you could say in between 0% and 100%. So that seems pretty clear. We could also say that if we look at the probability of the entire sample space, well, that should be the probability that some outcome occurs. And just like in the previous example, that should be 1 or 100%. There's another rule that we used before, which is sort of the complement event. That is, if we say the probability of A complement, which is to say that A does not occur, well, that's the opposite of A occurring. So the probability is 1 minus the probability of A. If we look at that in terms of the flipping two coins, we can say, for example, the probability of getting at least one head, well, we could compute it as the probability of heads, heads, or heads, tails, or tails, heads, but we could also compute it as 1 minus the probability of 0 heads, because that's the opposite of getting at least one head, and then it should be 1 minus a quarter, which is again 3/4. So we have two different ways of computing the probability of getting at least one head using this general rule that the probability of A complement is 1 minus the probability of A. Now, you might be wondering, what does it even mean to say that we have a probability, like the probability of, heads, tails is equal to a quarter? Well, we'll pretty much stick to that as being a theoretical world statement. It's saying that we have a probability model, we have a theory which says that the probability of getting heads and then tails in this experiment is equal to a quarter. There are other possible interpretations that we should at least mention. One of them is the so-called long-run interpretation of probability, which says, well, if we repeated this experiment over and over again lots and lots of times, then the fraction of times that we got heads, tails should be close to a quarter. And that is true, as we'll see. So that's another way to think about probabilities. There's also the subjective interpretation of probabilities, which says, look, in my opinion, the probability of getting heads and then tails is a quarter, and that's just my opinion, and that's the subjective probability. For the rest of this course, we'll pretty much stick to the theoretical interpretation. We'll say we have a probability model which says the probability of heads and then tails in this experiment is a quarter. So now let's consider a second example, and for that example, let's remember the experiment in the last lecture where instead of flipping a coin, we flipped a bottle cap. And we said, well, we don't know what the probability is of this bottle cap coming up red or silver each time. But suppose we were to flip the bottle cap twice. And for now, let's just suppose that we knew that each time the probability of the bottle cap coming up red was equal to a third. Of course, we don't know that, so we'll come back to this. But let's pretend that we knew the probability of red was a third, and therefore the probability of silver was equal to 2/3. Then suppose we flip this bottle cap twice. Well, then we can again talk about the possible outcomes. So here we have a sample space consisting of, well, the outcomes red, red, or red, silver, or silver, red, or silver, silver. Now in this case, the probabilities are not all equal. In this case, the probability of red, red is equal to a third times a third, which is a ninth. And the probability of red, silver is equal to a third times 2/3, which is equal to 2/9. And the probability of silver and then red is equal to 2/3 times 1/3, which in this case is again equal to 2/9. And the probability of silver and then silver is equal to 2/3 multiplied by 2/3, which is equal to 4/9. So now we have some probabilities which aren't all equal, but we can still check that the probability of the whole sample space should be the sum of these 4 different probabilities, and sure enough, it still adds up to 1 as it has to. We can also compute other facts. For example, suppose we were to let x be the total number of reds that we get in the 2 flips of the bottle cap. Well, then we can say, for example, the probability that x equals 2 is equal to the probability of getting red, which is 1/3 times 1/3, or 1/9. And the probability that x equals 0, let's say, is the probability that we got silver and then silver, which is 2/3 times 2/3, or 4/9. The probability that x equals 1 is the probability that we got exactly 1 red in the 2 flips. Well, that's the probability of either red and then silver, or silver and then red. So that probability is equal to 2/9 plus 2/9, which is equal to 4/9. So in this way, we can compute all sorts of things about different probabilities of outcomes and events, and different quantities like x or the y we had before, which are sometimes called random variables because they're random quantities. We can compute the probabilities for them too. So in this way, with these very simple examples, we have just the basics of how to compute probabilities, some basic rules about sample space and outcome and probabilities and events and random variables. And now we're ready to start understanding some more concepts involving probabilities. So in the previous lecture, we learned the basics of probability theory. Now we understand about probabilities and so on. Well, today we're going to focus more specifically on probability distributions of random variables. So for example, remember last time we had some experiments where we flipped an ordinary coin and we counted the number of heads that we had. Well, let's think about that a little more. So if we flip the coin twice in an experiment, and if we let y be the number of heads, then we already worked out the probabilities. We said the probability that y equals 0 is 1/4. The probability that y equals 1 is 1/2, and the probability that y equals 2 is equal to 1/4. These numbers add up to 1, and they give us all the probabilities for the random variable y. This is called a probability distribution, and in this case, it's called the binomial 2/2 as the distribution. So this is a particular name that we give to the distribution. It means we did 2 experiments. In this case, we flipped the coin twice, and the probability of success or a head each time was equal to 1/2. For something even simpler, if we flip just one coin and let x be the number of heads, or we could say it's just 1 if it's a head or it's equal to 0 if it's a tail, then we can say, well, the probability that x equals 1, that's the probability we got a head, so that equals 1/2. And the probability x equals 0 is also 1/2. So we could call this the binomial 1/2 if we wanted. We also call this the Bernoulli 1/2 as a distribution. And this means, it's a special name to mean we just did one experiment and the probability of success, or 1, was 1/2. Otherwise, we get 0. If we imagine flipping a coin 3 times, then the calculations get a little bit trickier, but it's still not hard to work out the probability distribution. Again, if we let x be the total number of heads that we get, then x could be 0 or 1 or 2 or 3 with these probabilities. And this would be called the binomial 3/2 as a distribution. So we see in this way that as we flip more coins, we get all different sorts of distributions. Or if we imagine flipping those bottle caps like we did last time, well, suppose we knew that the probability of getting red on each bottle cap was 1/3. In that case, if we flip one bottle cap and count the number of reds, then that would be the Bernoulli 1/3. Or if we flip the bottle cap twice and count the number of reds, then that would be the binomial 2/1/3. And we can work out the probabilities for that as we did. The probability that the number of reds equals 0 or 1 or 2. For a whole different kind of example, we can imagine rolling a 6-sided die like I have here. Well, if I randomly roll the die and let one particular side show, in this case I got a 2, well, I was equally likely going to get any of the numbers between 1 and 6. So we can set this up as saying that if you roll one die, and if you let W just equal the amount that's showing on the die, then W is equally likely to be 1 or 2 or 3 or 4 or 5 or 6. Each probability is equal to 1 out of 6. We can call this the discrete uniform distribution, which is to say the probabilities for W are uniform, equally likely on the 6 points, in this case the numbers from 1 up to 6. Now, once we're talking about these random variables, we can talk about other quantities related to them. For example, we can talk about their mean, or their expected value, which is what number they equal on average. There's a simple formula for computing the expected value of a random variable x. You just add up all the possible values multiplied by all the probabilities that x equals that value. So for example, if we're rolling the die and looking at the number shown, then the mean would be equal to, well, 1 multiplied by a sixth, plus 2 multiplied by a sixth, plus 3 multiplied by a sixth, and so on up to plus 6 multiplied by a sixth. This works out to 3.5, not 3 as some people might think. So we say that on average, if you roll a die, the average or mean or expected value that you'll get is equal to 3.5. If we go back to that coins example, we can say if we flip 2 coins, well, we might get 0 or 1 or 2 heads, but we know the probability. So the expected number or mean number of heads that you get when you flip 2 coins would be computed as 0 times a quarter plus 1 times a half plus 2 times a quarter, which works out to 1, which is what you might have expected. Okay, so now we understand the mean or expected value of a random variable. There's another quantity that we need to understand too, and that's called the variance. Now you may recall in last week's lectures we talked about the variance from some data from a sample, but we also have the variance in the theoretical world. In this case, the variance again tries to measure the spread of the values, or how far away they tend to be from their mean value. The formula is a little bit more complicated. It's given as follows. We take a sum of all the squared differences between the value and its mean and multiply that by the probability. So it's the expected value of how far the random variable is from its mean squared. So for example, if we just flip one coin, and if x is 1 if it's a head or 0 if it's a tail, well, then we can work out the variance because we just compute it as being 1 minus a half squared times a half plus 0 minus a half squared times a half, which works out to a quarter. We also have the standard deviation, or SD, just like in the experimental or real world, and the standard deviation is just the square root of the variance. So in this case, the standard deviation is a half. We could also consider, say, when we rolled that 6-sided die. In that case, we know that the mean was equal to 3.5, and now we can compute the variance by taking, well, 1 minus 3.5 squared times a sixth, plus 2 minus 3.5 squared times a sixth, and so on up to plus 6 minus 3.5 squared multiplied by a sixth. And when you work that all out, you get it to be a certain number which works out to about 2.92. And then the standard deviation is the square root of that. So in this way, we can compute not only the mean, but also the variance and the standard deviation of a random variable. Now, these quantities satisfy a few simple properties. The mean, or expected value, satisfies the nice property of being linear. It means if we take any linear combination of two different random variables, say x and y, then the expected value is just the corresponding linear combination of the individual expected values. This will turn out to be helpful to us later on. The variance is not quite as good. If we take the variance of, say, a constant multiplied by a random variable x, then the variance multiplies by a squared. And if we then take the standard deviation, well, it multiplies by the absolute value of A. So if A is positive, it just multiplies by A, but if A is negative, it multiplies by the absolute value, or the positive part of A. If we add a constant, that doesn't affect the variance. So the variance of AX plus B is just A squared times the variance of X with no mention of B. Now the variance of a sum of random variables, variance of X plus Y, sometimes it equals the sum, the variance of X plus the variance of Y, but only if X and Y are what's called independent, that they don't have any special influence over each other. We'll come back to that point later. So far, all of these random variables that we've been considering are what we call discrete random variables. It means that the possible values they take are values that can be written in a list. So maybe they can be 0, 1, or 2, or maybe they can be 1, 2, 3, 4, 5, or 6. But they're just values which we could write in a list. What if we had a random quantity that could take any value in a whole interval? This is called a continuous random variable. The simplest example of a continuous random variable or a continuous probability distribution is uniform on the interval from 0 to 1. Now this means we have a random quantity which is equally likely to be anywhere in the interval 0, 1. Well, it's a little harder to pin down what this means. We can think of it in terms of the probability that this random quantity is in any interval within 0, 1. For example, the probability that this random quantity is, say, between 0 and a third, well, that should be a third because that's the length of that interval. Or the probability it's between, say, a half and 3/4 should be 3/4 minus a half, or a quarter, because that's the length of that interval. And in general, the probability that it's between any two numbers A and B should be equal to B minus A whenever A and B are within the interval. Now this has an interesting consequence. It means that the probability that X equals any particular number A is equal to the probability X is between A and A, which is A minus A, which is 0. So it means somehow with probability 1, X will be somewhere between 0 and 1, and yet the probability is 0 that X equals any particular value. This is a little bit confusing, and we've learned that it's best to think about a continuous distribution like this, not by keeping track of all the individual probabilities, but by thinking of it as the area underneath a graph of a function. This function is called the density function. And for the uniform 0, 1 distribution that we've been considering, the density function is a function which equals 1 in between 0 and 1 and equals 0 everywhere else. Then we can talk about probabilities as being the area underneath the graph of this function. So for example, the probability that this random variable is between a half and 3/4, well, we can think of it as the shaded area here, the area underneath the graph, which is in between a half and 3/4. And of course that area is equal to 1/4, as we already figured out. Now, once we understand about density functions, then we can use them for other distributions too. For example, instead of just having a random variable that's uniform between 0 and 1, we could have a random variable that's uniform between, say, 10 and 50. It would have a density which is equal to 1 over 40 for all numbers in between 10 and 50. Otherwise, it's equal to 0. And the total area under the graph is still equal to 1. But now we could say, oh, the probability that the random variable is, say, between 25 and 32, well, would be given by the area underneath the graph, which is between 25 and 32, which in this case is equal to 7 out of 40. Other density functions will give us other examples of continuous probability distributions. For example, the exponential 1 distribution has a density function which is equal to e to the minus x whenever x is a positive number. Otherwise, it's equal to 0, as shown here. And again, the probability that, say, that random variable is between 2 and 3 would be equal to the area of the shaded region, which is underneath that graph. The single most important continuous distribution that we're going to study is something called the normal distribution, or the Gaussian distribution, or sometimes called the bell curve. and it's got a density which is given by this strange formula here. It's given by 1 over the square root of 2 pi times e to the minus x squared over 2. Now that's a function whose graph looks like this. And again, the total area underneath the graph is equal to 1. And again, the probability that, say, this random variable is between, say, 1/2 and 1.5 would be given by the area underneath this shaded region here. And once we have one bell curve that we like, well, we can make other ones by shifting them over. And what's called the normal mu sigma squared probability distribution is just given by starting with that old standard normal distribution and then shifting it over by some amount mu and stretching it out by some amount sigma. So for example, the normal 3, 2 squared probability distribution would be a bell curve which is centered at 3 and which is stretched out twice as wide as compared to the original standard normal curve. So in this way, we have lots of different probability distributions. One nice fact is if we have a random quantity, say x, which has the probability distribution given by a normal mu sigma squared for some mu and sigma, then we can standardize it by subtracting off the mean and dividing by sigma, and that gives us a new quantity z, and we can see that z will then have the standard normal distribution, also called normal 0, 1. So there's relations between all these different kinds of continuous distributions. The last thing we need to realize is that just like for discrete probability distributions, continuous distributions also have a mean and a variance. Now, in this case, computing it is a little trickier. We have to compute an integral instead of a sum, which may be scary for some people. So in this course, we're not going to worry too much about it. But for example, if we had a random variable which was uniformly distributed on 0, 1, then the mean would be the integral of x dx from 0 to 1, which is 1/2, which is what you might expect. And the variance would be, well, x minus that mean of 1/2 all squared, and then integrate that from 0 to 1, and that works out to 1/12. For the exponential 1 distribution, the mean is a formula in this case, which is the integral of x times e to the minus x, taken from 0 to infinity, because that's all the possible values, and that works out to be just 1. And in this case, the variance, which is again an integral, also works out to 1. For the normal distribution, well, it's hidden right in the notation that if it's normal 0, 1, then the mean is 0, and the variance and standard deviation are both 1. If it's normal mu sigma squared, then the mean or expected value is mu, and the variance is sigma squared, and the standard deviation is sigma. So we don't need to worry too much in this class about how to compute those integrals. We just need to understand that there's all sorts of different probability distributions. There's discrete ones and there's continuous ones. And they all have means and variances and other properties that we'll learn more about as we go forward. In particular, we'll learn that that normal distribution will turn out to be the most important distribution for us. We'll see that in the next lecture. So now we know about the basics of probability theory and the distributions of random variables. In this lecture, we're going to talk about long-run averages. What happens if you repeat an experiment lots of times and look at the average value that you get? Like so many things in probability theory, a good way to understand it is again to think about flipping an ordinary coin that has probability 50-50 of coming up heads or tails. So if I flip it just once, the probability of heads is 50%. Well, we already know if I flip it twice, then a quarter of the time I won't get any heads, and half the time I'll get one head, and a quarter of the time I'll get two heads. But what if I flip it lots and lots of times and look at the fraction of heads that I get? You might think as you flip it more and more, the fraction of heads should get closer and closer to 1/2. And indeed, in this lecture, we'll see that that's so, and we'll understand better how that works. So to start off, let's again imagine flipping a coin twice, and I've graphed here the probabilities for the fraction of heads that you'll get. So a quarter of the time you won't get any heads, half the time you'll get half of them heads, and a quarter of the time you'll get all heads. Simple enough. If we flip 3 coins, well, we worked out those probabilities before too, and we can see here that there's probability 1/8 of getting no heads, or 3/8 of getting a third heads, 1 out of 3, or 3/8 of getting 2/3 heads, or 2 heads out of 3, and 1/8 probability of getting all heads, 3 out of 3. What if I flip a coin 10 times? So here's a graph when I've flipped 10 coins and looked at the fraction of heads that I get. And we can see from this graph that the most likely fractions are fractions which are close to a half, corresponding to 5 heads out of 10. Now, a little bit less or a little bit more than half heads, corresponding to 4 heads or maybe 6 heads out of 10, are also quite likely. But getting no heads or 1 head, or getting 9 heads or 10 heads out of 10 are very unlikely. If we flip even more coins, we can see this more clearly. Here's a graph of the probabilities when we flip 30 coins. And we see now that sure enough, the probabilities closest to the middle, closest to half of the flips being heads, are indeed the highest ones. We can also start to see something else. We can see a little bit about the shape of the graph of these probabilities. We can see that it's highest in the middle and it falls off to the sides in a nice round shape that might look a bit familiar. If we flip 100 coins, we can look at the graph again. The first thing we see is that all the individual probabilities are getting quite small because there's all different possible results you could get for the fraction of heads when you flip 100 coins. But we can also see the shape, and if we stretch it out, here's another version of the same graph, just stretched out so we can see the probabilities better. And we see, sure enough, we've got this sort of curve shape, which should remind you of the density for the normal distribution that we saw in the last lecture. So what can we say so far? Well, we say that as we flip more and more coins, sure enough, the fraction of heads seems to get closer and closer to being a half, which is what you might expect. But also, if we look at the graph of the probabilities, that is the distribution of the fraction of heads that we get, it looks more and more like it has this curve shape, kind of like the normal distribution. Now, so far you might think, okay, fine, that's true when you flip a coin lots and lots of times, but what about other experiments? Well, let's do another one. So if we remember rolling a 6-sided die, and remember when we roll it and show some side at random, well, we have equal chance of getting any of the numbers 1, 2, 3, 4, 5, or 6, but what if we do it over and over again? So if we just roll one die, then we have equal probabilities of getting any of the numbers 1, 2, 3, 4, 5, or 6. So the graph of the probabilities looks like this, and it's not really very interesting. Well, suppose we roll 3 dice and look at the average of the 3 numbers that appear on the 3 dice. Well, then there's a bunch of possibilities we can get, because each of those dice could have been anything from 1 to 6. But when we look at the averages, these are the probabilities. So right away we can see that the most likely averages when you roll 3 dice are all, well, between about 3 and 4. But it's still possible you might get an average closer to 2 or to 5. It's not very likely you'll get an average near 1 or 6. What if we roll 10 dice? Well, then the probabilities look like this. And now, sure enough, we can start to see some of the old familiar patterns. First of all, we see that the highest probabilities are indeed close to 3.5, or between about 3 and 4, which you may recall 3.5 was the mean or expected value that we'd get each time we rolled a die. So if you roll 10, the average of the rolls you'll get will probably be somewhere between about 3 and 4, maybe a little more or a little less. And also we can start to see that same characteristic shape, the bell shape of that normal curve. If you roll 100 dice, then it's even more extreme. It's almost impossible to get anything that's not between 3 and 4 on average. It's got a high peak right near 3.5, and indeed it's got that characteristic shape of the normal distribution. So it wasn't just for flipping coins, it's also for rolling dice. Now, what are the general conclusions that we can make here? Well, the first one is what's called the law of large numbers. It says if you repeat an experiment over and over again and take the average of the results that you get, then that will get closer and closer to the expected value. And as you take an infinite number of repetitions, then you will indeed get the expected value. So if you flip a coin infinitely often, you'll get half heads. And if you roll a die infinitely often, then on average, you will get 3.5. But remember, we also had that characteristic shape. And that's what's called the central limit theorem, and it's extremely important in statistics. And it says that if you repeat an experiment over and over and average up the results, then the distribution of the probabilities for that average will get closer and closer to being normally distributed, or to having the bell-shaped curve. So it says that that normal distribution comes up approximately all over the place whenever we're taking anything that could be viewed as any kind of an average. If you need more convincing, then let's consider another example, this time of an experiment that's highly skewed. Suppose we have an experiment such that each time the outcome is usually 0, but is occasionally 50. And let's say that it's 0 96% of the time, and it's 50 the other 4% of the time. And then we repeat the experiment over and over and look at the probabilities for the average, for x bar. Well, after just one experiment, it's not that interesting. It's almost always 0, and occasionally it's 50. But after 3 experiments, well, it's still usually 0, but occasionally the average takes on some larger values. After 10 experiments, well, we're starting to see different values poke up for this average, but we don't really understand it. After 30 experiments, well, we're starting to see a little more of a pattern. We're starting to see some spread in the probabilities. After 100 repetitions of the experiment, we can start to see that most of the probabilities are pretty close to 0, but they're starting to spread out in a sort of a shape. And if we see that graph again just spread out a little more so we can look at it better, we see sure enough, after 100 experiments of this very, very skewed example, we still see this characteristic curve starting to appear of the bell shape, or the normal distribution. In this case, it's centered around the value 2 because the mean value in that funny skewed experiment was indeed equal to 4% multiplied by 50, which is 2. A whole different way to think about the central limit theorem is through a graphical display called a quincunx, which is shown here. It shows balls that are falling from above and hitting against these knobs or nails and bouncing around. And each time a ball hits a nail, it might bounce a bit to the left or it might bounce a bit to the right. But we can see that each time that adds a certain random amount to the position of the ball, whether it moves a bit left or a bit right. And after it gets through all the nails, well, its final position is kind of represented as a sum or some sort of average of all these different influences on it. And so as we run this for a long time, and as we keep track of where the different balls have landed, at first it seems like they could land all over the place, but after a while, sure enough, the distribution of where they land starts to approximately look like that normal distribution, or that bell shape again. Now, these results can be understood a little bit better if we remember what we learned about the mean and variance of probability distributions in previous lectures. So, if we imagine that we're repeating a bunch of experiments, and the results of the experiments can be written as x1, x2, x3, and so on, and suppose we know that the mean or expected value of each of the experiments is some number, let's call it m. And suppose we know that the variance of each of those experiments is some other number, let's call it v. Then, if we look at the average, so if we let x bar be the average of x1, x2 up to xn, then, well, the expected value of x bar of the average, as you'd expect, is just the same as m. It's the same on average. If it's like the average of the average is the same of the averages, if you want to think of it that way. But what about the variance? That's a little more interesting. So the variance of x bar, well, if you remember your properties of variance, since we're repeating these experiments independently, then the variance of that sum is just the sum of the variances, so it's n times v. But then we had the variance of that sum divided by n. But remember, with variance, if you multiply by a constant, or if you divide by a constant, then the variance is affected by the square. So actually we take that n times v and divide it by n squared. And it means we get a variance which is equal to v over n. And why is that important? Well, it's important because it's going to 0 as n goes to infinity. It means if you repeat the experiment more and more, then the variance or the uncertainty will go to 0. So also the standard deviation, which is the square root of the variance, will go to 0. So it means as you repeat an experiment over and over and take averages, then the amount of uncertainty gets less and less, and we get more and more certain of where we are. So this is a very important property of repeating experiments over and over again. As a final note, I want to mention that the central limit theorem provides an explanation for that empirical rule that Alison taught us about earlier. Remember that she said, well, with the empirical rule, it seems that with a lot of data, it has this neat property that about 68% of it is within one standard deviation of the mean, and about 95% of it is within two standard deviations of the mean, and about 99.7% of it is within three standard deviations of the mean. Before, that might have sounded just like magic, and when we saw that our data approximately followed that, it seemed amazing. But now that we know the central limit theorem, we can say, aha, these are the probabilities which approximately correspond to a normal distribution. So if we go back to that graph of a normal distribution, then we can say, well, what fraction of the area underneath the curve is indeed within one standard deviation? And sure enough, that area is about equal to 68%. If we look at the area which is within two standard deviations of the mean, sure enough, it's about 95%. And if we look at the area under the curve that's within three standard deviations of the mean, sure enough, it's about 99.7% of all the area under the graph. So when someone says, hey, this data follows the empirical rule, they're really telling you, hey, this data follows the normal distribution. And we're not so surprised anymore because we see, because of the central limit theorem, lots and lots of data follows the normal distribution, at least approximately. Now, not all data, and we've already seen examples of data which are skewed or have some other funny distribution, and in that case, they might not follow the central limit theorem. We'll see more about that as we go on. But in lots of cases, anything that arises from some sort of an average or some sort of lots of different little influences will tend to approximately follow the normal distribution. And we'll see as we go on that that allows us to make all sorts of inferences in statistics.
Now that we understand some of the important concepts from probability theory, our goal is to make the connection between them and statistics. That is, we want to understand how we can use these probability ideas to better understand our data and the kinds of conclusions that we can make based on them. The goal of this lecture is to introduce an important concept that will help us make that connection. The concept we'll be talking about is the sampling distribution. Let's revisit the way we're looking at the inferential process. We have data in the real world and models in the theoretical world. Or the theoretical world could be a population and our data could be measured on a sample from the population. Either way, we have parameters in the theoretical world, which are features of the models or the population. And typically, we don't know the values of the parameters. We use the science of statistics to estimate them by a statistic calculated from our real-world data. We're going to think about this in a somewhat backwards way in this video. But going forward, it's important to understand what this backward thinking means for the real world. For now, we're going to assume that we know the theoretical world. That is, we know the parameters of our models or the population values. And then for a few situations, we're going to look at what the statistics we would use in the real world to estimate the parameters might look like. Of course, in real life, we only get one sample or set of data. But for now, we're exploring what all of the possible samples we could have gotten could be, so that we will be better able to understand that one sample that we'll actually get. Let's start with an example that we've already seen, flipping a coin 10 times, which is equally likely to come up heads or tails. This has a well-understood probability model in our theoretical world. The number of heads that can come up in 10 flips Could be anything from 0 or 1 or 2 up to 10. And some of these values are more likely than others. Let's flip 10 coins a few times and see what we might get. We'll use this applet, which simulates coin flips using an American penny. We'll set it to carry out 10 flips. For our first trial, we get 3 heads, which has been noted here in the plot. Let's try it again. We get another 3, so now there are 2 3s on the plot. This time we got 5 heads in our 10 flips, and now we got 4 heads. I'd like to do this a total of 1,000 times. We've already done 4, so I'll add in 996 more. The plot shows the frequency of all the observed counts of heads that we got. Not surprisingly, 5 heads happened most often, 4 and 6 also happened fairly often, and 0 and 10 heads didn't happen very often in our 1,000 trials of 10 flips of a coin. The probability distribution here is binomial 10 1/2, which looks like this using theoretical probability calculations. Suppose that the theoretical world parameter that we're interested in is the probability that a flipped coin comes up heads. We'll call this P. For 10 flips of the coin, the probability distribution then would be binomial 10P. Because we understand this model, we understand what might happen in the real world if we flipped a coin 10 times. Of course, in the real world, we get just one set of 10 flips. Our estimate of the parameter is the proportion of heads we got in our 10 flips. We'll call this P hat and calculate it as the number of heads observed divided by 10, the total number of flips. We use hats in statistics often to indicate statistics calculated from data to estimate theoretical world parameters. If we'd done another and another and another 10 flips, our real-world data would give various values of P hat each time, with probabilities following our binomial distribution. The fact that we don't get the same value each time means there is variability in our estimate. This variability is called sampling variability. Sampling variability is the variability we expect to see in a statistic that we're using to estimate a theoretical world parameter. Variability occurs because of the randomness in our data. The probability distribution of the estimator of the theoretical world parameter is called a sampling distribution. Sampling distributions are probability distributions with means or expected values and variances or standard deviations that we can calculate using the definitions and rules that Jeff showed earlier to calculate these quantities from probability distributions. We'll use these definitions and rules to calculate the expected value and variance for the sampling distribution for the estimate of the probability of heads from 10 flips of a coin, P hat. Earlier, Jeff showed that one coin flip can be modeled as a Bernoulli 1/2 random variable, which is either 1 or 0 with probability 1/2. And he showed that the expected value or long-term average of such a random variable is 1/2 also. If we generalize this to any situation where something happens or doesn't happen, heads or tails on a coin flip, red or silver in a flip of a beer cap, a randomly chosen person supports a government initiative or doesn't, with probability P that it happens, i.e. comes up 1 for our Bernoulli random variable, and then probability 1 minus P that it doesn't happen, or comes up 0 for our Bernoulli random variable, then the expected value or long-term average, using the formula Jeff gave us, is the sum over x of the possible values of x times their probability. For the Bernoulli p random variable, we get 0 times 1 minus p, or 1 times p, which works out to be p. If we think of 10 repeated coin flips, each as Bernoulli p random variables, with outcomes for these 10 Bernoulli random variables x1 through x10, and we estimate p, the probability of what we're interested in happening, as the number of times it happens divided by the number of experiments, 10 in this case, then this is x1 plus x2 plus x3 and so on plus x10 divided by 10 because, say it happens 4 times in our 10 experiments, then 4 of x1 through x10 will be 1 and the other 6 will be 0. And the sum of these 4 ones and 6 zeros will be 4, the number of times we get heads or whatever else we're interested in. So p hat, which is the sum of x1 through x10 divided by n or 10, the number of experiments, is an average of 10 Bernoulli p random variables. And Jeff showed that for any n random variables with the same expected value, the expected value of the average is that same expected value. So the expected value of p hat is p. So in other words, we're using p hat, the calculated proportion of times that something happens in the real world, as our estimate of p, the theoretical probability that it happens, and the expected value or long-term average of our estimate is exactly what we're trying to estimate. Hopefully this sounds to you like a good property of an estimator. Indeed, such an estimator, which has expected value what it's trying to estimate, is called unbiased. So now we know that if we estimate the probability that something happens by p hat, the proportion of times it happens in our data, that the probability distribution of p hat, or its sampling distribution, has expected value p. So p hat seems to estimate what we want it to estimate. But in any one observed set of data, are we likely to be close to p? This depends on the variance of the sampling distribution. What we need to know now is the variance of p hat. Again, we'll look at one Bernoulli random variable, which is 1 or 0, or heads or tails, with probability p that it's a 1. Jeff showed us this formula for calculating the variance from a probability distribution, and for this Bernoulli random variable, we get p times 1 minus p. And in a previous video, Jeff showed that when we're taking the mean of a series of variables that have the same variance, the variance of the mean is the variance of the individual variables divided by n. So since p hat is a mean of 10 Bernoulli random variables, the variance of p hat is then p times 1 minus p over n, and the standard deviation is the square root of that. Note again how the variance and the standard deviation decrease with n. So the larger our sample size, that is, the more times we flip the coin or run the experiment, or the larger our sample size, the variability in the proportion of times the coin comes up heads or we observe what we're interested in decreases. That should be intuitive. We get more precise estimates with less variability with larger sample sizes. Here's an illustration of how the sampling distribution for p hat changes with sample size when the theoretical parameter p is 0.5. When the sample size is 10, as we've been working with, we have this binomial distribution for our sampling distribution of p hat, centered around our theoretical p of 0.5, since p hat is an unbiased estimator. Increasing the sample size to 40, or 4 times as large, cuts the standard deviation in half, since the standard deviation changes with root n. That gives us this distribution, still centered at 0.5, but more tightly clustered around it because of the smaller standard deviation. And increasing the sample size to 100 gives us this sampling distribution, even more tightly clustered around 0.5. To summarize some of this, when we're estimating a parameter that is a proportion or a probability of an event happening, and we know the value of the parameter is p, and we estimate it with p hat, the proportion of times that we observe the event in our data, then the probability distribution for the possible values p hat could be, in other words, its sampling distribution, has expected value p and standard deviation, the square root of p times 1 minus p divided by n. In working out some of these results, we looked at p hat as an average of Bernoulli random variables. Of course, we know a bit more about what happens in averages in the long run from a previous video. In particular, the larger the sample size, the closer an average gets to normally distributed. So for large sample sizes, a good estimate for the sampling distribution of p hat is the normal distribution with mean p and variance p times 1 minus p over n. We've looked a lot at the case where p equals 0.5, which gives us a nice symmetric sampling distribution. When p is further from 0.5, say closer to 0 or to 1, we need a sample size that's much larger before the normal distribution is a good approximation based on the central limit theorem. Let's look now at another case. Suppose our theoretical world model is a normal distribution. The normal distribution is a good model for quantitative data in many cases, so it will be important to us. A normal distribution has two parameters, its expected value, mu, and its variance, sigma squared, or you could talk about its standard deviation, sigma. For now, let's say the parameter that we're interested in is mu, the expected value. If our data are observations from this normal distribution, a natural choice to estimate the expected value is the average of our data values. We'll think of our data as observations of n values from this normal distribution with mean or expected value mu and variance sigma squared. We'll call these observations x1, x2 up to xn. Then our estimator of mu, our average of our data values, is x bar, the sum of the observations divided by n. Now, since x1 through xn all have mean mu, we saw previously that the expected value of the average is the same as the expected value of the individual variables if they all have the same expected value. What that means in this case is the expected value of x bar, the average, is mu. In other words, x bar is an unbiased estimator for mu. If x1 through xn all have the same variance, sigma squared, and they're independent of each other, we also previously saw that the variance of x bar is sigma squared over n, and then the standard deviation of x bar is sigma over the square root of n. What we've just done very quickly is derive two properties of the sampling distribution of x bar, the average of our data, which we're using to estimate mu, the expected value of our distribution in the theoretical world. Given that our theoretical world model is the normal mu sigma squared distribution, then the probability or sampling distribution of x bar has expected value mu and standard deviation sigma over root n. This is similar to the results we saw for p hat, our estimate of a proportion or probability. Like p hat, x bar is unbiased, and the larger our sample size n, the more precise estimates we get because of the smaller variance or standard deviation. We can use another applet to investigate the sampling distribution of x bar, the mean or average of our sample. Let's start with a theoretical probability model that has a normal distribution. This one has mean 16 and standard deviation 5. Now let's simulate some data. This time our data will be a sample of size 5 from our theoretical world model, the normal model. When we do this, the 5 data values in our sample are plotted here, and the mean or average of our sample data, the average of the 5 values we just randomly drew, is plotted here. We can see that the average is 16.4, which is quite close to our theoretical probability model value of 16. Let's take another sample of size 5. This one has a mean of 15.38. We can put our two means together in this plot, the distribution of means plot. The average of the means, each of which is a sample average from our samples of size 5, is 15.89. And if we do this 3 more times, we now have 5 samples of data, and we get 5 resulting possible values for what x bar, the mean of the sample values, can be. Now let's clear those so that we can take 1,000 samples. We don't see all our sample data anymore. It's too much for this plot. But we do now have a clear distribution of all of the 1,000 sample means. Note that it appears to have a normal distribution, and its mean is 16.05. very close to the 16 in our theoretical model, which of course is what we expect since we know that we have an unbiased estimator. Also, it is much less spread than we have in our theoretical model, also expected. The standard deviation of the distribution of means of samples of size 5 should be the theoretical model standard deviation divided by the square root of the sample size 5. And 5 divided by the square root of 5 is 2.236, and this is very close to the 2.30 we got for the standard deviation of our 1,000 samples. For a second example, let's increase the sample size to 25. We'll draw 1,000 samples again. For the 1,000 averages calculated from the samples of size 25 each, the mean, the overall average of these 1,000 means, these individual averages, is 16.01, extremely close to our theoretical model value of 16. And the standard deviation of the distribution of means with sample size 25 is 1.03, very close to 1/5 of the theoretical model standard deviation of 5. And again, this is exactly what we expect for a sample of size 25. So to recap, what we've seen when we start with a normal theoretical probability model and take samples of size n and calculate the mean for each sample, the mean of these means is the same as it was for the probability model. And the standard deviation of the distribution of means decreases from the value for the theoretical model by a factor which is the square root of the sample size. What happens if we start with a theoretical world model that isn't normal? Well, because we're working with means and we have the central limit theorem helping us here, we expect to see essentially the same properties. Let's use the skew distribution as our theoretical world model. It has a mean of 8.08 and a standard deviation of 6.22. We'll see what happens if we look at the sampling distribution of the mean, both for samples of size 5 and for samples of size 25, and we'll compare them on these two lower plots. The two sampling distributions for these samples of size 5 and 25 both have as their mean a value very close to our theoretical model value. For the theoretical model, remember it was 8.05, and for the distribution of samples of size 5, the mean is 8.05, and for samples of size 25, it's 8.04. So again, this illustrates that using the average as an estimator of the mean of a theoretical probability model is unbiased. That is, we expect to get what we're trying to estimate. Now let's talk about how the sampling distribution differs with the two sample sizes. The distribution for the larger samples, the samples of size 25, is less spread out since it has smaller standard deviation, which is what we expect. Remember, the standard deviation of the distribution of the means is the theoretical standard deviation divided by root n. So the larger n is, the less the spread. Also, the distribution for the smaller sample size is a little bit skewed. Less so than our theoretical model, but still a little bit. So the central limit theorem has only partially kicked in when the sample size is 5. But it looks like it's working quite well when n, the sample size, is 25, as the distribution for means of samples of size 25 looks quite symmetric and bell-shaped, like a normal distribution. P-hat, an estimator of a proportion or probability, and X-bar, an average, the estimator of the mean, are going to be the most important estimators going forward, and they're very well understood, as we've seen. So it's going to be possible for us to carry out inference for P and mu, what we're estimating with P-hat and X-bar, because the statistics we're going to use to estimate them, although they vary from sample to sample or from any measurement to any other measurement, they follow the structure of an understood probability distribution called the sampling distribution, which we've just studied. Knowing the sampling distribution is going to help us to quantify how much error there is in our estimates, and whether any observed differences can be explained plausibly by random chance, or if we'll need another explanation. And these are the important ideas of inference. We can look at the sampling distributions of estimators of other parameters of the theoretical world probability model, but the only other estimator we'll look at now is the estimator of the variance. Recall that when Jeff introduced the variance calculated from data, it was almost the average of the squared deviations from the mean, except it was divided by n-1 rather than n. This applet gives us the opportunity to explore the sampling distributions for the variance if we divide by n-1 or if we divide by n. Choosing variance from the menu gives the biased version, that is, divided by n. The version of variance in the applet with the U is the unbiased version, with n-1 in the denominator. We'll start again with a theoretical model that's a normal distribution with standard deviation 5, or more importantly, the variance is 25 then, which is what we're trying to estimate. Let's take samples of size 25, and we'll randomly simulate 1,000 data sets and compare the distributions of our two versions of the variance. Both distributions are a little right-skewed, which, although we haven't studied it, it's a known property of the distribution of variances. So if we wanted to carry out inference on a variance, we'd need a right-skewed model and not a normal model. But let's focus on the center to see how well these variances are estimating the variance of the theoretical model. Again, the theoretical model had a variance of 25, and here we see the biased version has a mean of 23.91, not too far off from 25. But the unbiased version of the variance has a mean that is much closer. The mean of its distribution is 24.91. So that's a very short demonstration of why it's necessary to divide by n-1 when calculating the variance from data. What's coming next is that we're going to take some of these ideas about probability that we've been discussing and apply them to the analysis of data. And in particular, we'll focus a lot on inference for proportions and means. So why these two quantities in particular? Proportions and means are very important in a number of applications. Proportions in particular are used in polls, and they're also important in studies such as our HPV study, where we're interested in the proportion of people who developed an HPV infection, depending on whether or not they were vaccinated. Means also have many applications. If we're comparing the error in age estimation between males and females, typically what we're looking at is whether or not the mean error differs between males and females. Or similarly, if we're comparing life expectancy among regions of the world, we might ask, is the mean life expectancy the same in these different regions? So the sampling distribution for proportion and means is going to be extremely important to us. And thankfully, we have some theoretical properties we've seen and the central limit theorem to help us.
Introduction to Probabilities, our tutorial. This week, Jeff and Allison introduced a new part of statistics, probabilities. Jeff discussed some discrete and continuous random variables, like the binomial and uniform, and you saw their mass and density functions in a graphical form. Allison then talked about sampling distributions and what happens in the long run. R has a few functions we can take advantage of when trying to calculate probabilities from a known distribution, or plot the mass or density functions. Let's start by looking at a discrete binomial distribution. Recall in the lecture on probability distributions, you worked through an example where a fair coin was flipped 3 times, and you let x equal to the total number of heads observed. We know the distribution of x is binomial, with 3 trials, and the probability of success, or heads in our case, equal to 1/2. Of course, we know that x can only take on values from 0 to 3, and they must be integer values, since it is a discrete distribution. To calculate the probability at any particular value of x, we can use the function dBinom, which stands for distribution binomial. For example, the probability that we observe no heads, so x is equal to 0, is 0.125, or 1/8. To obtain the whole distribution of this binomial random variable, we need every possible value of x and their probabilities. So let x equal to a sequence of numbers from 0 to 3, increasing by 1 with the sequence command. And let prob x equal to the probability of x from this binomial 3.5 distribution. We'll combine the results for better viewing, and now we can see the whole distribution with all values of x and their respective probabilities. We can plot x and the probabilities with the plot command to get a better idea of what this distribution looks like. Notice that we specified type is equal to h to obtain bars similar to a bar plot. And we can calculate the mean as well by just taking the sum of all x values times their probabilities. And as you might have guessed from the graph of the distribution, the mean is equal to 1.5. Similarly, we can do this for a binomial random variable with sample size 50 and probability of success 0.2, just to get an idea of what the binomial distributions can look like. For an example on continuous distributions, we can look at the uniform and normal. For the uniform 0-1 distribution, let's start with a sequence of numbers from -1 to 2, a sequence of length 100 to have a lot of points available. Then with the dunif command, which stands for distribution uniform, we can obtain the distribution function at each x value and plot these to see that the uniform 0-1 takes on the value 1 whenever x is between 0 and 1, and 0 everywhere else. Similarly, for the standard normal distribution, we create a sequence of values for x from -3 to 3 and obtain the distribution function with a dnorm command, which stands for distribution normal. And lastly, in the sampling distribution lecture, Allison discussed samples and their properties after repeated trials. We will recreate the sample of the binomial 10-0.5 distribution that you saw in the lecture with the simulation coin tossing. If we wanted just one sample from this distribution, we can use the R binom function, which stands for random binomial. We can specify that we would like just one sample from a binomial distribution with sample size or trials equal to 10 and the probability of success 0.5. We can see that in this one sample, we obtained 4 heads. Let's try creating 1,000 samples. That is, we would like to perform 1,000 experiments where each consists of tossing a coin 10 times. We'll store the number of successes or heads for each of the 1,000 experiments in binom sample. With the table command, we can see what our outcomes were and how often we observed 0 successes, or 1 or 2, or so on. We can save these frequencies and plot them to get a visual representation of the samples obtained. Don't be surprised if the numbers you obtain are very different when you try to do this yourself. After all, these are random samples, and just like in real life, when you toss a coin, you know that the outcomes you get in one sample can be very different than in another sample. But what should remain the same, even if your samples are different, are the properties of the sampling distributions you learned.
In the last set of lectures, we saw how we can use a simple probability model to describe some of the randomness that we observe in the real world, which leads to variation in the possible values we could observe. In any one experiment, we don't know what the outcome might be, but the probability model gives a structure to the chances of the possible values that we might observe. We were also introduced to the concept of a sampling distribution, which is the probability distribution for a statistic that we can calculate from some data, such as possibly a proportion or a mean. Now we're going to go back to starting with the real world, our data, and developing some inferential procedures so that we can say what we can about the theoretical world that we're interested in. To review the way we're thinking about data and the inferential process, let's look again at the underlying structure. In the real world, we have some observed data. These could be life expectancies or age estimates on skeletons, or counts of people developing HPV infections, or the sequence of heads and tails we get when we're repeatedly flipping a coin. We don't observe the theoretical world, but that's what we really want to understand, given the imperfect and incomplete information that we have in our real-world data. In the theoretical world, we might have a scientific model that describes the nature of the variables, and we have a statistical model that describes the nature of the variation or the probabilities associated with the variables and the statistics that we observe in the real world. We use the data from the real world in conjunction with the models we've devised in the theoretical world in order to make conclusions. Sometimes we think of the theoretical world as a population from which we've observed a sample to get our data, and the goal is to make our inferences about the population based on that sample. When introducing probability, Jeff started by flipping a coin 10 times. We know that a coin is equally likely to come up heads and tails, so we'd expect to get 5 heads and 10 flips. That's what our scientific model in the theoretical world says. Indeed, the probability model for the number of heads when flipping a coin a fixed number of times has this distribution, which is called the binomial model, and which has expected value, or mean, of 5. The binomial model is our statistical model in the theoretical world. But of course, there's also some variance in the number of heads we might get in our 10 flips. We don't expect to get exactly 5 heads each time. Indeed, Jeff got 6 heads. This binomial model is our sampling distribution for 10 flips of a coin, where what we're interested in is the number of heads. We can see from this distribution that 6 is a reasonably likely value, and although it's possible to get 0 or 1, or 9 or 10 heads, these extreme values are quite unlikely. We could also think about this in terms of the proportion of heads. We'd expect to get 50% heads, or a proportion of 0.5, but 60% heads, as Jeff got in 10 flips, is reasonably likely. No heads or only 10% heads, or the other extreme, 90% or 100% heads, is quite unlikely. So we don't expect to get 5 heads every time, but 6 and 4 are quite possible. 3 and 7 could happen too. What's the limit? Where do we draw the line for the range of possible values for the proportion of heads that is what we'd expect to get most of the time? Back in the introduction to probability, Jeff also flipped a beer cap that was red on one side and silver on the other. In his 10 flips, the beer cap came up red 4 times. Now, if a beer cap is equally likely to come up red or silver on each flip, then the number of reds in 10 flips would have the same sampling distribution as the distribution for the number of heads when flipping a coin 10 times. And we can see that 4 is a possible value with a reasonable probability. But after just 10 flips, I wasn't convinced that 40% is a reasonable estimate of the proportion of reds when flipping a beer cap. Indeed, there seemed to me a lot of other plausible values for the proportion of reds. And even if flipping a beer cap is not 50-50, say there's only a 20% chance of getting a red cap, then we'd have this sampling distribution, which comes from another binomial distribution with 10 flips, but now a probability of 0.2 of seeing red. And getting 40% reds still seems reasonable. So I put Jeff to work, and I had him flip the beer cap 990 more times for a total of 1,000 flips. It took him a while, but he finished and got 576 reds in his 1,000 flips. So now we've flipped a beer cap 1,000 times and observed 576 reds. This is our real-world data. We have a statistical model for this situation. It's binomial again for the 1,000 flips. But this time, we don't know the probability of getting red on any one flip. So now the question is, what can we say about our beer bottle cap and the proportion of times it comes up red when flipped? We can estimate this proportion. We have an estimate of 57.6%. This is a statistic calculated from our data, and it seems like a reasonable estimate for our parameter in the theoretical world. But it would be good to say more. I don't really believe that it is exactly 57.6%, and I'd like to know a range of plausible values for the theoretical world parameter. I'd like to know if, based on these data, it could be as low as, say, 40%, or maybe as high as 60%. It may not seem like estimating the proportion of times a flipped beer cap comes up red is a pressing scientific problem, but this scenario is extremely common. Governments and political parties and the press regularly use polls to estimate the proportion of people who are going to vote for a particular candidate or who support a particular issue, such as whether or not we're willing to pay more tax for more subways. They survey a sample of people to make inference about a population. This is our observed data, analogous to our beer cap flips and how many came up red. And the parameter they're trying to estimate is the proportion of people who support the candidate or are in favor of more taxes in the population, corresponding to the true probability of a beer cap coming up red when flipped, what we might see if Jeff flipped it infinitely many times. Let's introduce one more example that we'll be using in the upcoming lectures. A facelift is a common cosmetic surgical procedure, and one of the goals of patients undergoing the surgery is typically to look younger. A few years ago, some surgeons came to the Statistical Consulting Service at the University of Toronto to ask for our help in quantifying just how much younger a patient might look after such surgery. They wanted to be able to tell their potential patients that, on average, people look X years younger. So they took photos of 60 patients just before their surgery and again 1 year later. Then for each photo, they asked 10 people to estimate the age of the person in the photo, and they averaged the 10 estimates together for a measure of the perceived age. How much younger a person looks post-surgery could then be measured as the difference in the perceived age for their before versus after photo, adjusted for the year that passed between when the photos were taken. So we have some real-world data measured on a sample of 60 people, and we'd like to make inferences about a theoretical world which includes the population of all facial plastic surgery patients. We can estimate the mean perceived age change, but we'd also like to know how precise that estimate of the mean is. If the surgery, say, makes people look 10 years younger on average, based on our data, do we think the theoretical world mean might be as high as 15 or as low as 5? So in addition to the estimate of the theoretical world mean, we need a range of plausible values for it. The topic of the next few lectures is confidence intervals, which are methods for giving a range of plausible values for our theoretical parameters, given the information we have in our data from the real world. As we go forward into inference, remember that in order to use inferential procedures, we need our data to either come from a randomized experiment or from a random sample from some population, or at least that we can think of as a random or representative sample of a population, collected without any bias. If there isn't any randomization, we don't have a probability model in our theoretical world, and our inferential procedures don't apply. And another note before we go forward, the inferential procedures that we'll be using for the next little while all assume that our data are independent. That is, there's no relationship between any of the observations. This is the most important condition that we need for inferential procedures. If we don't have independence, we need much more complicated methods.
In this lecture, we're going to learn about confidence intervals for proportions or for the probability of something occurring. This will allow us to understand how those polling companies compute things like something is accurate with a margin of error of plus or minus 4%. To start off, let's remember again that example with flipping the bottle caps. If we flip a cap 1,000 times and get 576 red, what does that tell us about the true probability of getting red when you flip the cap? Well, if we let P stand for this unknown but true probability of getting red when you flip the cap, then we could estimate P just by the proportion. So the estimate, which we'll write as P hat again, is 576 divided by 1,000, or 57.6%. But the question is, how confident are we? How sure are we that P really is how close to 57.6%? Well, with everything we've learned so far, we can figure this out. We already know that the distribution of P hat has a mean and a variance. In fact, the mean of P hat, or expected value, is equal to P, so that's good. The variance of P hat, well, we worked that out previously, and that works out to P times 1 minus P, all divided by N, where N is the number of samples, which in this case is 1,000. Now, we also know the central limit theorem, and it tells us that since P was made up of an average or a proportion of lots and lots of flips, that it approximately follows a normal distribution with this mean and variance. That is, we can say that P hat has a distribution approximately which is normal with this mean and this variance. Now we can do a little bit of manipulation. If we subtract off the mean and divide by the square root of the variance, then we get a quantity which has approximately the standard normal distribution. Now, the standard normal distribution is something we know all about. We can graph, and we can get the probabilities for it too. For example, it turns out, for the standard normal distribution, that the area under the curve between minus 1.96 and plus 1.96 is just equal to 95% of all the area. So it means usually, if you have a normal distribution, you'll be between minus 1.96 and plus 1.96, which means that only 5% of the time will you be farther away than that. So in other words, the probability that this quantity, which has approximately a standard normal distribution, will be more than 1.96 is approximately equal to 5%, or equal to 0.05. Now, when we rejig this and work it all around, we end up by concluding that the probability that P is between P hat minus 1.96 times the square root of P times 1 minus P over N, and P hat plus 1.96 times the square root of P times 1 minus P over N is about 95%. Now, this is what we will call a 95% confidence interval. We're saying that we're 95% confident that the true unknown value of P is somewhere in this interval. Now, of course, the true value of P isn't random. It's really more P hat that's random because we did a random sample by flipping that bottle cap over and over again in order to try to compute it. But nonetheless, we call this a confidence interval, and we say we're pretty sure that P is within this range, or at least that the probability it's outside this range will be only 5%. Or in other words, 19 times out of 20 it'll be within this range. Only 1 time out of 20 will it be outside this range. Now, if we understand what we did for the bottle cap, then it's easy to do it in general. We can say if we have any experiment with a certain probability of, let's call it success, like getting red, let's say, and if we experiment and get n different experiments or trials, and then we say, well, let's look at the proportion of successes, so the number of successes divided by the number of trials, we'll call that P hat. It's our estimate of the true probability of success on each trial. And then we still know the mean and variance, just like in the previous example. We can still rewrite everything and end up with this same formula that says that the probability is 95% that the true value P is between P hat minus 1.96 times the square root of P times 1 minus P over N and P hat plus 1.96 times the square root of P times 1 minus P over N. And this gives us, again, the 95% confidence interval. There's a few other things we can say here. One is, you might think this isn't that useful because, after all, the confidence interval has P in it, but P was unknown. Well, there's two ways to proceed there. One is we could say, well, P is probably pretty close to P hat, so let's just kind of substitute in P hat instead of P. That's often done. Another thing that's done, as we'll see in more detail in the next lecture, is to say, well, this can actually be bounded by substituting in when P is a half, because that's the widest interval that we could get. So what it means is that we can use as a confidence interval that same interval, but this time substituting in when P is a half, and that gives us a slightly wider confidence interval, so we're being a little bit cautious or conservative, but it's actually very useful, and this is what's often done. For another example, let's talk about a public opinion poll. So here's an opinion poll from a recent United States presidential election, and it talks about the percentage of support that each of the candidates had when they did their survey. And at the end it says, oh, it had a margin of error of plus or minus 4%. Well, now that we understand confidence intervals, we can understand what they're saying. Indeed, if we remember that formula for the confidence interval, we had that range was between p hat minus something and p hat plus something. Well, that something is often called the margin of error. And indeed, if we compute in this case, we can say, well, the margin of error, when we stick in the conservative assumption that p is a half, then we compute the margin of error to be just a little bit more than 4%. So that's why that opinion poll said that the margin of error was plus or minus 4 percentage points. They meant that when you compute the half width of the 95% confidence interval, that it does indeed work out to be approximately 4%. Now you might think, why do we have to stick to this 95% confidence interval? Or why do we have to find an interval such that the quantity is in it 19 times out of 20? The answer is, you don't. You can compute any confidence that you want just by going back to that graph for the normal distribution and saying, well, we knew that if you were at plus or minus 1.96, then you'd have about 95% of the area. But you can do differently. For example, if you just do between minus 1.645 and plus 1.645, then you'll still get about 90% of the area. So you can use that value to make 90% confidence intervals. Or if you want to be more careful, and you go from minus 2.576 up to 2.576, then you'll get about 99% of all the area underneath the curve, and that's the way to get 99% confidence intervals. Indeed, for any value of alpha, if you want to make sure that the probability that you're wrong is only alpha, you can find a value, sometimes called z sub alpha over 2, such that the area under the normal curve, which is less than minus z sub alpha over 2, is equal to alpha over 2. And then if you take the interval from minus z sub alpha over 2 to plus z sub alpha over 2, then that will contain 1 minus alpha of the area. That is, the part you miss will only be alpha. And that's a way to get confidence intervals at the confidence level 1 minus alpha. So if we go back one more time to that experiment with the bottle caps, well, in that case, n was 1,000, and the number of successes was 576. And in this case, well, if we want a 95% confidence interval, then it would go from p hat minus 1.96 times the square root of p times 1 minus p over n, but when p equals a half, which is from 54.5% up to that same thing plus the 1.96, which in this case is a little over 60%. So we can say we're 95% confident that the true value of p, when you flip that bottle cap of getting red, is within this interval. If we didn't want to be quite so certain, but just 90% certain, then we could take the interval where instead of 1.96, we'd use 1.645, and we get an interval that way, which would be a little bit narrower because we're pretty sure, although not quite as sure, that it's in this narrower range. If we wanted to be really careful and wanted to be really sure, we wanted to be 99% confident, then we would take a wider interval, this time using the value 2.576, in order to get a confidence interval which is a little bit wider, but we're even more confident that the true value of p is somewhere in this range. So in this way, we can see that there's a bit of a trade-off between how certain we want to be and how small an interval we want to be, how accurate we want to be. But nonetheless, we can see that by using this idea of confidence intervals, we can understand once we do an experiment what it really means. So the proportion is probably pretty close to the true value, but not exactly there. And this gives us an interval that we can say we're quite confident that the true value is somewhere in this interval, this confidence interval.
The goal of this video is to learn how to determine the sample size you need when trying to estimate a proportion. If you've ever paid really close attention to polls, you may have noticed that very often they survey just over 1,000 people. So where did this 1,000 come from? That's what we're going to learn. When planning any study, determining the number of observational or experimental units that are needed is an extremely important consideration. This is our sample size. If the sample size is too large, we're unnecessarily wasting time and resources and unnecessarily exposing our observational or experimental units to any risks or inconveniences that might be associated with being studied. On the other hand, if our sample size is too small, we won't be able to investigate what we want to investigate, and we won't have precise enough estimates in order to be able to make meaningful conclusions. The topic of this video in particular is determining the sample size when our goal is to estimate a population proportion, and we do so with sample data collected from a simple random sample from the population. Here's an example of a typical poll published on the Toronto Star newspaper's website in 2011. Rob Ford became Mayor of Toronto on December 1, 2010. He was elected on a platform that he called Respect for Taxpayers. This included the elimination of any spending in the city budget that he felt was unnecessary. Of course, the reality of implementing budget cuts is always difficult and controversial, and, as the headline suggests, the people of Toronto's support for the cost-cutting dropped as they saw programs important to them being eliminated. I've extracted a few excerpts from the article so that we can talk about the numbers. In particular, 1,046 people were surveyed. Of these, 42% said that they approved of the job Ford was doing during the budget-cutting process. And the margin of error of this estimate is plus or minus 3%, 19 times out of 20. 19 times out of 20 is 95%. Using the methodology used for this poll, and assuming, rightly or wrongly, that the only error is due to the variability in the sampling distribution, a 95% confidence interval for the proportion of adults in the entire city of Toronto who supported Rob Ford is our estimate, 42%, plus or minus our margin of error, 3%, for a 95% confidence interval from 39 to 45%. Let's step back now to the planning stages of the poll. In polling, a 3% margin of error for a proportion has become a standard value, accepted in most circumstances, resulting in a confidence interval with a range of 6%. We saw in the last video that a margin of error for a proportion is a value from a normal distribution or a quantile, z alpha over 2, times the square root of p times 1 minus p divided by n. Suppose we know that we want our margin of error to be 3% for a 95% confidence interval, and we want to see how many people we need to poll. Since we want a 95% confidence interval, as we saw in the previous video, our normal quantile is 1.96. So we let the margin of error be 0.03 and take our formula and solve for n. There is, of course, a complication here. We haven't collected any data yet, so we don't know what p is or we don't have an estimate for it. The typical course of action is to take the worst-case scenario. Since we don't know what p is, we'll plug in the value that would result in the largest margin of error. Then if our estimate of p is something else, we'd end up with a smaller margin of error, which is better than getting a larger one than what we planned for. Our margin of error includes the expression p times 1 minus p. Here's a plot of that for p ranging from its possible values 0 to 1. We can see it's a quadratic function that has a maximum value which occurs when p is equal to 1/2. So that's the value of p that maximizes our margin of error. Plugging in p equals 1/2, solving for n, gives 1,067 as the necessary sample size. Any pools you've seen that have a sample size a little bit bigger than 1,000 have used a calculation like this. What if we wanted a smaller margin of error, say 1% or 0.01? Solving the equation, again using p equals 1/2, the worst case scenario for the margin of error, gives 9,604 for our required sample size, which is 9 times the 1,067 that we saw for a margin of error of 3%. So to cut the margin of error to 1/3 of its previous value, we need to increase the sample size 9-fold. Similarly, if we wanted to halve the margin of error, we need 2 squared or 4 times the sample size. So lowering the margin of error is expensive in that it requires a much larger sample size. How would the required sample size change if we wanted a 99% confidence interval instead of a 95% confidence interval? Your intuition might tell you that we need a larger sample size to have more confidence. And indeed, this is correct. Let's stick with our margin of error of 3% or 0.03, and for our normal quantile z alpha over 2, we'll use 2.576, which is the value that we require for our 99% confidence interval. This gives a sample size of approximately 1,843. So we need about 800 more people than we needed for the 95% confidence interval. If instead we wanted 90% confidence, you could probably guess that we'd need fewer people, and indeed in that case we'd only need 752. Here's another City of Toronto poll from the Toronto Star. As the headline says, this one was massive. They surveyed 12,848 people. Why did they include so many people in their sample? The City of Toronto is broken down into 44 wards, and the researchers wanted to be able to estimate the proportion of Ford supporters on a ward-by-ward basis. The article claims that the margin of error of this poll, with 95% confidence, is 0.9%. While that may be true for a proportion calculated using data from all 12,848 respondents, it's not true for any estimates on a ward-by-ward basis. If we assume that there are equal numbers of respondents in each ward, which probably wasn't the case, but let's use that as an approximation, then dividing up the 12,848 respondents among the 44 wards gives about 292 respondents per ward. The resulting margin of error, 5.7%. This situation also illustrates something we must always keep in mind with confidence intervals. If we have a 95% confidence interval, we expect it to cover the population proportion 95% of the time. In other words, 95% of such intervals include the population value that we want. The flip side of that is that it misses 5% of the time. Unfortunately, we never know whether we're in the 95% or in the 5%. However, with 44 confidence intervals, one for each ward, we have a pretty good chance that we've missed the true P in at least one of those confidence intervals. Since we expect to miss about 5% of the time, in 44 confidence intervals, we'd expect to miss the true proportion about twice. But we don't know in which of those wards we missed it. This situation with confidence intervals for each of the 44 wards in Toronto illustrates a situation where we need to be cautious in interpreting polls. In any situation where we have multiple polls, a common example is the daily tracking of public opinion on a matter, and we have a 95% confidence interval for each poll, we expect then that 5% of the confidence intervals will miss what we're trying to estimate. That's not a problem. It's exactly what we expect from the randomness in the sampling process. We just have to be careful not to interpret the results as if the results of all of the polls together will all cover all of the population parameters 95% of the time. And no matter how large our sample size for a poll is, the resulting confidence interval likely won't capture the population proportion if the procedure suffers from non-response bias, in which part of the population is missed in the polling process. Maybe some people don't want to participate, or it suffers from improperly worded questions that lead to response bias. The procedure to construct the confidence interval assumes we have a simple random sample, so that every possible sample from the population is equally likely to have been chosen. Polling organizations have complicated methods for dealing with the bias that results from people not responding to their polls. Each organization has their own proprietary method, which is sometimes why you see results from different organizations that don't agree, and why some organizations are sometimes accused of their own biases.
In this lecture, we're going to continue our study of confidence intervals. So far, we've learned about confidence intervals for a proportion, when we're trying to estimate the probability of something occurring, whether it's flipping a bottle cap and it coming up red, or whether it's surveying a voter and seeing if they're going to vote for the candidate. Now we'd like to extend that to other kinds of data where we're trying to estimate the true mean of the data in terms of a sample. So to start off, let's remember what we did for proportions. Let's go back to the bottle cap experiment. And in that case, we estimated the probability of getting red just by what we called p hat, the fraction of times that we got red from the data. And then we said, well, this p hat, we know that its mean is the true p, so that's good, and its variance satisfies a certain formula. But also, this proportion is made up of sort of a sum or an average of a bunch of different influences, so the central limit theorem says that it's approximately got a normal distribution with that mean and variance. Once we know that, then we can rejig it to get something that has a standard normal distribution, and then we can get a range that 95% of the time it will be within, and then we can do a little more manipulating and end up with a 95% confidence interval. We also had the problem that this confidence interval was in terms of p, and p was unknown. Well, but we can substitute p hat for p, or we can substitute a half for p to be more conservative, and either way, we get a confidence interval. Now, let's consider the data that Allison presented last time about the number of years younger that 60 different patients were perceived after undergoing plastic surgery. Now, the data in this case consists of the number of years younger that each of the 60 people is perceived. So the first one was 2.8 years younger, the second one was 9.1 years younger, and so on, up to the 60th one, who was 5.7 years younger. So what we'd like to know is the true mean value for the general population of people who undergo this plastic surgery. That's the theoretical world, and we'd like to know the theoretical or true mean value, which we'll call mu. But all we have are the data. Now, we already know that we could try to estimate mu by x bar, the sample mean, the mean of those 60 numbers that we got, the average. But does that mean we're sure that on average exactly 7.177 years is the perceived amount younger when anyone undergoes this plastic surgery? No, there's some uncertainty in the value of mu, and we would like to get a confidence interval for mu again. Well, just like last time, we know some things about the sampling distribution of this x bar. We know that on average, it equals mu, the true mean, so that's good. But we also know it has some variance. In this case, the variance is equal to sigma squared over n, where sigma squared is the true variance of the number of years younger perceived of all the people who get this plastic surgery. Now, again, this x bar is made up by averaging a bunch of different values, in this case 60 values. So again, the central limit theorem says that approximately this x bar has a normal distribution with that mean and that variance. Well, from there we can proceed exactly as we did before. We can say, okay, we'll subtract off the mean and divide by the square root of the variance to get something that's a standard normal, and then we'll use this figure of 1.96 as the possible plus or minus range for the standard normal to happen 95% of the time, or 19 times out of 20. And then we'll rearrange that a little bit just like before and end up with a 95% confidence interval for the true mean mu in terms of x bar minus 1.96 times the square root of sigma squared over n, and x bar plus 1.96 times the same square root. So now we have a confidence interval just like before. The problem is just like before, it's in terms of an unknown value. The last time the confidence interval was in terms of p, which was unknown, but we had some tricks for how to make a substitution. This confidence interval is in terms of sigma squared, which is the true variance of the different number of years when different people get plastic surgery. And of course, we don't know that either. So what are we going to do? Well, let's start by remembering that formula that we had a while back for the sample variance and the sample standard deviation, which allowed us to try to estimate the variance and the standard deviation S from a sample. Maybe that will help us here. So here we have a confidence interval, but in terms of this unknown sigma squared. So maybe we can just substitute in S squared instead of sigma squared. Well, we almost can. There's some good properties there. For example, the expected value of S squared turns out to be exactly the true unknown variance sigma squared. So that's good. And in fact, that tells us why we divided by n minus 1 instead of n when we had that formula for the sample variance. It turns out, though, that when we try to now use our usual trick of subtracting off the mean and dividing by the square root of the variance, well, now it's sort of a sample variance, and it's not quite the same, and it turns out we get a slightly different distribution. It's not actually the standard normal distribution, but it's pretty close. It's something called the t distribution, with n minus 1 of what are called the degrees of freedom. It's just a parameter for us. But we have this new distribution, which is almost like a normal distribution, but it's not quite. To illustrate that, we can look at a couple of graphs. Here's the standard normal distribution in blue compared to a t distribution with only 3 degrees of freedom in red. And we can see they're pretty similar, but the t distribution is a little bit wider, corresponding to having more uncertainty because we didn't know the true variance. We had to estimate that too, so it made things more uncertain. But as we go up to higher degrees of freedom, it gets closer and closer to a normal. Here it is comparing a standard normal to a t distribution with 10 degrees of freedom, and we can see already they're quite close. So the t distribution is pretty similar to the normal distribution, especially when the degrees of freedom are large or when you have lots of samples, but it's a little bit different. So how does that help us? Well, if we go back to that case of the number of years that we perceive people to look younger, well, we had a 95% confidence interval in terms of the true variance sigma squared, but if that's unknown, well, we could replace it by S squared, but then we would also have to use the t distribution. The t distribution in this case has 59 degrees of freedom because it's n minus 1, and n was 60 was the sample size. So you might think that's going to change this number 1.96. How's it going to change it? Well, here's a table which gives some of the values, which you can look up in a book or you can get the computer to tell you. And they say if you're making that 95% confidence interval, well, for the normal, you use that number 1.96. For a t distribution, you have to use slightly larger numbers because we have slightly more uncertainty, so we need a larger interval before we're just as confident. But the amount you need, which is larger, isn't that much larger. Even with only 3 degrees of freedom, okay, well, it's from 1.96, instead you need 3.18. But as you go up to 6 or 10 or 15 or 20 degrees of freedom, it's getting pretty close to that 1.96. By the time you're up to 59 degrees of freedom, which is what we have here, it turns out to be exactly 2.00 as the number you need instead of 1.96, just a little bit larger. And as the number of degrees of freedom get larger and larger, it gets closer and closer to that same 1.96 as for the normal. So returning to our calculation, we can say we've still got that same confidence interval, except we need to replace that 1.96 by a 2.00. And then we can compute the confidence interval the same as before using our value x bar and also using this s squared value. And when we plug in the numbers for that data, here's what we get. And it works out to an interval between 6.42 and 7.94. So this tells us that the true mean of the number of years was somewhere between these two numbers. And that's how we get a 95% confidence interval for this mean, this unknown mean in terms of number of years. Or for another example, let's consider again our old friends, the skeletons. In that case, we had 400 observations, so n was 400, For each one, we had the difference between the estimated age and the actual age at time of death, and the mean of those 400 different age differences turned out to be about minus 14.15, and the sample variance of those 400 observations turned out to be about 199.5. So what if we wanted a confidence interval for the true mean of the age differences? Well, it turns out that if n is 400, so there's 399 degrees of freedom, then the value we want to use for a 95% confidence interval, instead of 1.96, well, is about 1.966, so just a tiny bit larger. And we can plug that in and we see we get a 95% confidence interval for those age differences, for the true mean of them. Or maybe we only wanted a 90% confidence interval. We didn't need to be quite so confident. Well, in that case, instead of the value 1.645 for the normal, turns out we use a value about 1.649, just a tiny bit higher again. And we can plug that in, and sure enough, we get a 90% confidence interval for the true mean of those age differences. So whether we're studying skeletons or whether we're studying anything else, if we have some data and we want to know the true mean, and all we have is a sample mean, then we can use these simple properties of the normal distribution and the t-distribution, which is almost the same, in order to get approximate confidence intervals. And that gives us a range of values that we're pretty sure include the true values.
In many inferential procedures, there are necessary conditions that must be satisfied in order for our sampling distribution of our estimators to be appropriate. And an important consideration in any analysis is to examine whether or not these conditions hold. For confidence intervals, if these conditions don't hold, we can't claim that the confidence intervals have the coverage that we say they do. Without the necessary conditions, for example, we can't say that a 95% confidence interval covers the true theoretical parameter for 95% of all data sets. The actual coverage might be much less. In this video, we'll take a closer look at the necessary conditions we need for the two types of confidence intervals we've covered so far. For a confidence interval for a proportion, or for the probability of getting a success on some experiment, we have this formula. And for that p in the margin of error, we saw that we can either plug in our estimated value p hat, or if we want to be a bit conservative, we can plug in 1/2. The construction of this formula required two conditions to hold. First of all, we needed all n observations to be independent of each other. So, say we were estimating the probability of getting a red when flipping a beer cap, we need each flip of the beer cap to be independent. If we're estimating the proportion of Torontonians who support the job that their mayor is doing, the people polled must not be related. This independence condition is hard to check using statistical methods, but it's extremely important to think about the context of the problem and whether or not it applies. For our second necessary condition, we note that the formula also includes the quantity z alpha over 2, which is a critical value from a normal distribution. As we saw, p hat can be thought of as an average, and in order for this formula to be appropriate, we need n, the sample size, to be large enough for the central limit theorem to kick in so that p hat is approximately normally distributed. We'll now investigate the effects of this second condition on the coverage of a confidence interval. We'll use this applet, which simulates data and calculates the resulting confidence interval for any value of the theoretical parameter p and any sample size n that we want. In this applet, the Greek letter pi is used for our theoretical parameter that we've been calling p. Let's start with an example that we're quite familiar with now, flipping a coin that's equally likely to come up heads or tails 10 times. So we'll keep pi at 0.5, that will be our probability of heads or our probability of getting a success, and we'll change the sample size n to 10. Our first random simulation of this gets 6 successes and 4 failures, so p hat, our proportion of successes, is 0.6. We can see the sample we got here in this box showing the 6 successes and 4 failures. Throughout, I'm going to stick with a confidence level of 95%. Using our formula, the confidence interval is from 0.296 to 0.904, as we can see here in the applet. The vertical bar is our theoretical parameter. The applet draws a confidence interval from its lower to its upper limit, and if it crosses the vertical bar, then the confidence interval includes p. And we can see that this confidence interval from 0.296 to 0.904 includes 0.5, and the confidence interval crosses the theoretical bar. So this confidence interval captured the theoretical value that we're trying to capture. Let's try another sample. Again, we get 0.6 for the proportion of successes. Let's try it again. This time we get 8 out of 10, a less likely value. And we now have a confidence interval that does not include 0.5. It doesn't cross our vertical bar, so it gets colored red. So far, 2 of our 3 simulated confidence intervals have done what we want them to do. That is, they include our theoretical parameter p of 0.5 in between its limits. To better see how well this is working, let's simulate 100 such confidence intervals. Confidence intervals aren't designed to be perfect. Indeed, they're designed to miss a certain percentage of the time. And since we're doing 95% confidence intervals, we expect our confidence interval should miss 5% of the time if it's appropriate. So in the 100 confidence intervals we're simulating, and assuming that the necessary conditions are being met, we'd expect that 5 of them would not include 0.5. They'd miss our theoretical parameter. And here are our 100 confidence intervals. We can see all of the 100 estimates of p hat in this plot. The estimates marked in red are the less likely values, and they correspond to the red confidence intervals, which don't include 0.5. There are 15 of these red confidence intervals, so we've only captured the true value of our theoretical parameter 85% of the time, instead of the 95% that the confidence interval was designed for. Did we just get unlucky? Let's try this again with another 100 simulations of these 10 coin flips, and we get 84% of our confidence intervals capturing the true parameter. Again, less than 95%. So it seems that a sample size of 10 isn't enough to rely on the central limit theorem normal approximation for the sampling distribution of p hat. What if we flipped our coin 100 times? Will the normal distribution be a better approximation to the distribution of p hat than it was for n flips? Let's try 100 simulations again. This time, 94% of our confidence intervals included 0.5, which is very close to the 95% that we expected. And one more time, we get 94% again. So it seems that a sample size of 10 wasn't sufficient, but 100 looks pretty good for our central limit theorem approximation, at least when our theoretical value of p is 0.5. When the probability of getting a success is 0.5 or 1/2, the sampling distribution of p hat is symmetric, centered around its expected value of 0.5. Here's the distribution when n equals 100. But regardless of the sample size, the shape is symmetric with a strong central peak, both features of the normal distribution. When the theoretical parameter p is closer to its limits, let's look first of all at, say, p equals 0.05, so the probability of success is only 5%. Then the sampling distribution of p hat is skewed, unlike the normal distribution. And as you might expect in this case, we need a larger sample size before the normal approximation works well. Let's investigate this with the applet. We'll change the theoretical parameter to 0.05 and take 100 samples, each of size 100, and calculate the confidence interval each time. These are squished over to the left now because we're trying to capture 0.05, a small value on this scale. Instead of 95% of our confidence intervals capturing 0.05, we got 90% of our confidence intervals capturing our theoretical parameter. Let's try again, get 90% again. Let's see if this is a fluke. Try another time, 91%. And once more, this time 88% of our confidence intervals capture our theoretical parameter. So it seems that the coverage of these confidence intervals isn't bad, but it's not the 95% that we claim. Let's try something even more extreme. This time we'll make our probability of success 0.01, only 1%. The sampling distribution of p hat, then, is quite skewed. With a sample size of 100 and a probability of success of 0.01, only 59% of our sample of 100 confidence intervals capture the theoretical parameter. That's not very good. Let's try again. This time we get 66%. Still not very good. So clearly something's not working with our confidence interval. For a theoretical p that's so extreme, only 1%, 100 is not a sufficient sample size for our normal approximation. So now let's try bumping up our sample size to 1,000. This time 94% of our confidence intervals captured the theoretical parameter, very close to the 95% claimed. So for such a small theoretical p, a sample size of 1,000 is at least sufficient. The normal distribution is a continuous distribution, yet in this case we're using it to approximate a discrete distribution, discrete since we can only get an integer number of successes. So the confidence level is often less than 95%, or whatever level is chosen, because the normal distribution isn't a perfect approximation. Many improvements have been devised for this method of confidence intervals for p, including 2 that are implemented in this applet that provide more accurate coverage. It's also worth noting that these confidence intervals are designed to account for the imperfections we have because we only have a finite sample of data. And if we had a different sample, we'd likely get a different estimate. In polls, there are often many other sources of error, such as non-response bias and the error that results from poorly worded questions, and we haven't accounted for any of these sources. Now let's switch to our second confidence interval, this time for our mean, where we have this formula. The necessary conditions for this confidence interval to hold, in other words, for this confidence interval to truly capture the true mean the right percentage of the time, are first of all, that the n observations are independent. Again, independence is difficult to check, but there's no way around this one. You can think of it this way. If the n observations aren't truly independent, then your sample size really isn't as big as n. It's something a little bit smaller, and thus that formula doesn't apply. Our second condition is that we need x bar, our estimator, to be approximately normally distributed. And we'll investigate how well the central limit theorem works in this context by how well our confidence intervals work. Again, we'll use an applet where we start with a theoretical model and simulate several confidence intervals to see how often we capture the true theoretical mean within the confidence interval. This time, we'll start with a normal distribution. This normal distribution has a mean of 500 and a standard deviation sigma of 100. 500 is our theoretical parameter that we want to estimate, and it's marked by the vertical bar below the histogram. We'll also work with a sample size of size 10. We'll take a random sample, and you can see in yellow the sample values that were selected to be our data. For this sample of size 10, the average, x bar, which is our estimate of mu, is 510, and the standard deviation of the sample is calculated to be 91.21. That's our S. Again, we're going to stick to 95% confidence throughout. The critical value we need from the t-distribution with 9 degrees of freedom for a 95% confidence interval is approximately 2.26, and a quick calculation gives our confidence interval with a lower limit of 441.81 and an upper limit of 575.19. This includes 500, the mean of our normal model, and, as we can see, the line joining the lower to upper limits crosses the vertical bar at 500. So this confidence interval was successful at capturing the theoretical mean. Let's simulate some more samples of size 10 and see how the resulting confidence intervals behave. Here we have one that misses a theoretical mean. By chance, for this sample, we got a lot of smaller values, and our estimated mean is only 412, and our upper limit 481.28. so our confidence interval doesn't include 500. For this applet, we can show confidence intervals from 20 samples on one screen. So finishing that up in these 20 samples, the resulting confidence intervals miss the true mean just that once. So our 95% confidence intervals correctly captured what they were supposed to 95% of the time. You might think that was too good to be true. So let's simulate another 20 confidence intervals. This time, we missed the true mean twice. Let's do it again. In these 20 confidence intervals, we didn't ever miss the true mean. One more time, we missed it twice. And another 20 confidence intervals also didn't have any misses. We've just seen a total of 100 confidence intervals for the means for samples of size 10 from this distribution. And if we add up the misses, we missed 5 times, which is exactly what we'd expect for 95% confidence intervals. The t-distribution confidence interval for the mean works extremely well in terms of capturing the true mean as many times as it's supposed to when the normal distribution is the actual distribution of the data. So let's see what happens with another distribution. We'll switch to the skewed distribution for our theoretical model, and we'll still stick with 95% confidence intervals for the mean, calculated from simulated samples of size 10 from this model. This time, the model mean is 223.1, so that's what we're hoping to capture in our confidence intervals. Our first set of confidence intervals for our 20 samples miss the model mean twice. The second set of 20 doesn't miss the mean at all. The next set of 20 misses twice, and then we don't miss it again, and then again in our 20 confidence intervals, we don't miss the mean. So in our total of 100 confidence intervals, we've only missed the mean 4 times for 96% coverage. Even when the theoretical model from where our data came is not normal but skewed, the t-confidence interval procedure works extremely well at covering the mean the right percentage of times. For t-confidence intervals for the mean to not work well, we need fairly extreme situations. Here's one, where the theoretical model puts most of the probability on values here on the left, but also makes it possible to see some very large outliers. Our theoretical mean is 83. Let's take a sample size of 10 and check what happens with 20 confidence intervals. We've missed the mean 15 times for a coverage rate of 25%. Certainly not 95%. Of course, the central limit theorem is an asymptotic result. That is, it works better the larger n the sample size is. So perhaps our estimate x bar, the average of our sample, will be closer to normally distributed for a larger sample size, something more than 10. The largest sample size this applet allows is 40, so let's increase the sample size to that, and we'll quickly generate 100 samples. In the resulting 100 confidence intervals, we missed the theoretical mean of 83 10 times, or we covered it 90% of the time. Again, these are 95% confidence intervals, so the coverage isn't quite what we claimed, but it's pretty close. This illustrates how well the t-confidence intervals for the mean work, even with this extreme situation and a sample size of only 40. Of course, in this situation, I've been completely ignoring the fact that perhaps estimating the mean may not be a sensible thing to do. Remember that when working with data, the mean or average is not a robust measure. That is, it's affected by unusual observations. When we're talking about the expected value or mean of a probability model, it is also affected by extreme values, in this case pulled up by the large values we could have. And because of these possible large values, the mean of 83 that we got here is actually larger than the possible values on the left where most of the probability is. So to summarize, the t-distribution confidence intervals work extremely well, even when the data aren't normally distributed, but not in situations where it really doesn't make sense to use the mean. This is another illustration of just how powerful the central limit theorem is. Because of it, the t-confidence intervals for the mean are extremely robust. In this situation, Robust means that they work well, giving confidence intervals with very close to the coverage claimed, even when some of the necessary conditions aren't satisfied. So we have two types of confidence intervals for proportions and confidence intervals for the means. Both of them rely on the central limit theorem in order to derive the formula. As we've seen, t-confidence intervals work extremely well, even for small sample sizes. However, the confidence intervals for the proportions tend to need much larger sample sizes in order for them to work well in terms of covering the true population parameter as often as they're supposed to. Recall that for both these confidence intervals, we also need all the observations to be independent. And if they're not, the procedures don't apply. In all inferential procedures in statistics, including confidence intervals, it's important to pay attention to the necessary conditions that must be satisfied in order for the inferential procedures to apply. And it's important to understand the implications for the results if the conditions aren't satisfied. Otherwise, we can't really make meaningful conclusions.
Confidence intervals for proportions are tutorial. Remember the example that Jeff worked through in the lecture? He flipped the bottle cap 1,000 times and observed red 576 times. Your goal was to construct a confidence interval for the true but unknown probability p of observing red. The first method you learned was to substitute p hat for p to obtain the 95% confidence interval. We'll let p hat equal to 0.576. To obtain the critical value z from the standard normal distribution, we will use the Q-norm function, which stands for quantile normal. Recall that this value z from the standard normal distribution has probability above it of 0.025, or alpha over 2. In the Q-norm function, we specify the upper tail probability of 0.025, the mean and the variance of the standard normal distribution, and since this probability is in the upper tail, we need to specify lower tail equals to false. Now the margin of error is simply z times the square root of p hat times 1 minus p hat over n, and the confidence interval is p hat plus or minus the margin of error. We could alternatively use a function called binom.convint from the binom package. Let's install the package first by navigating to Packages and Data, Package Installer, and search for the package binom. Install the package and all of its dependencies, and then load it using the command library binom. Now the binom.convint function is available to us. We must specify the number of observed successes, or reds in our case, the number of trials, 1,000, and the confidence level of 0.95. The function also requires that we state which method we would like to use to calculate the confidence interval. We will use methods equal to asymptotic to obtain the desired results similar to above. The second method you learned was more conservative. It was achieved by letting p equal to a half in the confidence interval formula. We need only change our margin of error to reflect this. So we will redefine me to equal to z times the square root of a half times a half over 1,000. And again, our confidence interval is p hat plus or minus the new margin of error. Notice that this method yields a confidence interval that is wider than the first, but only ever so slightly. The reason for this is because p hat is very close to a half, or 0.5. So in this example, the two different methods produce very similar results. For practice, try constructing confidence intervals like the ones we just did, but at different confidence levels. What arguments would you need to change in Q-norm? And how would these different confidence levels change the width of the confidence intervals? Sample size for estimating a proportion, our tutorial. In Allison's lecture, you learned how to calculate the sample size required if you wish to create a confidence interval for a proportion for varying confidence levels and margins of error. In this tutorial, we will use R mostly as a calculator,
but also to be able to find critical quantile values from the standard normal distribution. Let's remind ourselves of the formula for finding the sample size. Suppose we wished to estimate p to within 3% with a 95% confidence interval. How large of a sample size would we need to be able to do this? We know that for a more conservative estimate, and of course for the maximum margin of error, we should let p equal to 1/2. We'll let the margin of error equal to 3% or 0.03. Now to find the value z alpha over 2, we know that for a 95% confidence interval, alpha equals to 0.05, so alpha over 2 is 0.025. Using the Q-norm function, we can find this value to be approximately 1.96. Finally, the sample size required is approximately 1,067 subjects. If we wanted to have a smaller margin of error, say 1% or 0.01, we can see that the sample size required is much bigger, 9,604 subjects. This makes sense since a narrower or more precise confidence interval requires more data. What if we wanted a higher confidence level than 95%? Say we wanted 99%. Well, for a 99% confidence interval, we know alpha is 0.01, so alpha over 2 is 0.005. Our new value for z is 2.576, leading to a much bigger sample size of 16,587 subjects. So we can see that if we want to be more confident, we again require an even bigger sample size. Increasing the confidence level or the precision of a confidence interval requires additional data, which means a bigger sample size. But a larger sample size has its drawbacks. So there's generally a fine line between how big of a sample can be collected and how confident we can be in the results. Confidence intervals for means R tutorial. In this R tutorial, we will learn how to create confidence intervals for the mean. Recall the example that Jeff showed in the lecture, where the perceived number of years younger was recorded on 60 plastic surgery patients. We will read in the data and store it under plastic, and let age change be the first and only column V1 in the plastic dataset. If we wanted to calculate a confidence interval for the true mean by hand, we could obtain x bar, the mean of our sample, and var, the variance. With the qt command, we can find the critical value from the t distribution. Recall that this critical value is the value from the t distribution which has 0.025 probability above it, or alpha divided by 2. We specified the upper tail probability of 0.025, the degrees of freedom 59, and since this probability is in the upper tail, we need to specify lower tail equals to false, and save it under t. Now the margin of error is simply t times the square root of the variance over n, and the confidence interval is x bar plus or minus the margin of error. But of course, R has a much simpler function, t.test. With t.test, we need only specify the data we have and the confidence level. We will set it to 95%, but try playing around with different confidence levels and see what you can discover. T.test produces a lot of output. For now, we will focus just on the 95% confidence interval created. Notice that we obtained the same confidence interval by hand above. If we want to suppress the rest of the output and display just the confidence interval created, we can specify at the end of the command $conf.int, and this will give us the confidence interval and associated confidence level. Similarly, you can use the command t.test for the skeletal remains dataset to obtain a confidence interval for the true mean age difference.
We've already seen a number of situations where we looked at data and saw something interesting, perhaps a difference between two groups, and we wondered whether or not that difference is significant. In the next few lectures, we'll be developing the methodology for carrying out statistical tests in order to answer that question. Determining whether a difference is statistically significant involves answering the question, could that difference just be due to chance? Or is it so unlikely that it must say something else about the nature of the data. Let's review the inferential process again. In the real world, we have some observed data, and in the theoretical world, we have some models, statistical and scientific, that can be used to describe the real world. The statistical models include the variation that we naturally have in our observed data. The combination of our real-world data with our theoretical world models allows us to make conclusions based on our data. And how strong or how broad these conclusions can be depends on how our data were collected. Now, these conclusions could be about parameters in our models, or when our data were collected as a sample from a population, the conclusions could be about the population based on our sample. We're now going to start learning about using statistical tests in order to answer specific questions about the values of our population or theoretical world parameters. Here's how we look at it. If we observe something in our real-world data, could it just be due to chance? Or is it telling us something stronger about our theoretical world, perhaps contradicting an assumption that we've made about it? Several lectures ago, we looked at these box plots, which summarize life expectancies in two regions of the world. The box plots show that life expectancies in almost all countries in East Asia and the Pacific region are higher than life expectancies in almost every country in sub-Saharan Africa. Could this be by chance? Could it happen just because of the natural variability that there is in the measurements of life expectancy from country to country? To use statistical tests to answer this, we first devise a theoretical model that assumes that life expectancies are the same in both of these regions. And then we use our knowledge of probability and sampling distributions to see how likely it is to get the differences that we see between these two regions, or differences even more extreme. We are investigating whether our real-world data support what we're assuming or hypothesizing about the theoretical world, which is that life expectancies are the same in these two regions, or whether our data are providing some evidence that our assumptions or hypotheses are false. It may seem clear that life expectancies are not the same when comparing East Asia and the Pacific and sub-Saharan Africa. But what about this comparison between East Asia and the Pacific and South Asia? This one is less clear-cut, and we definitely need some methodology to investigate whether the differences are significant or not. Here's an example that we'll be looking at soon. In the probability lecture, Jeff flipped a beer cap that was red on one side and silver on the other 10 times, and he got 4 reds. If we assume that a beer cap, like a coin, is equally likely to come up on either side, red or silver in this case, would 4 reds be surprising? Probably not. In fact, we can't say a lot when Jeff only flipped the cap 10 times. So I had Jeff flip the beer cap a total of 1,000 times, and he got 576 reds. That's pretty close to 50-50. But if it was perfect, we would have gotten 500 reds. So assuming this beer cap is equally likely to come up red or silver, is 576, our observed data, or any value that's even further from 500, so unlikely that we think that it can't be 50-50 red or silver? If it is unlikely, we'd see what we'd call a statistically significant result. Let's quickly look at 2 more examples that we'll be examining. A recent University of Toronto study had raters examine photos of 60 patients before and after having a facial cosmetic surgery. The raters gave their guess at the age of the person in the photo, and the perceived age was calculated as the average of the raters' guesses. So for each patient, we have the difference in their perceived age from before to after the surgery. The patients, on average, looked younger after the surgery. But could that just be by chance? There's a probability distribution of possible perceived age changes. If we model it in our theoretical world as being centered at 0, in other words, we expect no perceived age change, then although some people will have positive and some people will have negative values for their perceived age change, how likely is the mean difference that the surgeons got? The other example we'll study is based on this 1992 article from the Journal of the American Medical Association. In a book published in 1868, the German Dr. Wunderlich reported on the analysis of over 1 million temperature readings from 25,000 patients, a very large data set, especially in 1868. And, ignoring fluctuations due to time of day, Wunderlich reported that 37 degrees Celsius is the mean temperature of healthy adults. This new article reports on a study to critically appraise Wunderlich's result, which stood as the standard for more than 100 years. The researchers in this article took measurements on 148 healthy men and women, and they found an average mean body temperature of 36.8 degrees Celsius. That's a little less than Wunderlich's 37 degrees. Is it a significant difference? Did Wunderlich's result need to be updated? In other words, if Wunderlich was right and his result still held when this modern study was carried out, how likely is it to get differences as large or larger than 0.2 of a degree? Wunderlich's axiom is our model for the theoretical world. Our real-world data don't completely agree, and we need to determine whether these data have a reasonable chance of occurring or whether they are giving us evidence that our theoretical world model might not be correct. In the next few lectures, we'll be studying the methodology of statistical tests. They'll give us a structure to investigate the types of questions that we've illustrated in these examples. And so that we'll be able to conclude, is the difference just due to chance? Or does it contradict an assumption we've made about our theoretical model, so there's some other explanation for the nature of the data? Welcome back. A statistical test is a little bit like a proof by contradiction in mathematics. We start by assuming something, and typically what we assume is not what we want to show. In fact, it's often the complete opposite. And then we do some work under that assumption, and we end up with a contradiction, or something that is obviously wrong. So as a result, we conclude that there must be something wrong with our original assumption. In statistics, we have to deal with the natural variability that's associated with our data. So there's uncertainty associated also with obviously wrong. And for us, obviously wrong will mean unlikely in a probability sense. In this video, we'll outline some of the steps and structure of a statistical test, and we'll introduce some of the vocabulary that is used. In statistics, tests are used to answer direct questions about the theoretical world, and the goal is to determine whether the data provide enough evidence for us to believe a claim about the population or theoretical world. Statistical tests are often called hypothesis tests or tests of significance. There are very subtle differences between these two phrases, but they're so subtle that we won't worry about them. A direct question we might want to answer with a test might be something like, is a beer cap, like a coin, equally likely to come up on either side when flipped? Or, after a facelift, does the perceived age show that people look younger? Or, is the mean healthy body temperature for a human 37 degrees Celsius? The first step of a statistical test is to formulate an hypothesis to test and specify an alternative to that hypothesis. Throughout this video, I'm going to use a court case as an analogy to a statistical test. Many legal systems around the world are based on the presumption of innocence, often referred to as innocent until proven guilty. We presume that our starting point is that anyone charged with a crime is innocent, and the burden of proof is on the prosecution to prove otherwise. In statistics, the presumption of innocence corresponds to what we call the null hypothesis, written as H subscript 0 and typically said H naught, where naught here is nothing or zero. The null hypothesis says that nothing is happening. That is, it's the status quo, or there is no relationship, or there are no differences. We use the null hypothesis as a working hypothesis. We assume it is true and see if our data are likely under that assumption, or if they contradict it. Usually in a court case, we're trying to show that the defendant is guilty, and that corresponds to our alternative hypothesis in statistics. Sometimes the alternative hypothesis is called the research hypothesis because it's what the research wants to show. The alternative hypothesis is written as an H with a subscript a lower or uppercase A. That's the notation I prefer. Some people like to write it as H with a subscript 1 in contrast to H sub 0 for the null hypothesis. Like the prosecutor who wants us to conclude that the defendant is guilty, we typically want to prove that this research or alternative hypothesis is true. And the way to make that conclusion is to see if we have enough evidence to rule out that any differences from the null hypothesis could be due to chance. So an important first step in any statistical test is to carefully define what our null hypothesis is and what the alternative is. As an example, if our goal is to show that facial plastic surgery reduces the mean perceived age, our null hypothesis would be that nothing is going on. So we'd assume that the mean perceived age change is 0, and our alternative would be that the perceived age change is positive. That's assuming we're calculating age change as the perceived age before minus after surgery. That's an example of a one-sided alternative. We're only interested if the mean perceived age change is positive, meaning patients look younger. We can also have two-sided hypotheses. In our beer cap example, if we're interested if it's 50-50, we'd be interested in whether the chance of getting reds is greater than a half or if it's less than a half. So then we'd use a two-sided alternative corresponding to not equal to a half. In most situations, two-sided tests are appropriate, and if you're ever in doubt, use a two-sided test. The first step in any statistical test, then, is to clearly specify what the null hypothesis is and what the alternative to it is. In a court case, we need evidence collected by the police and prosecution, which brings us to our second step. The second step in our statistical test is also to put together the evidence. In statistics, the evidence is provided by our data. In order to make the data useful, we have to summarize it into a statistic called the test statistic. Like any statistic, the test statistic is a numerical summary of the data. But what differentiates a test statistic from just any statistic is that it is formulated assuming that the null hypothesis holds. This is important to remember in statistical testing. We make an assumption, H0, our null hypothesis, and we then work as if it is true. So as an example, if we assume that a facelift doesn't lower the mean change in the perceived age of a patient, then we construct the test statistic under the assumption that the mean age change is 0. So our second step is to accumulate some evidence. That is, collect some data, summarize them into a test statistic, always assuming that the null hypothesis is true. Once the evidence has been collected and summarized for the judge or jury, they have the responsibility of careful deliberation. They need to decide if the evidence is overwhelming enough to reject the presumption of innocence, beyond a reasonable doubt. In statistics, the tool for deliberation is a p-value. A p-value transforms a test statistic into a probabilistic scale. It is a number between 0 and 1 that quantifies how strong the evidence is against the null hypothesis. If the evidence is not beyond a reasonable doubt, that means that chance, or the natural variability we expect, is a reasonable explanation for anything we see in our data that is not consistent with what we'd expect if the null hypothesis is true. To decide whether the results could just be due to chance, we ask the question, if the null hypothesis is really true, how likely would it be to observe a test statistic, our summary of our data, of this magnitude or even larger, just by chance? The numerical answer to this question is the p-value. The smaller the p-value, the more unlikely it is that we observe our data, assuming the null hypothesis is true. So the smaller the p-value, the stronger the evidence we have against the null hypothesis. A p-value is not a measurement of how likely it is that the null hypothesis is true. The null hypothesis either is true or isn't true. We may not know which it is, but we can't put a probability value on it because it's not random. What a p-value does tell you is how likely the observed data would be if the null hypothesis were true. It's a measure of the strength of the evidence against the null hypothesis, and the smaller the p-value, the stronger the evidence. So our third step is to determine how unlikely the test statistic is if the null hypothesis is true, and this is our p-value. And finally, we have the verdict. Our judge or jury has one of two choices. They could decide that the evidence is not strong enough to convincingly rule out that the defendant is innocent, and they'd conclude not guilty. In statistics, not strong enough evidence means the p-value wasn't small, and we conclude that our data are consistent with the null hypothesis. We can't conclude H0 is exactly true, but we can't reject it either. Or our jury could decide that they are willing to rule out the possibility that an innocent person stacked up this much evidence against them, and then they'd reject the presumption of innocence and conclude that he or she is guilty. The corresponding situation in statistics is a small p-value. We have data that are unusual enough that we are willing to rule out that the null hypothesis is true, and by chance we got the observed data that we did. In this case, we have a small p-value, and we reject the null hypothesis, concluding that we have sufficient evidence against it and that the alternative hypothesis must be true. In this case, we say we have a statistically significant result. At this point, you may be wondering how small is small for a p-value. 0.05 or 5% is a very common cutoff for small, but it's a little bit arbitrary. If we get a p-value less than 0.001, that can be considered strong evidence against the null hypothesis. Larger than that, but less than 0.01, is still pretty good evidence against the null hypothesis. And after that, it starts to get a little bit gray. Between 0.01 and 0.05 is considered small enough evidence to say the null hypothesis is not true in many situations. In other situations, even getting a p-value between 0.05 and 0.1 is enough evidence to conclude that the null hypothesis isn't true. When we get one of these larger values for our p-value, the evidence against the null hypothesis isn't as strong. And if we get a p-value greater than 0.01, that means that if the null hypothesis is true, what we've observed in our data is something that happens 10% of the time. Then we conclude that our data are consistent with the null hypothesis. Depending on the context of the problem, you might be willing to accept a larger or a smaller p-value. If concluding that you have a statistically significant result is going to incur a lot of expense or possible discomfort for people, then you'll want a smaller p-value than if the consequences of a statistically significant result aren't quite so expensive or inconvenient. So the final step in a statistical test is to make a conclusion based on our p-value in the context of our problem. To summarize, here are the 4 steps of a statistical test. In the upcoming lectures, we'll apply them to real data and real questions.
So far, we've heard the basics about hypothesis testing and p-values and so on. Now we want to try it out and see if we can compute with it. For a first example, let's remember that poll that Allison told us about, where they said that the current mayor of Toronto was supported by only 42% of the respondents in a poll. Now you might want to draw conclusions from that. You might want to say, for example, less than half of the people support the mayor. The question is, would that be a fair thing to conclude? Can we conclude from the results of that poll that indeed less than half of all the residents of the city actually support the mayor? Well, to consider that, let's start by remembering that the number of people surveyed was n equals 1,046, and the percentage of them which said yes, they support the mayor was equal to 42%. So that means the true support of the mayor, call it P, is unknown, but the estimated support of the mayor from this sample is equal to P hat, which is 42%, or 0.42. So now we want to test as a hypothesis whether the true probability P of people supporting the mayor is indeed less than 50%. So to set it up, we have to have the null hypothesis, H0, which would be that actually it's true that half the people support the mayor, versus the alternative hypothesis that actually less than half of the people support the mayor. And the question is whether we can reject that null hypothesis and say, yes, actually less than half of the people actually support the mayor. Well, how are we going to compute the p-value? We should start by remembering that in the theoretical world, assuming H0, the null hypothesis, then we can say that, well, p hat minus p divided by the square root of p times 1 minus p over n has approximately a standard normal distribution. That's what we learned before. So in this case, it means if we fill in the values that p hat minus p over the square root of 0.5 times 1 minus 0.5 divided by 1046 should have approximately a standard normal distribution. From there, we can say, well, what we observed under the null hypothesis would be that p hat minus p was the 0.42 of the population that we observed supporting the mayor minus the 0.5 of the population that we're assuming under H0 supported the mayor, which of course is equal to minus 0.08. So to compute a p-value, we want to compute the probability of observing a value that extreme or more extreme under the null hypothesis. We want to compute under the null hypothesis the probability that p hat minus p is less than or equal to minus 0.08. Well, with a little rewriting, we can say it's the probability that this quantity that we said has approximately a standard normal distribution is less than or equal to some other quantity just involving some numbers, which turns out to say what's the probability that something with a standard normal distribution is less than or equal to minus 5.17. Well, 5.17 is a pretty extreme value for the standard normal distribution, and indeed this probability is only about 1 in 9 million. So we can say, well, yeah, the p-value here is about 1 in 9 million, and that's very small. That's so small that we can say the probability that just by chance, if the mayor's true level of support was 50%, that a sample would only find 42% support is so small that we can reject the null hypothesis, and we can say that no, it's not true that the mayor's support is 50%, it's indeed true that it's less than 50%. For another example, suppose we said, yeah, we can really conclude a lot from this poll. Maybe we can conclude that the mayor's support is less than 44% or 0.44. Well, we can set things up exactly as before. Now the null hypothesis would be that p is 0.44, and the alternative hypothesis would be that p is less than 0.44. Again, this is a one-sided test, and again, we start by saying under the theoretical world, if we take p hat minus p and divide by the square root of the appropriate quantity, then we get something which has approximately a standard normal distribution. But in this case, we observed p hat minus p under the null hypothesis to be minus 0.02. So that means that the p-value is the probability of observing such an extreme or more extreme value under the null hypothesis, which in this case works out to the probability, once we readjust things, that a standard normal distribution is less than or equal to minus 1.30. Now, that's actually not so unlikely. 1.30 is not such an extreme value, and this probability is about equal to 9.68%. That's not so small. So in this case, it depends on our level of significance, but we probably can't reject the null hypothesis. So we probably say, well, okay, we were sure the mayor's support is less than 50%, but we're not so sure it's less than 44%. For another example, let's go back to that case of flipping that beer cap and trying to figure out if the probability of getting the red side up was 50% or was some other value. Well, in this case, we could write that the true probability of red is p, which is unknown, and our observed estimate p hat in this case was, well, we got 576 red flips out of 1,000, which is, of course, 57.6% or 0.576. So now the question is, our null hypothesis will be that p is actually 0.5, and our alternative hypothesis will just be that p is any other value besides 0.5. So this is a two-sided test. We're not trying to figure out if it's strictly less or strictly more than 0.5, just if it's different than 0.5. So in this case, under the null hypothesis, we've observed that p hat minus p is 0.076. So the p-value now should be the probability of observing in absolute value, because it's a two-sided test, an observation which is equal to that extreme or more extreme under the null hypothesis. And we can use our same trick as before. We can rewrite things by dividing by that square root of p times 1 minus p over n, and we end up saying that it's the same as the probability that the absolute value of a normal is at least 4.81, which is of course twice the probability that a standard normal is less than or equal to minus 4.81, because it could be less than minus 4.81 or more than 4.81. And that works out to about 1 chance in 650,000. So again, it's extremely small. And again, we can reject the null hypothesis and say, when you flip that beer cap, it's not 50% chance of getting red. Even though the fraction was pretty close to 50%, it's far enough away and we had enough data that we can say, no, p is not equal to 50%. So in this way, we're able to test hypotheses for proportions or probabilities by rewriting the equation and computing the p-value. In this way, we know when to reject the null hypothesis and when we can't reject the null hypothesis. This allows us to form sound statistical conclusions about probabilities and proportions. So now we know how to test hypotheses and compute p-values when we're talking about a probability or a proportion for something. What if we wanted to do inference about mean values? Well, it turns out we can still do hypothesis tests, and it's really not much harder. For an example to start off, let's remember that data about the patients who had undergone plastic surgery and whether or not that made them look younger. We had data for each patient showing how many years, on average, people seem to think it made them look younger. Now we can say, well, does that mean that for patients everywhere, on average, it's going to make them look younger? Or were these patients just a little bit lucky? So to set this up as a hypothesis test, let's remember the data that we had. In this case, we had n equals 60 different observations of people, and for each one, we had the number of years that they seemed to look younger. Now, if we took the average of those 60 different observations and called it x bar, then x bar was equal to about 7.177 years. And the corresponding estimate of standard deviation, S, was equal to about 2.948 years. So if we want to set this up as a hypothesis test, we can say that in the theoretical world, we have the true mean number of years that this plastic surgery makes you look younger, and we'll call that mu, and that's unknown. Then we also have the estimated number of years that it makes you look younger, and that's our x bar, which is 7.177 years. Now we would like to test whether or not mu is more than 0. So we have a null hypothesis that says mu equals 0, and an alternative hypothesis that says mu is more than 0. To turn this into a hypothesis test, we need to recall something that we learned previously, that in the theoretical world, according to H0, if we look at x bar minus mu and divide it all by the square root of s squared over n, then that has a distribution which isn't quite a standard normal, but is a t distribution with n minus 1 degrees of freedom, or in this case, 59 different degrees of freedom. So how can we use that? Well, in the theoretical world under H0, where mu equals 0, what we've observed as x bar minus mu is just 7.177. So this means that the p-value should be the probability of observing such an extreme value under the null hypothesis. Well, we compute the probability that x bar minus mu is at least as big as 7.177. Well, we can again manipulate both sides by dividing by the square root of s squared over n. And now we've got a quantity which we know its distribution is this t sub 59, And the question is, what's the probability that that is bigger than or equal to, in this case, 18.86? Well, that's something that, again, you can look up in a table or get the computer to compute for you. And it works out to a tiny number, about 1 chance in a 1 followed by 26 different zeros. Unimaginably small. So we can say in this case, of course, we reject the null hypothesis, and we definitely say that this plastic surgery did indeed make people look younger on average. For another example, let's go back to our old friends, the skeletons, once again. Now, remember with the skeletons, we had the age difference between their estimated age and their true age. We had this observation for 400 different skeletons. And in that case, out of these different observations, we computed that X bar, the sample average of the difference between the estimated minus the actual age, was equal to 14.15 years. And the corresponding estimate of standard deviation, S, was equal to 14.13 years. It's just a coincidence that those two numbers are so similar. That doesn't mean anything. In this case, we're just trying to figure out whether this mean is something that's different from 0. So it means we want to use a two-sided test. And our null hypothesis should be, in this case, that mu is equal to 0. That is, that on average, there's no difference between the estimated age and the actual age for these skeletons. Our alternative hypothesis is just that mu is some number which is different from 0. Again, we don't want to specify now whether it's bigger than 0 or less than 0. We're just testing whether or not mu is equal to 0 or equal to some other value. Now, in the theoretical world, we know that x bar minus mu divided by the square root of s squared over n has approximately a t-distribution with n minus 1 degrees of freedom. In this case, n is 400, so n minus 1 is 399. So that means that if we want to compute a p-value, then we want to compute the probability under the null hypothesis of observing, in absolute value now, because it's a two-sided test, a value which is that extreme or more extreme for the difference between mu and x bar. Well, we can compute the probability that x bar minus mu in absolute value is bigger than or equal to the observed value, which is the absolute value of minus 14.15. Well, we can use our old trick. We divide both sides by the square root of s squared over n, and we eventually say it's the same as the probability that the absolute value of the t sub 399 distribution is bigger than or equal to 20.03. Now, one trick is the probability that an absolute value of something like a t-distribution is bigger than or equal to some value is just twice the probability that the value is less than or equal to the negative of it. Because, again, the absolute value can be bigger if either the value is bigger or the value is smaller than the minus of it. So it's 2 times the probability that a t-distribution with 399 degrees of freedom will be at least as small as minus 20.03. And you can work that out. It again works out to be an unimaginably small number. In this case, something like 1 over 3 followed by 61 zeros, just unimaginably small. So in this case, we can say again that we reject the null hypothesis and we say, no, it's not true that those skeletons stay the same on average. In fact, those skeletons, on average, the estimated age is, well, in this case, actually smaller than the true age. But in any case, we can say that the estimated age minus the true age is not equal to 0 on average. So let's do one more example. In this one, let's remember Allison's data about people's true body temperature. And remember, there's a long-held belief that, well, the average true human normal body temperature is equal to 37 degrees Celsius or 98.6 degrees Fahrenheit. But some people have wondered whether that's true. And remember, they did an experiment where they got 130 different people and they measured the temperature of each one. And they got different values like 36.67 and 37.22 and so on. And these were different values of the temperature of these different subjects. And then they said, well, does this confirm or deny the possibility that the true average human body temperature is equal to 37 degrees? Well, to set this up as an experiment, we can say that the null hypothesis now is that the true normal human body temperature, mu, is equal to 37 degrees. And the alternative hypothesis is that it's something else besides 37 degrees. Now in this case, we don't have any prior knowledge of whether it's more or less, so again we'll do a two-sided test. So in the theoretical world, again assuming the null hypothesis, we can say that, well, x bar minus mu over the square root of s squared over n should have a t-distribution with n minus 1 degrees of freedom, or 129 degrees of freedom. So what does that mean? It means that the p-value should be computed by saying, what's the probability that the actual difference in absolute value of x bar minus mu is at least as big as the observed difference, which in this case was 36.80513 minus 37, which is about minus 0.19487. It's a rather small difference, but what's the probability we would observe at least that large a difference, assuming h0? Well, again, we know how to work this out. We start by dividing both sides by the square root of s squared over n and rearrange so we eventually get it to be the same as the probability that the absolute value of something with a t-distribution with 129 different degrees of freedom is bigger than or equal to, well, in this case it works out to 5.455. And again, that should be twice as much as the probability that the t-distribution is less than or equal to minus 5.455. And again, this is something we can look up in a table or get the computer to compute for us. And we find out again, it's extremely small. It's about 1 chance in 4 million. So once again, we can reject the null hypothesis and say, no, it's just not true that the average normal human body temperature is equal to 37 degrees Celsius. It seems like it's close, but it's a little bit less than 37 degrees. So in this way, we can do hypothesis tests and compute p-values even when we're talking about a mean or an average value. And once again, we can decide when to reject the null hypothesis and when to accept the null hypothesis. And we can decide whether or not the mean values are bigger than or smaller than or equal to certain values.
When carrying out a statistical test about their data, it is often the case that researchers would like to show that the alternative hypothesis is true. That is, they'd like to reject the null hypothesis, which is typically the status quo or that nothing is going on, in order to show that there is something going on. Perhaps there's a difference between two groups, or maybe the mean body temperature is not the established value that people have been working with for a number of years. Or perhaps when flipping a beer cap, it's different than a coin in that it's not equally likely to come up one side or the other. If a study is well designed, there will be a high probability of making that decision. That is, rejecting the null hypothesis when, indeed, it isn't true. And such a test is said to have high power. In this video, we'll discuss more about the concept of power and the possibilities that a statistical test may result in an incorrect conclusion. When carrying out a statistical test, the first step is to define our hypotheses. For this video, we'll assume that our null hypothesis is that some parameter from the theoretical world, whether it's the probability of heads or the mean of a distribution of, say, body temperatures, is equal to some value. We'll call it our hypothesized value. And our alternative hypothesis is that the parameter is not this hypothesized value, and depending on the situation, we can use a one-sided, a greater than or less than alternative, or a not equal to, a two-sided alternative. Typically, the two-sided alternative is what we would use. We then calculate a test statistic from our data under the assumption that the null hypothesis is true. Assuming the null hypothesis is true, the p-value is the probability of observing the value of the test statistic that we got, or a value more extreme. And small p-values give evidence against the null hypothesis. Sometimes people talk about the significance level of a test. The significance level gives a cutoff for how small is small for a p-value, and it's typically denoted by alpha. Although in practice it's not always necessary to define in advance a significance level or some strict cutoff, it will help in the discussion of the concepts in this video. If we have a significance level alpha, the p-value is then the smallest level of alpha at which the data are statistically significant. And sometimes the p-value is thus called the observed level of significance. To go back to our legal analogy for a second, You can think of the significance level as the definition of reasonable doubt when we want to ensure guilt beyond a reasonable doubt. In a statistical test, the researcher typically wants to show the null hypothesis is not true and the alternative is true. Something interesting is going on. In order to have high probability of that happening, the researcher needs high power. Since the significance level is our cutoff for how small our p-value is in order to declare a test statistically significant, it also gives us a measure of how the test performs in repeated sampling. If we did the same testing situation over and over and over again, repeatedly collecting a different sample of data and calculating a new test statistic and p-value, and then we did it again and again and again, sometimes we'd get weird or unusual data. Even if the null hypothesis is true, the data could be quite different from it. Suppose you use a significance level of 1%. Then in these repeated samples of data and repeated statistical tests, 1% of the time you'd get weird enough data that you'd get a p-value that's less than 1%, less than the significance level, and you'd reject the null hypothesis, which would be a wrong conclusion. The good news is that 99% of the time you would not reject the null hypothesis, which would be the right decision. So it sounds like a good idea to set the significance level to be very small, so that you don't mistakenly reject the null hypothesis. The problem is that if you set alpha too small, you'll never reject the null hypothesis, even if the true value is nowhere near what the null hypothesis value says it is. So we want to be able to detect a false null hypothesis. If the null hypothesis is not true, that's the conclusion we want to make. What we need is a high probability that the test will reject H0 when an actual alternative value of the parameter is true. For a fixed significance level and a particular alternative value of the parameter being true, the probability that we reject the null hypothesis is called the power of the test against that alternative. So the power is the probability of making a correct decision when the null hypothesis is false. That is, we correctly reject the null hypothesis. The higher the power of a test, the more sensitive it is in detecting a false null hypothesis. As its name implies, power is a good thing. We'll want power to be high. So, what do we need to do in order to get higher power? We'll investigate this question using the applet. For simplicity, the applet assumes that all distributions of data are normally distributed. The blue normal distribution at the top, labeled the null population, represents our theoretical world model under the assumption that the null hypothesis is true. Here, our hypothesized value of the mean is mu0, which is 100, and is the center of this distribution. To calculate a numerical value for power, we need to do so for a particular value of the alternative, not just say any value greater than 100. Here, that alternative value is called mu1, and we'll start with it equal to 115. Our red normal distribution at the top is the model for this alternative worldview. It is centered at the alternative mean value of 115. Note that both the null and alternative populations have the same spread, and that's quantified by 15, the value of sigma, or standard deviation. We're interested in testing the mean, so we'll keep the standard deviation the same in the null and alternative populations. The shaded blue and red normal distributions at the bottom are our sampling distributions for the mean, x bar, or the average of our sample data. So they're the distributions of what the mean could be when it's calculated from our real-world data. As we saw previously, the sample mean or average is an unbiased estimator, so these distributions are centered at the same values as our theoretical world models. However, these sampling distributions have less spread. Recall that the standard deviation of an average is the standard deviation divided by the square root of the sample size. Here our sample size, n, is 4, square root of 4 is 2, so the standard deviation of these sampling distributions is half what it is for the theoretical world models. For this demonstration, we'll start with a significance level of alpha equal to 0.05. So this is our cutoff for a small p-value. Our alternative here is one-sided, a greater than alternative. So we're testing the null hypothesis that the mean is mu0 and the alternative that the mean is greater than mu0. So that means that alternative values of the test statistic are values out in the right tail of the sampling distribution, assuming that the null hypothesis is true. That is, the blue sampling distribution. The red vertical dashed line shows the cutoff for values of the test statistic for which we'd get a small p-value, less than our alpha of 0.05, and then reject the null hypothesis. We won't reject for values to the left of the dashed line, but we will for any to the right, as they'd result in the small p-value. And that's indicated in the dark blue shaded region. We're looking at the blue sampling distribution corresponding to the null population or null hypothesis theoretical world model because we carry out statistical tests assuming the null hypothesis is true. But in this case, we actually know that the alternative value of 115 is the truth. So we want to reject the null hypothesis, and our power is the probability that we do so. Since the truth is that the mean is 115, to calculate this probability, we use the red sampling distribution for the alternative population, or alternative theoretical model. We still reject H0 if the test statistic is to the right of the vertical bar, and the probability that we correctly reject is shaded in pink. This is more than half the sampling distribution, and the probability works out to be 0.639. So our power, the probability we correctly reject the null hypothesis, is 0.639 for this situation. We can experiment a bit by drawing random samples of data. Clicking Sample randomly selects a sample of size 4, which is our sample size, or the value of n in this case. The sample is selected from the alternative population, since that's what the truth is here. We can see the randomly chosen sample here, and the resulting mean here. And we can see that we've correctly rejected the null hypothesis. Let's do this 9 more times. We've correctly rejected the null hypothesis 5 of the 10 times and failed to reject it incorrectly the other 5 of the 10 times. We expected to reject the null hypothesis 63.9% of the time, since that was our power. We got 50%, which is reasonably close to 63.9% for a sample of only size 10. Now let's see what happens when we change some of these values. What if the alternative value was further away from our hypothesized null value of the mean? Let's change it to 130, so our null value is wrong by a greater amount. Since we're holding everything else constant, we should be more likely to reject the null hypothesis, since the true alternative value is far from it. And indeed, the sampling distributions are quite separated now. So getting a value in the alternative sampling distribution that is greater than the value of the test statistic that would result in a p-value of 0.05 or less is extremely likely. Almost all of the area under the alternative sampling distribution. And the power is calculated to be 0.991, quite high. For comparison, now let's put the alternative back to 115, and we'll change our significance level from 0.05 to 0.1. Our criterion for rejecting H0 is now less strict. We'll reject if the p-value is less than 0.1, 10%, so we'll reject more often. As a result, the probability that we correctly reject the null hypothesis, our power, should be larger. And indeed, it is larger than our original value of 0.639. It's now 0.764. Now let's put alpha back to 0.05, and let's look at the variability. Less variability should give us more precise estimates, and that's good. So let's change sigma from 15 to 10. The distributions may appear to have the same spread, but if you look carefully at the applet, the scale is changed, reflecting the smaller value of sigma. Of course, increased precision is a good thing, and this has increased our power to 0.912. Finally, let's increase our sample size to 25. Our sampling distributions are now much more tightly clustered around the mean, reflecting the smaller amount of variability we have in our estimator of the mean. And as a result, our power goes up. This time it's so high that our program has just rounded it to 1. So to summarize, we've seen 4 different ways we can increase the power, the probability that we correctly reject the null hypothesis. The first is having a null value that's further away from the alternative. Now, in practice, this is hard to do. We wouldn't know the true value, and we want to be motivated by a null value that is scientifically interesting. So knowing this fact isn't really too useful in practice, although it is good to know that we have larger power, that is a larger probability of rejecting a null hypothesis when we should because it's wrong by a lot. We can also increase power by increasing the significance level, alpha. So then we reject more often for larger p-values. However, there are consequences to doing this, as we'll see in a couple of minutes. Reducing the variability also gives higher power. Getting more precise measurements, perhaps by controlling for other sources of variation, is always good for helping us to make strong conclusions, and it increases power. And finally, we can get more power by increasing the sample size. When planning studies, the necessary sample size is determined by choosing a significance level and the desired power, and then determining how many observations are necessary in order to achieve that desired power for a particular difference between the null hypothesis and the alternative that is of scientific interest. Power is the probability that we make a right decision, in particular that we reject the null hypothesis when we should, because a value from the alternative hypothesis is the truth. If we think about statistical testing as making a decision, it's possible that we could make the wrong one. There are two types of errors we can make: incorrectly rejecting or incorrectly not rejecting the null hypothesis. These are called type 1 and type 2 errors. Not very creative names, but widely used. We make a type 1 error if we reject the null hypothesis, but it is actually true. This happens because, by chance, we happen to get data that are unlikely, so they appear to be inconsistent with the null hypothesis. If we're using a fixed significance level alpha, that is, a fixed cutoff for how small our p-value needs to be to reject the null hypothesis, the probability that we get data unusual enough to wrongly reject the null hypothesis is alpha. Suppose alpha is 5%, and we carry out 100 statistical tests, and the null hypothesis was true for all of them. We'd still expect to get some significant results, that is, get p-values that are less than 0.05, and thus we'd reject the null hypothesis, and we expect that to happen for 5 of these 100 tests. Unfortunately, for any given data and test with a statistically significant outcome, we can't tell if it's one of the 5% or not. But for any test, we have to be prepared that we could make this error. Going back to our courtroom analogy, a type 1 error, rejecting the null hypothesis when in fact it is true, is analogous to an innocent person being falsely convicted. A type 2 error happens when the null hypothesis is not true, but we fail to reject it. This is related to power, the probability we correctly reject the null hypothesis when it is not true. Indeed, the probability of a type 2 error is 1 minus the power. We denote the probability of a type 2 error by the Greek letter beta. A type 2 error typically happens because we don't have enough power, which typically happens because the sample size is too small to be able to detect the difference between the true value and what our null hypothesis says. In our courtroom analogy, failing to reject the null hypothesis means we can't say the defendant is guilty beyond a reasonable doubt. So the verdict would be not guilty, and a type 2 error would be that a criminal was freed. In practice, of course, we'd like to have low probability of both type 1 and type 2 errors. But lowering the probability of one type of error, generally speaking, increases the probability of the other type of error. Increasing the sample size can decrease the probability of both types of error. This is analogous to having more evidence in a criminal trial, leading us to be more likely to make the correct verdict. But it is often a balancing act between the two types of error, and which is more serious can depend on the context. A medical analogy can illustrate this point. Suppose we have a diagnostic medical test for determining whether a patient has a disease or not. The null hypothesis will be that the patient doesn't have the disease, and the alternative will be that the patient does have the disease. Then a type 1 error would occur if the test says that the patient has the disease, that is, rejects the null hypothesis, when in fact the patient doesn't have the disease. This would have probability alpha. A type 2 error would be not rejecting the null hypothesis, that is, the test saying the patient doesn't have the disease, when in fact he or she does, and this would have probability beta. If decreasing alpha increases beta, and vice versa, it's necessary to decide which type of error has more serious consequences, so that you can sacrifice making one type of error in order to lessen the chances of making the more serious error. But which type of error is more serious? If the disease is treatable and the patient will die without the treatment, then a type 2 error would be more serious, as an incorrectly diagnosed ill patient would miss out on the treatment. But if the treatment had its own serious side effects and the disease wasn't fatal, a type 1 error might be more serious. In medicine, all tests have associated false positive and false negative rates, with a trade-off between the two. And how to manage that trade-off needs to be determined based on the consequences for the patients. The same is true of statistical tests, where we have to consider the implications of making a wrong decision. If choosing to reject the null hypothesis, which is typically the status quo, will incur a great deal of expense, then we won't want to do that unnecessarily, so we won't want to make a type 1 error, and we'll insist on having a very small p-value, very strong evidence against the null hypothesis, before we're willing to reject it. In the next video, we'll consider some more advice about carrying out statistical tests in practice. We've now seen a number of situations where we can use statistical tests in order to help us draw conclusions about our data. Some of the results of these tests have been quite important. For example, we were able to show that we have strong evidence that the mean body temperature is not 37 degrees Celsius, which was a result that held for more than 100 years. But any powerful tool must be used responsibly. In this video, we'll talk about potential pitfalls that can occur when working with statistical tests of hypotheses, and how you might avoid them. Here's our first piece of advice. Be careful not to misinterpret p-values. Okay, that might seem pretty obvious, but it's incredible how often it's done. Remember from a previous lecture, what a p-value does not tell you is how likely it is that the null hypothesis is true. But that's a very common misinterpretation. As an example, when we were comparing the mean body temperatures to the established value of 37 degrees, the p-value doesn't tell us how likely the mean body temperature is to be 37 degrees. What it does tell us is how likely it would be to get the observed data that we got if it really was 37 degrees, and then we can assess whether our null hypothesis is a reasonable assumption. Remember that a p-value is a measure of the strength of the evidence. That's pretty valuable, so report the p-value. That might seem obvious too, and it's kind of old-fashioned, but you'll often see reporting that says there was a statistically significant difference, p is less than 0.05. Well, having a p-value smaller than 0.05 is interesting, but just how much smaller than 0.05 was it so that we can actually assess the strength of the evidence? Saying it's 0.03 is good. Then we know that the evidence is only moderate. Our second piece of advice is that data collection matters. No sophisticated testing can correct fundamental flaws in the data collection process. If the sample wasn't randomly chosen, or we haven't controlled what we could, or we haven't randomly assigned treatments to subjects, then we can expect to have bias, confounding, and we won't be able to make causal conclusions. Our next piece of advice, always use two-sided tests. Okay, not always, but unless you're really sure a priori that you're only interested in one direction and that other direction is of no interest whatsoever, then you should use a two-sided test. Here's why. Imagine we're testing a mean. So let's say our null hypothesis is that the mean mu is equal to some value. We'll call it mu star. And we calculate our test statistic, and we get some value. We'll call it t star. In the one-sided case, suppose the alternative is that mu is greater than mu star. Our p-value is this shaded area, the probability of getting a value more extreme than what we got, which in this case is greater than what we got. For the two-sided alternative, where mu is not equal to mu star, more extreme than what we got includes both tails of the distribution, both the values that are bigger than t star and the values that are less than negative t star, since both are more extreme than what we got. So as a result, the p-value for the one-sided test is only half the p-value of the two-sided test. So for the one-sided test, we're more likely to get a significant result. Would that significant result be meaningful? Not if we really should be doing a two-sided test. Taking a look at your data and seeing whether it's larger or smaller than what you expect, and then deciding whether you should do a one-sided or a two-sided test is cheating. Next, statistical significance is not the same thing as practical significance. What that means is that just because we see a statistically significant result doesn't mean that it's meaningful in a practical way. To illustrate this, let's look again at the example of flipping a beer cap. We're interested in whether or not the beer cap comes up 50% reds. Imagine these three sets of data. We got 6 reds and 10 flips, that's our first set. In our second set, we got 58 reds and 100 flips. And our third set of data, what we actually got, 576 reds and 1,000 flips. If we calculate the test statistic for each of these, we get 0.63 for the first data set. That's a reasonably likely value from a normal distribution. We get 1.6 for the second set, also a reasonable value near the center of a normal distribution. For our third data set with 1,000 flips, we get 4.81. By our empirical rule, 99.7% of the data is within 3 standard deviations of the mean. That means within +3 to -3 on a standard normal curve. 4.81 has to be way out in the tail and a very unusual value. But effectively, our data were all the same or very similar. Each of the data sets had very close to 60% reds. So why are these test statistics so different? Well, don't forget that the test statistic has n, the sample size, in it, and that can make a big difference. When we calculate the p-values, we get a large p-value for data set 1, a reasonably large value for data set 2, certainly not small enough to reject the null hypothesis. But for data set 3, we get an extremely small p-value, so we have extremely strong evidence that the proportion of times a beer cap comes up red is not 50%. What this example illustrates is that very small effects can be highly statistically significant when a test is based on a large sample. But that doesn't mean it's practically important. We have to make that decision based on the context. To flip that around, lack of significance doesn't necessarily imply that the null hypothesis is true. We could get a test with a large p-value, so it's not significant because the sample size is too small, or maybe there's just too much variability in the data to be able to detect a difference. So maybe we just don't have enough power. In addition to possibly not being associated with a practically meaningful result, remember that small p-values can happen for a number of reasons. They can happen by chance. They can happen because there were problems related to the data collection. For example, there could have been lack of randomization. They can occur because there were violations of the assumptions underlying the particular test of significance we're using. Or they can happen because the null hypothesis is false. Typically, with a small p-value, we conclude that the null hypothesis is false, but we need to be careful that none of these other reasons are why we got a small p-value. When dealing with data, there is always variability in the associated uncertainty, and it is important to understand both the strengths and limitations of statistical procedures. Because by chance, every now and then unusual data will be observed, we can get a significant result in a hypothesis test, even when the null hypothesis is true. And if multiple tests are carried out, we expect that some of them will be this unusual case. Suppose we have a significance level of 0.05. Then we'll reject the null hypothesis anytime we see a p-value that is less than 0.05. What that means is 5% of the time when the null hypothesis is true, we'll get data that are unlikely enough to reject the null hypothesis. So be suspicious when you see a few significant results when many tests have been carried out. For example, if there's no significant result for the entire group being studied, it may be tempting to think of ways to divide the observational units into subgroups and see if there's a significant result in any of those subgroups. But in a test repeated on each of 20 subgroups, one would be expected to have a significant result, a p-value less than 0.05. That's not an interesting result, that's just what we expect. Related to this is the concept of data snooping. Here's what you shouldn't do. Take a look at your data, notice two groups differ, and then say, I think I'll carry out an hypothesis test to see if they do differ. Such a test is much more likely to be significant than if you were guided by a scientific question rather than the data. The primary hypotheses to be investigated should be specified before any data are collected, not suggested by the data, because otherwise the p-value isn't meaningful. For the tests for proportions and means that we've learned, we require the following conditions to be true. First of all observations must be independent of each other, and we need the sampling distribution of the estimator of the proportion or mean to be at least approximately normally distributed. We say that any statistical procedure is robust if it is not sensitive to the violations in its necessary conditions. For our test, there's no way to get around independence. Our observations must be independent of each other. But the sampling distributions of p hat and x bar, our estimators of proportions and means, are approximately normally distributed by the central limit theorem, which tells us that averages have distributions that approximate the normal distribution for large sample sizes. So how large of a sample size do we need for a test? It's hard to make general rules, but here are some ideas to keep in mind. We'll talk about proportions first. Proportions are discrete. In flipping a coin 100 times, we can only observe proportions of 0 out of 100, or 1 out of 100, or 2 out of 100, and so on. There's only 101 possible values. But the normal distribution is for continuous variables that can take on any value to any decimal place all the way from negative infinity to positive infinity. So because our test relies on the normal approximation for a proportion which is discrete, we typically need larger sample sizes for the central limit theorem to kick in. When the true value of our proportion is 0.5, the sampling distribution of our estimator p hat is symmetric, like the normal distribution. However, when the true value of p is further away from 0.5, say closer to 0 or 1, the sampling distribution of p hat, our estimator, is skewed. Here's, for example, what it would look like for p equal 0.01. In these more extreme cases, we need larger sample sizes for the central limit theorem to hold. Otherwise, we need to use a different probability distribution for the analysis, and the testing procedure that we have that relies on the central limit theorem won't work well. That is, the p-value won't be correct. Turning to tests of means, for these we have the t-test, and the t-test is remarkably robust. It gives p-values that are very close to correct, even for distributions of data that aren't symmetric and bell-shaped. So t-tests are useful even for small sample sizes, except when our data are very skewed or there are extreme outliers, which are both cases when the mean may not be the best choice for a representative measure of the data. Statistical tests should always be preceded by plots and summary statistics, which may indicate any problems with the data, perhaps there are skew or outliers, and illustrate any effect that you are seeking. If you can't visualize something in a plot, you may wonder if it's practically important, even if it's statistically significant. Well, some statisticians are working on very sophisticated procedures. Fundamentally, testing can't correct flaws in the data collection design, so be careful when collecting the data to avoid bias and confounding and the inability to generalize and other consequences of lack of randomization. It's easy to put data into a statistical software package and generate p-values. It's much harder to truly understand them and to assess if they really answer the question you want. But statistical testing works well if you design a study carefully to investigate focused questions and then use tests to assess the evidence for or against your hypotheses.
Hypothesis testing for proportions, our tutorial. With the introduction of hypothesis testing, we now have a new statistical tool in our tool belt. Allison introduced the main idea behind hypothesis testing, and Jeff showed a few examples of how hypothesis tests can be used for proportions. The first example Jeff walked through was the results of a poll on the proportion of supporters for the Mayor of Toronto, Rob Ford. Here's the formula for the test statistic, and we can calculate it using R to obtain negative 5.17. For the p-value, we would like the probability below this test statistic, which we can obtain with the command pnorm. We could also use the binom.test command from the binom package, which we have previously installed. The binom.test command requires that we have the number of successes rather than the proportion. So if we know that 42% of respondents support the mayor, then we know the count must be 0.42 times 1046. Rounded to the nearest integer, that would mean approximately 439 of the respondents. In the binom.test command, we will enter x, the number of successes, 1046, the total sample size, and we will state our null hypothesized proportion of 0.5, and that the alternative hypothesis is p less than 0.5. Let's go through the output one line at a time. First, we can see that we have 439 number of successes in 1046 total number of trials. This yields a p-value of 1.144 times 10 to the power of negative 7. That is 0.0000001144. From the guidelines you've seen in the lecture, this p-value is extremely low, which will lead us to reject the null hypothesis. It provides very strong evidence for the alternative hypothesis, that the true proportion of successes is less than 0.5. In other words, we have very strong evidence that the true support for Mayor Rob Ford is less than half. Do note that the binom.test does not provide the test statistic, just the result. We can also see a reported 95% confidence interval, but be careful because this confidence interval is a one-sided confidence interval, which we will not focus on. And lastly, we see the sample estimate for the probability of success p-hat, which we started with. For an example of a two-sided test, we can recreate the results of Jeff's beer cap experiment. With 576 successes, or reds, in 1,000 total trials, we again obtain a very small p-value, so we can reject the null hypothesis and conclude with strong evidence that the true proportion of red is not equal to 0.5, or that the two sides, red and silver, are not equally likely to come up on a beer cap. Hypothesis testing for means, our tutorial. In the lecture today, you saw Jeff extend the idea of hypothesis testing and apply it to the mean or average value of a measured quantitative variable. Let's see how we can use R to test a hypothesis about a population mean mu. We'll begin with Jeff's example of the plastic surgery patients and their perceived age change. We'll read in the data and set change equal to the first column V1 in the dataset. To calculate the test statistic using R, we will need the mean age change, x bar, the variance, s squared, and the sample size, n. We will enter our calculated statistics into the formula. We have x bar minus the null hypothesized mean, 0, divided by the square root of s squared over n, and we obtain a test statistic of 18.86. Now the p-value is the probability above 18.86 from the t-distribution with n-1 degrees of freedom. We can use the pt command, inputting our test statistic value t, the degrees of freedom n-1, and since we would like the probability above the test statistic, we will specify lower.tail equals to false. We can see that with such a small p-value, we can reject a null hypothesis. We have very strong evidence to suggest that on average, people looked younger after the plastic surgery. For an example on a two-sided test, let's look at the body temperature dataset, and again, the first column is the one we will refer to as temp. R has a built-in function t.test for conducting hypothesis tests for a mean. We will use it on our variable temp, specifying also the null hypothesized mean of 37, and that the alternative hypothesis should be two-sided. In other words, we are testing whether the true mean temperature differs from 37 degrees. We see in the output our test statistic of -5.455, our degrees of freedom 129, and the p-value. Since this p-value is very small, we can reject the null hypothesis and conclude the alternative, that the true mean temperature is not equal to 37 degrees. As part of the output, we also obtain a 95% confidence interval and the sample estimate of the mean, or x-bar. If you wish to change the confidence level for the interval, you could do so with the optional argument conf.level in the t.test command.
So now we know about confidence intervals and we know about hypothesis testing. In this lecture, we're going to consider the connection between them. Now, at first it seems like there really isn't much of a connection because their purpose is pretty different. Hypothesis testing is when we want a yes or no, whether we can reject the null hypothesis that a certain quantity equals a certain value, or we can't reject it. Confidence intervals are about what's a range of plausible values for the quantity. So they're kind of different. And indeed, we've seen, for example, we've done one-sided hypothesis tests and two-sided hypothesis tests, but we've only done two-sided confidence intervals. And also in the next week's lectures, we're going to see that when we have two samples, things get even more complicated and the relationship is even less clear. But despite all that, there is one nice clear connection between two-sided hypothesis tests and two-sided confidence intervals that we're now going to explore. As a first example, let's think one more time about flipping that bottle cap and it comes up either red or silver, and we had some data and we wanted to know the probability that it would come up red. So let's just remember what we said in that case about both the confidence intervals and hypothesis testing. So for the bottle cap, as far as hypothesis testing, we wanted to test the null hypothesis that the probability of getting red was just 0.5 versus the alternative hypothesis that it was some other value besides 0.5. How did we test that? Well, we first recorded our observations, which said we had 1,000 flips and our estimated fraction of the time we got red was 0.576. And in particular, that meant that the difference between the observed fraction and the hypothesized fraction for the null hypothesis was 0.576 minus 0.5, or 0.076. And then we want to know, is that value so large that we can reject the null hypothesis? Well, we said that we would reject the null hypothesis because we computed the p-value, and we said the probability that under the null hypothesis, H0, that you would observe such a big difference between the observed fraction of reds and the hypothesized fraction of reds was, well, we reconverted it to say it's approximately the same by the central limit theorem as the probability that a standard normal is bigger than some value, in this case 4.81. And we computed that that was an extremely small probability, about 1 chance in 650,000, which was much less than a typical significance level like 0.05. So we rejected the null hypothesis. As far as confidence intervals, that was kind of different. We said, well, the confidence interval, at least the 95% confidence interval, would be found by taking, well, our estimated fraction p hat plus or minus something. And in this case, that plus or minus was, first of all, 1.96, that magic critical value for the standard normal distribution, and then multiplied by the standard deviation. In this case, it was the square root of p times 1 minus p over n. And that gave us a certain confidence interval from 0.545 to 0.607. And we notice at that confidence interval, it misses the value 0.5. 0.5 is not in that confidence interval. So what does that mean? Well, there's two different things we can say. One is that we did a hypothesis test for whether 0.5 could be considered a possible value for the probability of getting red, and we said no, we reject that. Then we computed a confidence interval, and we said that confidence interval missed the value 0.5. So we kind of got a similar conclusion in two different ways. Is this just a coincidence? Well, the answer is no. We're going to see that this equivalence happens a lot more generally. For a second example, let's remember that human body temperatures data. So remember there we were testing whether it's true that the normal human body temperature is equal to 37 degrees Celsius, and we were comparing that null hypothesis to the alternative hypothesis that mu is not equal to 37. Now again, this was a two-sided test, and again we had some observations. In this case we had 130 different human observations, and the observed value of the difference between the mean that we got minus 37, our hypothesized value, was this 0.19487, and we also had an estimate for the standard deviation S. And again, we decided to reject the null hypothesis that the true normal body temperature was 37 degrees, and we rejected it because, again, we computed a p-value. In this case, we're saying, what is the probability that the observed value of x bar would differ from the hypothesized value, in this case 37 degrees, by as much as it did in our own observations? And we said, well, in this case, remember when we rewrote and divided things, we converted it to something involving a t-distribution with 129 different degrees of freedom. And we said it works out to be the same as the probability that that is bigger than 5.455. And again, we computed that was extremely small. That was like 1 chance in 4 million, which was much less than a typical significance level like 0.05. So we rejected that and we said, no, the normal human body temperature is not equal to 37 degrees Celsius. We also could compute a confidence interval in that case. And in this case, it's a confidence interval for a mean, and we know how to do that. It's our observed mean plus or minus a certain value, which, well, for the normal, it was 1.96. In this case, because it's a t-distribution, it's a little bit larger. It's 1.979. And again, times the square root of the observed standard deviation squared divided by n. And that works out to a certain interval shown here, which, again, misses the value 37 degrees. So again, we can say that in this case, we could either consider 37 degrees to be a null hypothesis and we reject it, or we could say, let's look at the confidence interval, and the confidence interval misses 37 degrees. Again, is that a coincidence? Well, no. So now let's talk about the more general theory and be a little bit more abstract or general for a minute here. And so we can say, well, in general, if we had some hypothesis test, and let's do it for means, although it's pretty similar for proportions, we'd say, well, we're testing, say, a two-sided test. We're testing that it equals some value mu naught, whether it's 0.5 or whether it's 37 degrees or whatever, compared to the alternative that is not equal. In this case, well, we get some observations, some number n of observations, and some observed mean value x bar, and some observed standard deviation s. And we'd also get the difference. I'll call it d for now for clarity. So d is the difference between the observed mean compared to the hypothesized mean according to the null hypothesis. So then we're going to reject the null hypothesis, H0, if the probability that the sample mean x bar would differ from the hypothesized value mu0 by more than the value d, more than the difference that we got. We'll reject it if that probability is less than or equal to alpha, whatever our significance level alpha is. Alpha might be equal to 0.05, let's say. And, well, we know that's the same as looking at, once we divide and so on, the probability that this difference divided by the square root of s squared over n is bigger than or equal to the corresponding value for what we observed. And then we say, well, that quantity on the left is approximately a t-distribution with n minus 1 degrees of freedom. And we want to know whether the probability that that is bigger than this value, d over square root of s squared over n, whether that probability is less than or equal to alpha. So that's the rule for rejecting according to the null hypothesis. Another way to think about it, which will make the connection to confidence intervals more clear, is to say, well, this will only happen if that amount of difference that we're saying is the probability that t is bigger than or equal to that in absolute value is less than or equal to alpha, if that difference is bigger than or equal to a critical value. So I'm going to write capital T now for a critical value, and this is the critical value which says that a t distribution with n minus 1 degrees of freedom in absolute value, the probability is bigger than or equal to that critical value is equal to alpha. So this is a critical value, and again, that's the thing that played the role of like 1.96 or whatever in our previous calculations. And you can think of it as saying, well, this is the value where we'd be right on the edge of rejecting the null hypothesis or not. If the observed difference is more than this critical value, then we'll reject it. If the observed difference is less than this critical value, then we won't reject it. But on the other hand, if we consider confidence intervals, well, a 1 minus alpha confidence interval, so if alpha is 0.05, that's a 95% confidence interval. Well, for mu, well, it's our observed x bar plus or minus what? Well, that critical value, like 1.96 or whatever, times the square root of s squared over n. That's our formula that we had before. So when will that miss mu 0, our hypothesized null value? Well, it will miss it if the observed difference, x bar minus mu naught, is bigger than or equal to this critical value times this square root of s squared over n. But if you think about it, that's exactly equivalent. It's the same thing, because if the confidence interval misses this value, so it means that this absolute difference is bigger than or equal to this value, well, that's exactly the same as saying that the probability that the p-value for the null hypothesis would be less than or equal to alpha. So we would then reject it. So in other words, it turns out, and if you didn't follow all this algebra, that's okay. It's just making a general statement related to what we already saw in the examples, that if you're just considering a single sample like we are so far, and if you're considering a two-sided test versus a two-sided confidence interval, then it turns out to be exactly the same thing at whatever significance level like alpha, if you say that you will reject the null hypothesis, or if you say that the corresponding confidence interval does not include the null hypothesis value. So in this way, we see that there are actually some connections. There's still kind of different ways of thinking. A hypothesis test is deciding yes or no whether or not we're going to reject a value. The confidence interval is giving a range of plausible values, but they have this connection that the range of plausible values will include a certain particular value if and only if that particular value would have been rejected by the corresponding hypothesis test. So this is a way to think about these two different subjects as being in a way kind of the same.
Up until now, we've learned inferential procedures, that is, tests and confidence intervals, for what we'd call the one-sample case. That is, we've been interested in a single proportion, such as the percentage of people who support the mayor, or a single mean, such as the mean body temperature for healthy adults. However, many questions that we might want to study require us to have two sets of data, or to look at the same measurement taken under two different conditions. So now we're going to look at expanding our statistical toolbox to include tests and confidence intervals to see if two measurements or two groups differ. We're going to go back now to our anthropology data and measurements on 400 skeletons, in particular estimates at age of death and how those estimates differ from actual age at death. We've looked at the estimates given by the Deganji method, in which age estimates were made by examining the first rib. Previously, we learned that the Deganji method tends to underestimate the age of death, with the errors in age estimation negative for more than 75% of the observations. As we can see by the third quartile, which is negative, and we can see that our average or mean error of age estimation is negative 14 years. So on average, the Deganji method underestimates the age of death by more than 14 years. When we first introduced this data set, we also discussed the Suchi-Brooks method. This method estimates the age from the pubic bone, a weight-bearing part of the body, so it may perform differently than the Deganji method. Looking at some summary statistics in the box plot for the error in age estimation from the Suchi-Brooks method, we can also see that it tends to underestimate, with a third quartile of 0, so 75% of our observations are 0 or less, at an average estimated error in age estimation of more than 7 years. So both methods underestimate the actual age. But maybe the Suchy-Brooke method performs a little better. If we look at the box plots for the two methods side by side, we can see that the values for the Suchy-Brooks method seem a little closer to 0, which is what we'd get if the actual and estimated age were the same. But there's a lot of overlap in these box plots. So you may wonder, is the difference between the two methods significant? Before answering that question, there is something fundamentally wrong with the representation in these box plots. The estimates by each method were taken on the same skeletons. But we don't know this from the plot, in which we can't tell how the measurements on each skeleton coincide. For example, our largest underestimate using the Deganji method was a whopping 60 years below the actual age. Using the Suchy-Brooks method, the largest underestimate was only 36 years. But are these even the same skeleton? Because these side-by-side box plots don't match up measurements on the same skeleton, this isn't the best representation of our data. This is an example of matched pairs. Matched pairs is useful when we want to compare two conditions or treatments or methods, and we are able to compare them on the same observational or experimental unit, or on two very similar matched units. This could be the same subject or skeleton, or perhaps something like twins or siblings. Some examples of matched pairs include, of course, comparing two methods on the same skeleton. Another common example is pre- and post-test scores. For example, I could test you on your statistical knowledge before the course, and then at the end to test the effectiveness of the course. Sometimes we can design a study to compare matched measurements taken at the same time or place. For example, if we wanted to compare sales in two branches of a store, we could measure sales in each branch on the same weeks, so then the sales are matched by week. Or in an experiment with two treatments, we could first give each experimental unit one treatment and then the other treatment for comparison. Such an experiment is called a crossover study. In a crossover study, we don't randomize treatments to experimental units, since each unit gets each treatment, but we do randomly determine the order each unit gets the treatments, in case the effect of one treatment might be affected by the treatment that precedes it. Matched pairs is a form of control. We are controlling for all the variables that naturally vary among independent subjects or experimental units or observational units by making our comparisons within these subjects or units. As a result, there is less variability or greater precision, and thus more power in our tests and narrower confidence intervals, in our estimate of the difference between the treatments or conditions being compared. Up to now, our inferential methods have assumed that all our observations are independent. Matched pairs aren't. If they were, we wouldn't get the greater precision that we're looking for in our comparisons. So we have to take that into account in our analyses. So, how are we going to carry out the analysis to compare the Deganji and Suchy-Brooks methods? The general approach is to treat each pair as one observation, and then they'd all be independent, since each skeleton is independent. For each skeleton, we calculate the difference in the error in age estimation between the Suchy-Brooks and the Deganji methods, and then we carry out the analysis on these differences. That's one measurement per skeleton, and we already know methods for one measurement. And in particular, comparing the means of these two methods will become looking at the mean of the differences. Before we proceed, there's one small item I need to point out about these data. For two of the observations, the Suchy-Brooke estimate is missing. Different statistical packages use different symbols for missing data. In R, the symbol is NA. I originally chose the sample of 400 skeletons that we've been working with in order to have a Deganji estimate for each, so the skeletons all had their first rib intact. But that doesn't mean that all other bones were intact, and indeed 2 of our 400 skeletons had damaged or missing pubic bones, so a Suchy-Brooks estimate wasn't possible. But we don't expect that a missing bone is related to age at death or its estimate, or sex or BMI if we analyze that. So we don't expect that leaving out missing observations will bias the results, So we'll continue with the 398 skeletons, for which we have both estimates for both methods so that we can compare them. Let's take a quick look at these 398 differences. From the plots, we can see that their distribution is fairly symmetric, and it's centered above 0. Indeed, the average difference is 6.854. So the difference in the error in the two methods is, on average, almost 7 years. Since both methods tend to underestimate age at death, so their errors are negative, and in this case we're subtracting the de Ganji errors from the Sachi-Brooks errors, a positive mean is an indication of higher error estimates in the Sachi-Brooks method, which means that they're closer to 0 on average. So it seems we have an indication that the Sachi-Brooks method is more accurate. One more statistic to note from these differences, the standard deviation of them is about 11 years. Let's call the difference between the error in age estimation between the Sachi-Brooks and de Ganji methods D. To test whether the mean error in age estimation differs between these two methods, we'll specify our null hypothesis that there is no difference, or that mu d, the mean of the differences, is 0. And we'll test that against the two-sided alternative of some difference between the mean of the methods, so the mean of the difference is not 0. The statistics we'll need from our data are the average of the differences, which is 6.854, and the standard deviation calculated from the 398 differences, which is just over 11. As we've already seen for a one-sample test of the mean, our test statistic is the sample average, standardized by centering around our null hypothesis value, in this case 0, and dividing by the standard deviation of the mean, which is the standard deviation divided by the square root of n, and this gives us approximately 12.37 for our test statistic. If the null hypothesis is true, this test statistic should be a value from a t-distribution with 397 degrees of freedom. With such a high degree of freedom, this will be quite close to a standard normal distribution. And in a standard normal distribution, we know that 99.7% of the data values are within 3 standard deviations of the mean, or within -3 and +3. So a value greater than 12.37, or more extreme in the other direction, less than -12.37, is very unlikely. And indeed, the p-value in this case has 29 zeros after the decimal place before it gets to a significant digit. So it's very, very small. With such an extremely small p-value, we can conclude that we have extremely strong evidence that the null hypothesis is not true. That is, the mean of the difference between the methods in the errors in age estimation is not 0. So the Sachi-Brooks method and the de Ganji method don't give the same mean error in age estimation. We noted earlier that the average difference between the methods was positive. And this is an indication that the errors in age estimation were closer to 0 for the Sachi-Brooks method. So the Sachi-Brooks method is giving age estimates that are closer to the actual age. Remember that the Sachi-Brooks method uses the pubic bone, a weight-bearing bone, where the de Ganji method uses a rib, a non-weight-bearing bone. So an interesting follow-up question might be to further investigate whether weight-bearing bones give more accurate estimates. Of course, this is an observational study, not an experiment, so we need to be careful not to overstate our conclusions. We can't say anything that implies cause and effect. But we can say that for the set of skeletons that are being examined here, there is strong evidence that the mean error in age estimation is not the same between the two methods. As an estimate of the difference in the error in age estimation between the Sachi-Brooks and the de Ganji methods, we have the sample mean of the differences, which was almost 7 years. Even better would be to include a range of plausible values for what this mean difference could be. And for this, we know how to construct a confidence interval. Suppose we want to be 95% confident that we capture the true mean difference in our interval. Since we have differences for 398 skeletons, we'll need the values from a t-distribution with 397 degrees of freedom, so that the area between them is 0.95 or 95%. These critical values that we need are negative and positive 1.966. And our 95% confidence interval for the mean of the difference is then our sample mean, 6.854, plus or minus this critical value from the t-distribution, 1.966, times the standard deviation of the mean, which is the standard deviation divided by the square root of the sample size. That gives us a 95% confidence interval from about 5.76 to 7.94. So we estimate that the true mean difference in the error in age estimation between the Suchi-Brooks and de Ganji methods is possibly as low as 5.76 or a little under 6 years, and as high as almost 8 years. From our statistical test, we had very strong evidence that the mean of the differences was not 0. And correspondingly, we don't see 0 within this confidence interval. For all of the inferential procedures that we've learned, we need independent data. That is, we need all of the observations to be independent of each other. In matched pairs designs, this isn't the case. Certainly, if we have two measurements on, say, the same skeleton, we expect that those two measurements will be related to each other. However, we can combine them into a single measurement, typically by taking a difference, as we did in this video. And then we have one set of independent observations, as long as the skeletons are independent, which we can analyze using the one-sample procedures that we've already learned.
In previous lectures, we've learned how to study the results of a single sample, whether it's a single poll or a single medical result or a single study of human body temperatures or a single study of those skeletons. We had one sample and we tried to do inferences on it. That could involve getting a confidence interval or could involve doing a hypothesis test, but we always just had one sample to consider. Or most recently, we talked about having paired samples where really we can just look at the difference between everybody's result in the second sample minus the first sample, and then it pretty much reduces to just having one sample. Now we're going to consider the case where we have two independent samples. So we have one sample about a certain result or fact, and then we have a whole other sample. And the question is, what can we do to infer between them in that case? For example, maybe we had one poll of a politician's support at one time, and then a few months later we had a second poll, and we want to make inferences about how the support for that politician has changed. So how can we do that? Well, to start off, let's remember what we did in the one sample case. And in particular, if we just had one proportion with some sample size n, and some observed fraction of successes or support or whatever, which we call p hat, then we knew some theory. We developed using the central limit theorem the idea that p hat minus p approximately had a standard normal distribution, and we knew the mean and we knew the variance. And this was good because we could use this fact to approximately compute confidence intervals and approximately get the p-values for hypothesis tests. So for one sample, we understood all that. Now suppose we have two independent samples, and let's say they're each a proportion, like they're two different polls, but they're done independently, so it's not asking the same people again and seeing how they've changed. It's asking one sample, and then later asking a whole different sample. There's no matching involved. We have two different proportions. So in this case, the first sample might have been of size n1 and the second one of size n2, and they could be different sizes. And in any case, we would probably observe different fractions of successes, a p1 hat and p2 hat. And what we're interested in are things about the difference between p1 and p2. Well, we can just look at the difference between the two samples. That's p1 hat minus p2 hat. And of course, the mean of that will still be p1 minus p2 because the mean of p1 hat is p1 and the mean of p2 hat is p2. So that's good. We already have a statistic which has the right mean. But in order to make progress with things like confidence intervals and hypothesis tests, we need to also know things like the variance. Well, we can work that out too. So in this case, the variance of p1 hat minus p2 hat, well, first of all, that's kind of like a variance of a sum of two things, but then one of them had a minus sign, but that's okay because variances get multiplied by the constant squared. So since they're independent, we can add the variances, and since we get to square it, that minus 1 squared kind of goes away, and we just have a sum of the two individual variances, which is that old formula that we remember for the variance of a proportion, the p times 1 minus p over n. Well, now we've got a sum of two of them. Okay, now if the two samples are reasonably large size, then it's still going to be true that the central limit theorem approximately applies, and we can say this p1 hat minus p2 hat approximately follows a normal distribution, and we know its mean is the true p1 minus p2, and now its variance is the sum of these two different components. Now we can do our old trick again of subtracting off the mean and dividing by the square root of the variance to get a sort of complicated little fraction which approximately has a standard normal distribution. So this is good, and it allows us to maybe again think about confidence intervals and hypotheses tests. So let's start by looking at confidence intervals. Let's recall we know that this complicated little fraction is approximately a standard normal distribution. Now we have our usual problem that the variance here, the variance in the denominator, actually involves these quantities p1 and p2, which are unknown. So for confidence intervals, we can do our usual trick. We'll say, well, we'll approximate p1 by p1 hat and approximate p2 by a p2 hat. And then we can say, well, now we've got a 95% confidence interval just like before. Namely, we want a confidence interval for p1 minus p2. And, well, that's going to be given by p1 hat minus p2 hat plus or minus. And if it's for a 95% confidence interval, then we use 1.96 times the square root of this variance term, which in this case is a little more complicated. It's p1 hat times 1 minus p1 hat over n1 plus p2 hat times 1 minus p2 hat over n2, but it's still just a formula, and it gives us confidence intervals. So let's try a simple example of that. Let's begin by recalling that we were talking a few lectures ago about some poll results for Toronto's mayor, Rob Ford, and there was a poll done in September of 2011 which said that his support had dropped compared to a previous poll. Well, the previous poll was in June of that same year, and here are the results. The number of people surveyed was 1,050 with his support at 57% in the first poll, and was 1,046 with his support at 42% in the second poll. So it certainly seems like there was a drop, but suppose we want to get a confidence interval for how much of a drop there really was. Well, the 95% confidence interval for this difference, his true support at the time of the first poll as compared to his true support at the time of the second poll, is given by the formula that we just developed. So it's the observed difference between the fractions of support plus or minus this 1.96 times this square root of this big complicated variance term. And, well, it works out so the observed difference is 0.15 or 15%. But then plus or minus this uncertainty, which is about 0.042. And when you work it all out, it says that we can be 95% confident that the true amount of support drop that the mayor experienced between these two polling times was between about 10.8% and about 19.2%. So that's our conclusion. We say, yes, his support seems to have dropped by something in this range. For a second example, let's consider two polls that were taken to gauge the voting support of U.S. President Obama just before the 2012 election. So in the first poll, they surveyed 1,010 people, and he was at 52% support. In the second poll, they surveyed just 563 people, and he was at 48% support. So in this case, his support went down a little bit, and the question is, does this mean there was an actual drop in his support, or was it just the luck of the polls that they did? Well, once again, we can compute a 95% confidence interval. And in this case, we can say, well, it's the observed difference, which is 0.52 minus 0.48 or 0.04, plus or minus this 1.96 times the square root of this big complicated variance term. And in this case, it works out to a confidence interval of between about minus 1.2% or positive 9.2%. So in other words, we can't really conclude much of interest. We can say that it's possible that his support actually went up a little bit, or it might have gone down by as much as 9.2%, but we're not really sure, and the situation is a bit unclear. And this leads to the question of whether we can test for whether these differences, like P1 minus P2, really are positive or really are negative or actually could be zero. So let's next think about hypothesis testing. So remember that in hypothesis testing, we want to test some null hypothesis as compared to some alternative hypothesis. In this case, if we're looking to see whether, for example, a politician's support has changed between one poll and the next, well, the hypothesis, the null hypothesis, would be that their true support stays the same, and the alternative hypothesis would be that there's been some change in support. Now remember what we know from general theory. We know that this funny thing, this p1 hat minus p2 hat minus the difference of the two means divided by the square root of this complicated variance formula is approximately a standard normal. Now, as with confidence intervals, we have the problem that p1 and p2 are unknown. But in this case, if we're testing hypotheses and we want to compute probabilities under the null hypothesis, we can use the fact that we're assuming then that p1 equals p2. And in that case, we would approximate both p1 and p2 by their pooled estimate, that is this p hat, which is the total number of successes in both samples divided by the total size of the two samples together. So with this p hat, we use that as an approximation for p1 and for p2 in the formula, and now we say that this other expression is approximately a normal 0, 1. It's just like before, but we've substituted this new value p hat for both p1 and p2. Now we can use that to compute p-values for hypothesis testing. So to go back to the example of the Ford polls, remember we had two polls with different sample sizes n1 and n2, and different observed proportions of successes, p1 hat and p2 hat. Now, the question would be, is there really a drop in his support? Now, the confidence interval that we already computed for p1 minus p2 suggested that it was positive and therefore suggested that there was a drop. But a confidence interval is not quite the same as a hypothesis test, and we don't want to confuse the two, so we want to do a pure hypothesis test now. And we want to test whether p1 equals p2 or whether p1 is not equal to p2. Well, in our observations, we had p1 hat minus p2 hat, of course, was 0.15. So we observed a 15% drop in support. We also compute this pooled value for p hat, which works out to 0.495. And now we can say, well, the p-value should be the probability under the null hypothesis that we would observe a difference in p1 hat minus p2 hat, which was at least as big as the observed difference, which is 0.15, even under H0, which assumes p1 equals p2. Well, that probability, again, by subtracting and dividing and so on, we can rewrite it in terms of something involving the absolute value of approximately a standard normal distribution, and saying, what's the probability that a standard normal distribution is bigger than or equal to this new value? And by the way, we didn't have to worry too much about subtracting p1 minus p2 on the right-hand side, because we're assuming under H0 that equals 0. Anyway, so it works out to saying, what's the probability that the absolute value of a standard normal distribution is bigger than or equal to 6.87? Now, 6.87 is a very extreme value for the standard normal distribution, which we know is usually between -3 and 3. So we can say, well, that's an extremely small p-value, and we can thus reject the null hypothesis. And we can say, no, it's just not true that p1 equaled p2 in this case. It's not true that Mr. Ford's support stayed the same between the two polls. On the contrary, it really did change, and his support really did drop between the times of these two polls. What about the Obama polls? Well, in that case, remember we had two different polls with two different numbers of people sampled and two different observed proportions of the people who supported Obama. And now we can test, is there a drop in support? Well, in this case, again, we have the null hypothesis that p1 equals p2 compared to the alternative that they're not equal. Again, we can compute the observed drop, which is 0.04, and we can compute this pooled value for p hat, which is 0.506, or just over 50%. Then once again, the p-value should be the probability under H0 that we would observe a difference in p1 hat minus p2 hat, which is bigger than the 0.04 that we did observe. Well, again, we can subtract and divide and work through it and end up saying it's the probability that a standard normal distribution is bigger than or equal to 1.52. Well, that's not so unlikely. That works out to about 12.9%. And that's probably bigger than our significance level. So we can say, well, in this case, the p-value isn't too small, so we cannot reject H0. That means it's perfectly plausible that, in fact, Mr. Obama's support didn't change at all between these two polls, and that was just the random fluctuation because of the random sample that they did to get the poll. And that's what we say in this case. For a final example, let's go back to that study of the HPV vaccine and how it affects HPV infections. Remember that they had a large sample of 6,163 young women who'd gotten the HPV vaccine, and they found that only 23 of them got HPV infection. They also had a sample of 6,018 young women who got some other vaccine, and they found that 345 of them got infected. So the question is whether this allows us to conclude that this HPV vaccine is useful, and indeed how much did it affect the infection rate. So let's start by considering confidence intervals. Well, we know the drill now. For the confidence interval, we take the observed difference, which in this case is just 0.004, the fraction who got infected with the HPV vaccine, compared to 0.057 as the fraction who got infected who took the other vaccine. And then we take that plus or minus, well, if we're doing a 95% confidence interval, then it's 1.96 times the square root of this big complicated variance expression, which in this case works out to a confidence interval of between minus 5.9% and minus 4.7%. So this means that P1 minus P2 is negative. In other words, P1 is a fair bit less than P2, and indeed that indicates that the young women who got the HPV vaccine were indeed less likely to get HPV infection, and in fact, the incidence decreased by probably between 4.7% and 5.9%. So that's a very big decrease. We can also think about it in terms of hypothesis testing. And in this case, we'd again want to test the null hypothesis that the true incidence of infection was the same for the two groups compared to the alternative hypothesis that it's different. Well, we still have those same numbers for the number of people in the sample and the observed fraction of infections for the two groups. So we can again compute the difference between the observed fractions. And now for hypothesis testing, we can compute this pooled value p hat, which in this case works out to about 0.030. And then the p-value, as we know, is to compute under the null hypothesis what's the probability that we would observe a value of p1 hat minus p2 hat in absolute value, which is bigger than or equal to the 0.053, which is the absolute value of the difference that we observed. And again, we can subtract and divide by the square root and end up saying it's the same as the probability that the absolute value of a standard normal is bigger than or equal to 17.14. Now, I don't have to tell you at this point that that's an absurdly extreme value for the standard normal, and indeed the p-value that you would be bigger than that is so small it's unimaginable. It's like 7 divided by a 1 followed by 66 zeros. It's just a number that's too small for us to think about. So we certainly reject the null hypothesis, and in this case we can say yes, the HPV vaccine did indeed help in the sense that the true incidence of getting the infection was definitely and unquestionably less for the young women who got the HPV vaccine as opposed to those who got some other vaccine. Now, can we conclude from this that the vaccine actually caused the infection rate to be lower? The answer is yes, we can. Because this was a randomized study, it means that whatever relationship we discover must actually be a causal relationship. The vaccine is what caused the infection rate to be lower. So in this way, we can now understand how to study two different independent samples of proportions. We can compute confidence intervals and hypothesis tests for the difference, the P1 minus P2, even when the two samples are independent. Next, we'll consider how to do the same thing when we're considering means instead of proportions. So now we know how to compare two different proportions. That is, if we have two different independent samples and we want to compute things about the difference of the two probabilities, like confidence intervals and hypothesis tests, then we know how to do that. What about for means? What if we have two different samples of means and we want to compare those means or say things about the difference of those means? Well, we can do it again, and it's pretty similar to the previous case, but it's a little bit trickier, as we'll see. So to start off, let's again remember what we know about one sample. In this case, one sample for a mean. Well, we know that if we have a sample with some size and some x bar and some s squared, then we had this distribution equation that said if you take x bar minus mu and divide by the square root of s squared over n, then that will have approximately a t distribution, and the number of degrees of freedom will be n minus 1. And this is good because it allows us to compute confidence intervals and allows us to do hypothesis tests and so on. What about if we have two independent means? So they're not matched, they're not paired up in any way. We just have two different samples, and we'd like to know something about the difference of the two true means. Well, again, the samples would have different sizes, n1 and n2, and they'd have different values of the sample mean, x bar 1 and x bar 2, and they have different sample variances, s1 squared and s2 squared. And we'd like to be able to say something again about the distribution so that we can compute confidence intervals and do hypothesis tests. Well, here's a fact, and it's what you might hope is true, that if you take the difference of the x bars and subtract the difference of the true means, mu1 minus mu2, and divide by the square root of some sort of a variance, then maybe it still has a t distribution. And it's a fact that approximately it does. This isn't quite true even in the limit of the central limit theorem and normal data, but it's approximately true. And the variance that we divide by on the bottom, well, it's the square root of a variance, and that's kind of what you might expect. It's the sum of the two different variances, the s1 squared over n1 plus s2 squared over n2. So that's good. The most surprising thing here is, what is the number of degrees of freedom, df? Well, turns out to be given by this rather complicated equation here, sometimes called the Welch-Satterthwaite approximation. And anyway, it's some sort of a complicated formula that gives us an approximate number of degrees of freedom to make this quantity approximately have a t distribution. Now, this number of degrees of freedom might not even be an integer, but that's okay. The t distribution can still make sense and can still be computed on a computer, even when the number of degrees of freedom is not an integer. It's something with a decimal point. So we can use this to get confidence intervals and hypothesis tests. So let's start off with confidence intervals. Now remember what we know. We know that we take this difference of the x bars minus the difference of the true means and divide by the square root of these sums of these two different sample variances. Then it has approximately a t distribution with some number of degrees of freedom given by that crazy formula in the previous page. And so then you say, well, can we get a 95% confidence interval for the difference in the true means? Well, sure. It should be the difference of the two sample means plus or minus the critical value t times the square root of this sum of the sample variances. Now, this critical value t corresponds to whatever significance level we've chosen, like alpha could be 0.05, and the number of degrees of freedom from that formula that we had. So t might be a little more than 1.96 in a typical example. So this is easy. Let's see how it works in an example. Let's go back to our friends the skeletons, and let's consider now, suppose we wanted to compare these age differences depending on the gender of the skeleton. So let's recall that we had 400 skeletons in total, and each one of them had some age difference between the estimated minus the actual age at the time of death. Now, for the male skeletons, there were 281 of them, and they had their own mean for the age difference, which worked out to minus 12.9 years, with their own sample variance of 181.5. And the females, well, there were 119 of them, and they had their own sample mean, in this case minus 17.1 years, with their own sample variance, in this case 231.5. So that means the difference in the sample means was equal to 4.2 years. But the question is, what does that say, if anything, about the difference of the true means, that is, the true age difference for male skeletons minus the true age difference for female skeletons? Well, first we have to use that crazy formula from before to get the effective degrees of freedom, df. In this case, it works out to just over 200. And then we have to get the computer to help us compute the corresponding critical value, and it works out to 1.97 in this case, which is just a tiny bit more than the 1.96 it would be for the standard normal distribution. So then a 95% confidence interval, well, it should be the difference in the sample means plus or minus this critical value of 1.97 times this square root of the sum of the sample variances, which works out, when you put in the numbers, to between 1.03 years and 7.37 years. So in other words, we're saying that this age difference quantity is indeed higher on average in the males. It wasn't just a fluke of the samples we got. It's a true fact, and this true difference, the mu1 minus mu2, the true difference between the means, is somewhere in this range. So that's a confidence interval for the skeletons. Let's do a second example. Let's remember that map of the world and how we had different regions. And in particular, we considered life expectancy in one region was East Asia and the Pacific. Another region was South Asia. And we could say, well, what's the difference in the life expectancies in those two regions? Well, in this case, we can start by remembering the facts and figures. So East Asia and the Pacific had 30 countries. Their mean life expectancy was 73.1 years with their sample variance. And South Asia had just 8 countries. Their sample mean life expectancy was 67.0 years with their own sample variance. So that means the difference in the sample means is equal to 6.1 years. And again, we can say, what does that tell us in the difference in the true means? Now, I should say that in this case, in some sense, there is no true mean because we just have these countries. There's not some overall population. But we can imagine there is. We can imagine, as we discussed before, a typical population of countries from East Asia and the Pacific and a typical population of countries from South Asia. And we're looking to see what the range is, or the confidence interval, on the difference in the means of these imagined theoretical world populations. So in this case, we again use that crazy formula to compute an effective number of degrees of freedom. In this case, it's just a little more than 9 because the sample sizes are so much smaller. And compute the corresponding critical value, which in this case works out to 2.26, so a little bit more than the 1.96 that it would be if we had a really large sample. And then we can plug in the formula and get a 95% confidence interval, again given by the difference in the means, plus or minus this critical value 2.26 times the square root of this sum of the sample variances. And when you stick in the numbers and work it out, we get a range from minus 1.2 years up to 13.4 years. So we're saying at the 95% confidence level, East Asia and the Pacific could have a life expectancy which is lower by as much as 1.2 years, or which is higher by up to 13.4 years. So that tells us about confidence intervals. What about hypothesis testing? In a hypothesis test, we usually want to test whether the true means of the two different samples are equal to each other, that's the null hypothesis, or they're different from each other, that's the alternative hypothesis. Now remember what we know. We know that this statistic, this difference of the sample means minus the difference of the true means divided by the square root of the appropriate sample variance, is approximately a t-distribution with some number of degrees of freedom given by that complicated formula from before. So we can use that to compute p-values. Now, one thing you might wonder, if you remember what we did with proportions, we said that under the null hypothesis, we were assuming the two p's were equal, so we could kind of pool our estimate and get a single pooled estimate for p hat. Well, in this case, you might wonder, under the null hypothesis, can we again pool things together? Well, the answer is no, unless we also assume that the two samples have the same variance. If they have different variances, then even if they do have the same mean under the null hypothesis, we can't pool them. So for now, we won't do any pooling, but at the end of this lecture, we'll consider the possibility of pooling if we assume the variances are equal. So for now, let's go back to that skeletons example, and remember we had the two different samples for the male skeletons and the female skeletons. They each had their sample size, their sample mean, and their sample variance. And we computed the degrees of freedom from that big complicated formula as being just over 200. And now we're going to do a hypothesis test to see, are the means of these two samples, that is the age differences for the male skeletons compared to the age differences for the female skeletons, are these two means equal or are they unequal? Well, the difference in the sample means, as we already saw, is equal to 4.2 years. But then the question is, does that tell us that mu1 minus mu2 is not equal to 0 either? Well, now we know how to compute a p-value. We'll say the p-value should be the probability that we would observe a difference in the sample means, which is at least as big as 4.2 years under the null hypothesis. So we do our old trick of subtracting off the mean, although in this case mu1 minus mu2 is actually 0, but we can think of subtracting it off, and then dividing by the square root of the sample variance again. And we do that to both sides. And then we say, well, the left-hand side is approximately the absolute value of a t-distribution with that number of degrees of freedom just over 200. And the right-hand side is just some number, and we can work it out. And we're saying, what's the probability that a t-distribution with that many degrees of freedom is bigger than or equal to 2.61? And the answer is that's pretty small. That's a little less than 1%. And so unless you have a very small significance level, you're probably going to say, well, we should reject H0. That means we would conclude that indeed mu1 is different from mu2. Indeed, the mean age difference for the male skeletons, even the true mean, is simply not the same as the true mean for the female skeletons. Okay, now let's do another example. Let's go back to that life expectancies example. And remember there we had one sample was the life expectancies in East Asia and the Pacific, and there were 30 countries there. The other sample was for South Asia, and there were 8 countries there. And they each had their own sample mean and their own sample variance. And again, we want to test the hypothesis that the two true means are equal versus the alternative that the two true means are not equal. Well, the observed difference in the sample means is here equal to 6.1 years. So the p-value should be the probability under H0 that the difference in the sample means would be at least as big as this 6.1 years. Well, again, we subtract off the mean even though it's 0. We divide by the square root of the sample variance that we compute, and we say it's the probability that the absolute value of a t-distribution with now the number of degrees of freedom is 9.09 is bigger than or equal to this number that when you plug it all in says is it bigger than or equal to 1.90. And that's approximately a 9% probability. Now that's not so small. So again, it would depend on your significance level, but probably you would say, no, we can't actually reject H0, and we would allow for the possibility that maybe these two means are equal. So maybe it's true that sort of a typical country from East Asia and the Pacific has the same average life expectancy as a typical country from South Asia. So now we know how to compare two means and how to get confidence intervals and do hypothesis tests, all using that same t-statistic that we developed at the beginning. As our final topic for this lecture, let's go back to that issue of pooling the estimates for the variance. So let's imagine now we're still doing a hypothesis test, but now it's a pool test, meaning that we're going to assume that the variances are equal for the two samples. We still want to test the same null hypothesis that the two sample means are equal versus the alternative that they're not equal. We still have this statistic from before which said that this quantity involving the differences of the sample means minus the differences of the true means was approximately a t-distribution. But now we're going to assume that the true variance is the same for the first sample as it is for the second sample. And that means that under H0, if we're trying to compute for the null hypothesis, we have the same mean and the variance, and then it turns out that we can pool the samples. So we come up with a common estimate of the variance for both samples together because we're assuming it's the same. And the formula for it is this pooled variance, which is kind of a weighted average of the individual sample variances of the two samples. Indeed, if the sample sizes are the same, then it's just half of one plus half of the other. If they're different, then we count the one that's a bigger sample a little bit more. But anyway, we get this pooled sample based on estimating the variance for the two samples put together. And the degrees of freedom in the t-distribution actually simplifies now. Under this assumption of equal variances, and where we're pooling the estimate for the variance, the number of degrees of freedom is simply the sum of the number of degrees of freedom for the two individual samples, namely n1 minus 1 for the first sample plus n2 minus 1 for the second sample. And that gives us a simple formula for the degrees of freedom, much simpler than that horrible complicated formula from before. So let's try this out in an example. Let's go back one more time to the skeletons. And again, we had the male skeletons, the 281 of them with their sample mean and variance. We had the female skeletons, 119 of them with their sample mean and variance. And we're still testing whether the means are equal versus whether they're unequal. But now we're going to assume that the true variances are the same for both genders. And if we assume that, then we can pool the variance estimator. And using that same formula, we get an S squared, this pooled variance, which works out to about 196.3. Now we knew that the observed difference in the means was 4.2 years, and now the number of degrees of freedom is just n1 minus 1 plus n2 minus 1, which is equal to 398. So now we know how to compute a p-value, and indeed the p-value should be the probability, once again, that the observed sample difference would be at least as big as the 4.2 that we got. And, well, again, we can subtract and divide and say it should be the same as this other quantity being bigger than or equal to 4.2 divided by the square root of that sample variance. But one difference now is instead of using S1 squared and then S2 squared, we're using this pooled value S squared everywhere. Well, then we can continue the calculation, and it's the same as the probability that a t-distribution with our new number of degrees of freedom, namely 398, is bigger than or equal to this number that works out to 2.74, and the probability of that works out to 0.0064. So this is a p-value which is even a little bit smaller than the p-value we got when we didn't make that assumption. We didn't get the pooled estimate for the variance. And once again, we would probably say that we're going to reject the null hypothesis. And once again, we would say that the male skeletons do indeed have a different true mean age difference compared to the female skeletons. Okay, so whether we're doing a pooled version or an unpooled version, now we understand how to compare two different means from two independent samples and to use these two different forms of the t-distributions, and we can compute the confidence intervals, we can compute hypothesis tests without pooling and without assuming the variances are equal, and we can compute hypothesis tests with pooling when we do assume that the variances are equal. In this way, we understand a lot about how to compare two different independent sample means.
Matched pairs are tutorial. We've made it to week 6, and we've learned a lot of things along the way, but we're not quite done yet. In terms of material, we are now focusing on the methods required to compare two samples. With respect to R, we still have to learn how to use R scripts, which are very useful to keep our code nicely organized. Let's first get acquainted with using R scripts. We can create a new blank R script from File, New Document. Or from this icon. An R script is essentially a text document, but it's special because it allows you to execute code from within the file without having to copy and paste or retype commands every time. Shall we try an easy example first? What's 1 plus 1? On a Mac, you can execute each line by pressing Command and Enter, or on a Windows machine, you can press F5. Or we can write more code, like 2 plus 2, highlight multiple lines, and execute them all at once, with again pressing Command and Enter. You can even insert comments by putting a hashtag in front of your comment. When this line is executed, R knows it is a comment, so it won't throw an error. You can now save this file and use it later. Our focus today will be on two sample confidence intervals and hypothesis tests for matched or paired data. You should download the R script I have uploaded along with this video to follow along. You can now open the R script from File, Open Document. You will notice that our R script has lots of commands and comments to remind us what the commands are used for. We'll begin by setting our working directory, reading in the data, and attaching it so we have access to the variable names. It's always good practice to look at the data before we begin working with it, and we can do this with the head command. It gives us a preview of the first few observations. Recall that for each skeleton, we have the Deganji error and the Suchi-Brooks error, making this a matched pair dataset. And we are interested in analyzing the difference between the two methods. Now the difference is already calculated for us, but we could do it ourselves as well, just by defining a new variable myDifference and setting it to the difference between the two methods. Notice that the subtraction is done component-wise, or line by line. If we view our difference and the one that's part of the dataset side by side, we see that they are the same. We can even double check that they are equal with the double equal sign, which is a logical question that returns true or false, again component-wise. You'll also notice that there are two NAs, which Allison mentioned in the lecture. We can even obtain the mean and standard deviation of the differences if we want to calculate anything by hand. But in this case, we must insert an optional argument na.rm is equal to true, which removes any NAs from the dataset. Now, since we are only analyzing the difference between the two methods, we have one sample yet again. It's just a sample of differences. So we can use t.test to test whether the mean difference is 0, or alternatively, whether the two methods are equal. With t.test, we also have the option of just inputting each dataset separately and specifying that they contain paired observations with the argument paired is equal to true. These two methods produce the same results. The extremely small p-value lets us reject HO and conclude that there is a difference between the two methods. R scripts are convenient when you have a lot of code to execute, when you need to execute the same commands over and over again, or when it's useful to have comments within your code. From now on, we will choose to use R scripts in our tutorials. We hope you will find them very useful. Comparing two proportions, our tutorial. In the lecture today, you learned how to compare proportions obtained from two independent samples. Jeff derived the form of the confidence interval and then showed how to arrive at the same conclusion using a hypothesis test for the difference in proportions. Let's work through the Rob Ford polls example. Recall that the first poll had 1,050 participants with a support of 57%, and the second poll had 1,046 participants with a support of 42%. Let's enter this information in R under appropriate variable names. We will need to calculate the number of successes for each poll, or the actual number of supporters. So for the first poll, we can multiply n1 times p hat 1 to obtain approximately 598 supporters out of 1,050. And similarly, we obtain 439 supporters for the second poll. Recall that we need to use the round function to obtain a whole number, since we are talking about the number of people. Now we are ready to use the command prop.test. The first argument is the number of successes, combined with the C command. The second argument is the sample sizes, again combined. The third argument is the alternative hypothesis, two-sided in our case, and we will add the optional argument correct equals to false. We'll decipher the output step by step. First, we can see that we obtain sample estimates for the proportions, these being the p-hat values we started with, 0.57 and 0.42. Next, we obtain a 95% confidence interval. This tells us that the true support for Mayor Rob Ford decreased by anywhere between 10.8 and 19.2%. If you wish to change the confidence level, you can do so with the argument conf.level. And above, we see the hypothesis test for the difference between the two proportions. With such a small p-value, we can reject the null hypothesis and conclude the alternative, that the true proportions of supporters differ between the two polls. Do note that for the hypothesis test, the test statistic calculated is not the one we want. Prop.test chooses to calculate a chi-squared test statistic, as opposed to our test statistic, which is derived from the normal distribution. But we can calculate the test statistic ourselves, using the formula that Jeff introduced. First, we'll calculate the pooled p-hat to obtain 0.495, and then we will use it to calculate the test statistic to obtain approximately 6.87. The p-value for this test statistic will, however, match the p-value obtained with prop.test. So it is safe to use prop.test if you're interested in just a conclusion of the test. Comparing two means, our tutorial. In the lecture today, Jeff extended our discussion on two-sample inference by introducing the confidence intervals and hypothesis tests used to compare two means from two independent samples. The example we will focus on will be for the skeletal remains dataset. Let's read it in and attach the variable names, and with the head command we will view the first few observations. We wish to compare the age difference between males and females, so we will have to split up the dataset. Recall that the variable sex has been coded such that 1 indicates a male and 2 indicates a female. So we will define a new variable male diff and we will set it equal to a subset of skeletons, our dataset. To index into the dataset, we will use square brackets, the first entry being the rows, where sex equals to 1 for males, and the second entry being the sixth column, which contains the DG difference variable we are interested in. And similarly, we will do this for the female differences. If we want to calculate anything by hand, it would be useful to obtain the sample size with the length command, the sample mean and the sample variance for both groups. And we can even find the critical value from the t-distribution with the qt command. But we can also let R do all of the work. For a two-sample t-test, we can use the command t.test, specifying the two independent samples, male diff and female diff. Notice that there are no additional arguments given. The default arguments are just what we need. The alternative hypothesis is two-sided, the null hypothesized mean difference is 0, and the confidence level is 0.95. Our conclusion from the confidence interval is that the mean age difference is higher for males by about 1.03 to 7.37 years. This conclusion is supported, of course, by the small p-value, from which we can reject HO and conclude that the true mean age difference for the male skeletons is different than for the female skeletons. You can also specify an extra assumption for this hypothesis test, that the two population variances are equal, with the var.equal is equal to true argument. This changes the test statistic in degrees of freedom, and therefore the p-value as well, but our conclusion remains the same. There is a significant difference between the mean age difference for the male and female skeletons.
So far in this course, we've learned about descriptive statistics like the median and the quartiles and the spread of the data, and then we developed theoretical tools to learn about inference, things like the confidence intervals and hypothesis tests and so on. This week we're going to consider linear regression, or lines of best fit, or how to understand linear relationships between the data. We already saw a little bit about this way back when we looked at the scatter plots to understand in a first way the relationship between two quantitative variables. Now we're going to get into it in more detail. So to start us off, let's go back to one of our favorite examples, the skeletons. And you may recall that we looked at a graph before, a scatter plot of the age difference between the estimated age minus the actual age at time of death of the skeletons, as compared to the BMI, the body mass index of the skeletons, to see if there was some relationship. Now, if we just drew a scatter plot, it looked kind of like this. It was a big jumble of dots. But then we talked about various ways of understanding it, things like the correlation and so on. And one of them was a line of best fit through the data, which looks like this. And we said, well, from this line of best fit, we can understand certain things, like, for example, the slope of the line, which in this case is positive and is about 0.41, which means there's a slight positive relationship. It means when the BMI gets larger, then the age difference seems to get slightly larger on average. But then you might wonder, first of all, how did we come up with this line of best fit, and what are its properties and so on? So to start us off, let's introduce a bit of vocabulary. So we have the dependent variable, or response variable, which is, we'll usually call it yi's, and it's the values that we're interested in trying to predict, in this case, like the age difference between the estimated minus the actual age of the skeletons. We also have the independent variables, also sometimes called the explanatory variable or the predictor variable, and that's what we'll usually call the x's, and that's in this case like the BMI, and we're seeing to what extent the BMI can help us to predict the values of the age difference. So this line that we're going to come up with, well, you might think of a line as having a formula like y equals mx plus b, and that's what we're going to do. It's more common to use slightly different letters and call it y equals b0 plus b1x. So we have a line like that, and we're trying to come up with the values of b0 and b1, which are the best they can be to make this line describe the data as well as possible. So how do we do that? Well, we can think that at a given point xi, the line value would give us a value for y, which is equal to b0 plus b1 times xi. But the observed value for y is the yi. And the difference between these two values, or the residual, is just yi minus b0 minus b1 times xi. We'd like to make these differences be as small as possible. Well, we don't just want them to be small because then they could go negative. So we might want to take their absolute values, or it turns out to be easier, kind of like we did for variance and so on, to take their squares. So we'll look at actually the sum of the squares of all of these differences between the observed values of y and the values that we would get if we plugged in xi into the formula for the line. And this gives us a big sum of squares, as it's called, and then we want to find the values of b0 and b1 which minimize it, which make this sum of squares as small as possible. Well, this is a job for calculus. So if you remember your calculus, you'll remember that we want to find a critical value, so we want to make the partial derivatives of this sum of squares with respect to b0 or with respect to b1 equal to 0. Now that's kind of a messy problem, but you can work it out, and you end up with these crazy formulas here for a formula for the value of b0 and a formula for the value of b1. Now in this course, we're not going to try to work these out by hand. We'll usually let the computer do it for us. But it's important to understand that there is a formula and there's no judgment involved. We're not eyeballing what seems like a good line of best fit. We're using a formula to find a line of best fit which minimizes this sum of squares of the differences between the predicted values and the observed values. In this example, when we work out those whole formulas, or let the computer do it for us, we compute that b0, which is sometimes called the intercept, works out to minus 23.3 years. And b1, which is sometimes called the slope, works out to plus 0.41. And that's what gives us this red line that we've graphed here. So how can we interpret these values? Well, 0.41 as a slope is saying that when the BMI increases by 1, then this age difference increases by 0.41. So it's a measure of how much the age difference increases when the BMI increases. Similarly, if the BMI were to decrease by 1, then the age difference would decrease by 0.41. So that explains the slope. What about this intercept value, b0? Well, one way to think about it is that's the value that the line would give us if the independent variable, in this case BMI, were equal to 0. Now, in this case, the BMI can never be 0, so it's not really that useful to interpret this intercept value, or a b0, in terms of the value when BMI equals 0. So we just think of it as how much we have to shift the line in order to get the line of best fit. Here's another question about slopes. Suppose we were to graph it the other way around. That is, instead of trying to do a regression of the age difference as a function of the BMI, suppose we try to do a regression for the BMI as a function of the age difference. Well, since we're just swapping things around, you might expect that the slope would just get swapped around to be the reciprocal, to be 1 over the other value. Well, let's try it and see. Here's a linear regression where now the independent variable, or x value, is the age difference, and the dependent variable, or y, is now the BMI. Well, in that case, we get a graph like this, and we can see that we again have a red line with a slightly positive slope. But is this slope just 1 over the other slope? No, not at all. This slope is equal to about plus 0.046, which isn't even close to 1 over 0.41, which was the other slope. So in other words, regression is not symmetric. Regressing one variable against another is not the same as regressing the second variable against the first one. For one final example, let's remember a graph that we saw earlier, a scatter plot for the countries and territories of the world, comparing their life expectancy in years compared to their GDP per capita. Well, we can see from this graph that the countries, as you might expect, with the higher GDPs also tend to have higher life expectancies. And indeed, we can fit a line of best fit, or a linear regression in this case too, and that red line gives us some sense of the relationship. It has a positive slope, in this case equal to about 0.45 years for every $1,000 of GDP per capita that the country has more. And the intercept in this case is 63.3, and that's again hard to interpret because it's sort of saying if the GDP were 0, then the life expectancy would still be 63.3 years, and that doesn't seem quite right, and indeed some of the data seems to contradict that too. So this suggests that there's more to the story than just the linear relationship, and indeed we can see that the points on the graph here seem to have their own behavior, which isn't just linear. So we'll come back to this point later of how to understand relationship in ways other than just the linear fit or the linear regression. Anyway, in all of these examples, we see that one possibility when comparing one quantitative variable to another is to take a linear regression where one of the variables is the independent variable and then the other variable is the dependent variable, and we use a line of best fit or linear regression which has a precise formula that you can work out on the computer to give us exactly what is this line that does the best job of trying to fit the data in the sense of minimizing the sum of the squares of how far the line is from the corresponding point. And in this case, we get a formula. In the lectures ahead, we'll learn more about how to interpret this formula and how to interpret this line and what it all means. So now we know the basic formulas for the intercept coefficient B0 and the slope coefficient B1 for the line of best fit or the linear regression through our data. For the most part, we'll just let the computer work out the B0 and B1 for us, but in this lecture we're going to think a little more about those formulas and what they really mean. Let's start, because it's a little simpler, with the intercept formula. So here's the formula for that intercept coefficient B0, and it's not that exciting in a way, but we can say, well, we can notice first of all that it kind of has y bar and x bar snuck into it. That is, it's the same as this version here, because after all, y bar is just 1 over n times the sum of the yi's, and x bar is 1 over n times the sum of the xi's. So is that of interest to us? Well, it does mean that you can rewrite the regression line. So if we have a given value xi, and we want to know what's the y value on the line at that point xi, it's given by this formula here. So it's b0 plus b1 times xi. But if we rewrite that a little bit, we can see it's kind of like start at y bar, start at the mean of the y's, and then shift that according to how far your xi is from x bar, and then multiply that by the slope, which is the b1. So it gives us a bit of an intuition about what this line of best fit is all about. One thing it means in particular is if it so happened that xi was equal to x bar, that is, if we started at an x value right at the mean, well, then the corresponding y value, as you can see, would also be equal to y bar. So it means that the point x bar comma y bar is actually on the line of best fit. So we can see that this line that tries to match up all the points as well as possible, it always goes right through the mean of x and mean of y. That's always going to be a point on the line. Okay, so that's a little something about the intercept coefficient. What about the slope coefficient B1? Well, that's a little more complicated. Remember, the formula here is kind of a big mess, and we don't really understand it too well. Well, let's just start manipulating a bit. We can start by dividing top and bottom by n squared, and then it looks like this. Well, that doesn't look too much better, but we can see some x bar and y bars hidden in there. So now we can rewrite it like this, where x bar and y bar is the same as before. The next trick is to say, well, both numerator and denominator, they're a sum of products minus sort of product of sums. Well, you can rewrite it this way, and you have to think about that for a second, because if you tried to multiply that out and sum it, you'd get some cross terms. But it turns out in both the top and the bottom, the cross terms kind of give you minus twice that final product, and then the final product there gives you one copy of it back. So you end up with the same minus x bar y bar in the numerator or minus x bar squared in the denominator, same as before, and you can check that if you want. Then we can just cancel out the 1 over n's for a second and say, well, here's a formula for B1. And now let's do something that looks even a little crazier. So what I've done here is I've, first of all, separated out the denominator into its square root multiplied by its square root again. And then I've also multiplied and divided by this other square root, the square root of the sum of yi minus y bar squared. And it ends up what looks like an even messier formula than we had before. But then we can start to interpret it, because we can say, well, B1 now is that first crazy thing, which we'll call R, times this ratio, which we'll call S sub y over S sub x. And each of these factors is something that we've seen before. So this R here, well, it's this big crazy mess of a sum of xi minus x bar, y minus y bar over square root, whatever. Well, that's a formula for the correlation between x and y. And we saw that way back when we were doing exploratory statistics. It's a measure of how much y tends to vary with x. So that makes perfect sense. Well, S sub x, that's just the sample standard deviation, or the square root of the sample variance for x. And similarly, S sub y is the sample standard deviation for y. So now we've kind of rewritten this big horrible formula for the slope coefficient B1, at least in terms of some things which are more familiar to us, even if they're not necessarily simple exactly. But that's going to turn out to be useful for us at times. Finally, let's talk about the residuals. So by residual, we'll mean the actual value that we observed minus the value that we would predict according to that line of best fit. So that is to say, the ith residual, we'll call it E sub I, and it's going to be y sub I minus what we would get on the line, namely the b0 plus b1 times xi. So you can rewrite it like this, and then we can start to learn some things about the residuals too. So what about the mean of all those residuals? Well, some of them might be positive, some of them might be negative. Here's a calculation for the mean. So the mean will then be the mean of the yi's, which is to say y bar, minus b0 minus b1 times the mean of the xi's, which is x bar. Now, if we just use, once again, that formula that we just derived for b0 and plug it in, then everything cancels out, and we get a mean of 0. So it means, yes, some of the residuals are positive, and some of them are negative, but their mean is 0, which kind of makes sense. It says that this line is trying to fit the data as well as possible, so it balances out. So on average, it hits it exactly. Sometimes it's too high, sometimes it's too low, but on average, it gets it right. Now, what about the variance of these residuals, these EIs? This turns out to be quite an important calculation. So we say, what's the variation in these EIs, the amount that's left over after we do our best line of best fit? Well, to do that, we need to do a little more algebraic manipulation, which I know you love so much. So we'll start out, here's the definition of EI. Then let's substitute in what we know for our formula for B0, and let's rewrite that a bit, and we can write it as yi minus y bar minus b1 times xi minus x bar. But then we can rewrite that and say, well, b1, we have this formula now, which is this r, this correlation, times sy divided by sx. So now we've got a formula for ei. Now let's look at ei minus e bar squared. Well, e bar, we just said, is equal to 0. So it's just ei squared. And we square that out. Now we do have cross terms, so we get this minus 2 times the cross term. And then we start computing for the variance. And the variance should be now the average, or 1 over n minus 1 times the sum of these things. And we start working it out, and we say, well, that yi minus y bar squared, when you take 1 over n minus 1 times that, that's just the variance of y, or sy squared. The second term is, again, this coefficient r times sy over sx squared, times this sx squared for the same reason. And then the cross term is, well, we've got a minus 2r sy over sx, but then we've got this sum of the xi minus x bars times yi minus y bars. So if we keep working away at that, we can say, well, this middle sum, that's kind of like a correlation again. And indeed, when we work it out and we stick in the values and normalize and everything, we get that the variance of E is the same as sy squared, well, that's the variance of y, times just 1 minus r squared, where r is this correlation coefficient again. So that is to say, when we put it all together, we can say the variance of the residuals E is equal to the variance of the y values, the yi's, multiplied by 1 minus r squared. So what does that mean? It means when you do regression, you kind of multiply the variance by 1 minus r squared, or once you take away the linear relationship, that removes or reduces a fraction r squared of the variance of y. And you can also, if you want to be fancier, say the linear relationship kind of explains a fraction r squared of the variation in y, and we're left over with just 1 minus r squared times the original variation. That's the variation in the residuals. Now this r squared is sometimes called the coefficient of determination, and you can think of it as saying what fraction of the variation in y has been explained by this linear relationship. Now if r squared equals 0, then that means, well, we didn't actually explain anything at all. There's no linear relationship between the y's and the x's, so we needn't have bothered. If r squared equals 1 at the other extreme, then that means the linear relationship explains everything. Once you know the x's, then you automatically know the y's completely. There's no leftover residuals. There's no leftover uncertainty. Usually it will be somewhere in between these two extremes, as you might expect. For our first example, let's go back again to the skeleton example where we were comparing the age difference, regressing that as a function of the BMI, the body mass index. And in that case, you can compute r squared either by working out the formulas that we talked about, or by computing the correlation and then squaring it, or by letting the computer do it for you. And one way or another, you figure out that the r squared is equal to 0.0186. Or in percent terms, you could say it's 1.86%. So that means in this case, the linear relationship is hardly explaining anything at all about the age difference. It's just explaining 1.86% of the variation that we get in this age difference can be explained by a linear relationship with the BMI. And that means that all the rest, over 98% of the variation, is not explained by BMI, and there must be more to the story. Let's do a second example, which is that GDP. So here we were considering the life expectancy of countries and territories around the world as a function of the GDP per capita of each of those countries. And that's the case. We already did the regression. Now we can compute the r squared again, either by using those formulas or by computing the correlation and squaring it, or probably by letting the computer do it for us. And in this case, we get a value of 0.4033, or just over 40%. So that's actually a much higher value, and it suggests that a fair bit of the variation in life expectancies in countries and territories around the world can indeed be explained by a linear relationship with the GDP per capita, or the wealth, of the different countries. And that's not so surprising. We've suspected for a while, and we've had some other evidence to suggest that indeed the GDP per capita is a fairly strong indicator of the life expectancy of a country. Now, it still doesn't explain everything because the r squared isn't 1, it's only equal to about 0.4, but it explains a fair bit. Now, we also notice that the relationship still doesn't look linear, as we said before, so once again, there's more to the story, and we'll come back to it again. But for now, we can see that r squared gives us some measure of how much of the variability is explained by the linear relationship. So in this lecture, we've learned a little more about those coefficients for the intercept and the slope of the linear regression, or the line of best fit. And we've also looked at the residuals, the E sub i's, and we've learned a little bit about how they are. For example, their mean is 0, and their variance can be computed in terms of the correlation and the standard deviations of the y and then the x. And then we saw finally that the linear relationship reduces the variance of the yi's. It multiplies it by 1 minus r squared, or it explains a fraction, r squared, of the variation. So far, we've been studying linear regression, or the line of best fit, through some data. And we came up with some formulas that tell us, here's a formula for B0, the intercept of the line of best fit, and here's a formula for B1, the slope of the line of best fit. Now, whenever we come up with a formula like that, you should be wondering, how much uncertainty is there in those values? That is, do we know that the true intercept and slope are exactly what the formula says? Or maybe we're not quite sure and there's some uncertainty. And maybe we've got the data world values of the intercept and slope, but maybe there are some underlying theoretical values from the theoretical world, and there might be some uncertainty about them. So let's consider that. To set it up, let's first of all concentrate on the slope, because that's usually more important. And we have a formula for the B1, the regression slope that we get from the data. And the question, as I said, is what's the uncertainty? Can we get confidence intervals? Can we do hypothesis testing for the true value of the slope? So for this to make sense, we have to imagine that there's a theoretical world with a true underlying slope, which we'll now call a beta 1 to distinguish it from the B1, which is the experimental or a data world. And now we want to say, how close are these things to each other? That is, we got from our data in that formula, we got a data world value B1. How close is that to the true theoretical underlying value of beta 1? Well, there's a very important fact that we're not going to justify here, but it says that this coefficient for the slope, it also satisfies a sort of a t-distribution. And indeed, if you look at the experimental value B1 minus the true theoretical value beta 1 and divide by a certain standard error of B1 that we'll talk about in a sec, then that also has a t-distribution, kind of like those confidence intervals and hypothesis tests that we did before. In this case, it's a t-distribution with n-2 degrees of freedom. We kind of lose 1 degree because we don't know the slope and lose another degree because we don't know the intercept. Anyway, it's just a fact for us that this formula has a t-distribution with n-2 degrees of freedom. And that standard error involved, well, that's a very important quantity for doing things like confidence intervals and hypothesis tests. And it turns out to be given by this crazy formula here. So the square root of the sum of the residual values, EI squared, divided by a square root of n-2, that same number of degrees of freedom, times the sum of the xi's minus their mean squared. So this is the formula that we're going to use. Once we have this fact, or we have this formula, then we can say, well, we can do things like get confidence intervals, and it's really the same as before. So we'd set it up and we'd say that now if we want a confidence interval, say to cover 1 minus alpha of the probability, well, that would be just kind of like it was when we had confidence intervals using the t-distribution before, namely the observed value, the B1, plus or minus the appropriate critical value, t sub alpha over 2, comma, n-2, because there's n-2 degrees of freedom, times this standard error of B1. Well, that's that crazy formula from the previous slide. So now we can say, well, let's do that skeletons example again. So that example of a regression that we had from the previous lecture. And there, remember, y was the age differences, the difference of the estimated minus the actual age of the skeleton at death. And x was now the BMI, the body mass index. And we had this data for 400 skeletons. And then we can say, well, in the experimental world or the data world, we computed a slope which was equal to B1, and it was plus 0.41. Then we compute, first of all, if we're going to compute that standard error thing, we have to compute the sum of the EI squareds, and that you can just compute or get a computer to compute it. It worked out to 78,132. We also have to compute the sum of those squared deviations of xi minus x bar, and that worked out to 8,992. And also we need that critical value for the t-distribution. Well, since it's a large number of degrees of freedom, it's probably pretty close to that usual 1.96 for the normal, and in this case it's actually 1.97, just a little bit higher. And then we can get the confidence interval the same as before. We take the observed value, the plus 0.41, and then plus or minus, well, that critical value, 1.97, times the square root of the sum of the EI squareds, divided by the square root of n-2 times the sum of the xi minus x bar squareds. And when you work that all out, it works out to an interval of between 0.12 and 0.70. So now we can say that when you're comparing the age difference for the skeletons compared to the BMI or the body mass index, well, we think the slope is plus 0.41, but we're 95% confident that it's between 0.12 and 0.70. So then you say, well, that's a confidence interval. What about a hypothesis test? Well, for a hypothesis test, the usual thing we want to test is whether the true underlying slope, the beta 1, is equal to 0 versus the alternative that it's some other value. Well, remember what we know. We know that if you take the observed B1 minus the true value beta 1 and divide by that crazy standard error for B1, that has approximately a t-distribution with n-2 degrees of freedom. And we already know that in this case, the B1 was plus 0.41. And what we just worked out was that that standard error of B1 from that crazy formula was equal to 0.148. So now we know how to compute a p-value too. It's our same old trick of starting by saying, well, what's the probability under H0 that the true value beta 1 differs from the observed value B1 in absolute value by at least what we got, which was 0.41. Well, you just divide both sides by that standard error, which in this case is divide both sides by 0.148. And then what we say is, well, that left-hand side, that's now like the absolute value of a t-distribution with n minus 2, or 398 degrees of freedom. And the right-hand side, that works out to 2.77. And it turns out that the probability, according to the computer, that a t-distribution with 398 degrees of freedom will be bigger than or equal to 2.77 in absolute value is about 0.0059. Now that's quite a small value, quite a small p-value. So probably we would have a significance level that would be such that we would reject H0. We would say it's not true that beta 1 equals 0. So in this example with the skeletons, we would conclude and say, no, there really is some sort of linear relationship, and the true theoretical underlying value of the slope is just not equal to 0. Now, you should be careful when you do either a confidence interval or a hypothesis test that you don't overstep your bounds and say, well, that means that when the BMI goes up, that causes a change in the age difference. Because after all, this was not a randomized experiment. We just got some observational data. And so that means we can't conclude any causal relationship. We can just say there's some sort of a relationship, and indeed some sort of a linear relationship, between the BMI and the age difference for those skeletons. So now let's consider a few other quick, simple examples to give us an idea of some of the limitations of linear regression. For our first example, consider the data here. You can probably tell that y has a very close relationship with x, in fact, a quadratic relationship. In fact, y is just equal to x squared here. But suppose we try to do a linear regression. Well, the line of best fit, according to the formulas, would look just like this. So it's doing its best to try to fit all these different data points, but it's not really telling us much. It's a flat line. It's saying that the slope is equal to 0, which is kind of like saying there's no linear relationship in this case between the y values and the x values. And yet we know there's still a very strong relationship. It's just quadratic. So linear regression by itself is not enough to tell us about the relationship in this case. For a second example, let's look at 4 different sets of data. In each case, there's 11 different points, 11 different x's and 11 different corresponding y's. And this is a famous example that tells us 4 different graphs. And in each one, you might say, well, what's the line of best fit or linear regression going to look like? Now, these 4 different sets of data look pretty different. One of them looks like a nice linear relationship. One of them looks like a curve. One of them looks like most points on a line, but one of them way up. One of them looks like all the points kind of squished on top of each other, except one way off in the corner. And yet, if we look at the line of best fit, it's exactly the same in each of these 4 cases. Furthermore, the mean of x is the same in each of these 4 cases, and the mean of y is the same in each of these 4 cases. And furthermore, the correlation between x and y is the same in each of these 4 cases. So this is a classic example to say, even if you know the means and the variances and the correlations and the lines of best fit, you still don't really know everything about the data and about the relationship between it. And sometimes you just have to graph it and look at it and think about it. For one final example, let's look at this set of 5 points, so 5 x values with 5 corresponding y values. And this looks like a pretty good relationship, pretty linear relationship. And indeed, if we graph a line of best fit, it goes pretty close to the data points, kind of like this. Suppose now we add one more point, a 6th point, down in the right corner like this. Well, we haven't changed the data that much. We've just added one new point. And yet if we look at the line of best fit now, then it's the purple line instead of the red line. And it's quite different. And this is a way of telling us that linear regression is not particularly robust or resistant to outliers. And if you put in just one or a few points which are very different, that could change rather significantly the line of best fit and thus the slope and the perceived linear relationship. So whenever you're studying linear regression, you should always keep in mind that maybe there's just a few outliers or a few unusual values which are skewing your sense of what the true relationship is. So now we understand a bit about how to do confidence intervals and hypothesis tests for these slopes with these linear regressions, and also some cautionary examples to let us think that linear regression is a very useful tool, but it doesn't tell us the whole story, and it's always good to do some graphs and think about what's going on and think about the limitations of linear regression. So far this week, we've learned a lot about linear regression as a way to understand the linear relationships between two quantitative variables. Now, one thing we could ask is whether the two variables are really well described by a linear relationship. Now, we know some things about that already. For example, we know the R squared, the coefficient of determination, to measure how much of the variability in y is explained by the linear relationship with x. And we know about hypothesis testing to test whether or not the slope is equal to 0 or is not equal to 0 when comparing y to x. But we could still ask whether there's other things about the relationship between y and x that are not captured by the linear relationship. So let's consider some examples of that. For the first one, let's consider what we'll come to regard as an ideal case. So here we have a bunch of different points. Again, there's different x values and different y values. And the graph looks kind of linear, and that's the first thing you should always do is look at the graph and see if it's linear. Then, of course, we can use our formulas or get the computer to plot a line of best fit, the linear regression line, and there it is, and we see it appears to describe the data fairly well. But then we can also look at the residuals. Now remember, the residuals are the difference between the actual values of y that we see and the values that we would see along that line of best fit. So if we transform this graph into a graph of the residuals, then we're just seeing how far apart these yi's are from the line. And this is an ideal case because it's not because the y's are all exactly on the line, there's always some uncertainty involved, but it's because there's no particular pattern in the residuals. We've taken out the linear relationship, and what we have left is just kind of independent random errors for each of the different observations. So some of them are above the line, some of them are below the line, but whether the x value is smaller or larger, that doesn't give us any trend as to whether the y's will tend to be below the line or tend to be above the line or tend to be farther from the line or tend to be closer to the line. So we say overall there's no particular trend in the residuals, that is after we take out the linear relationship, and that tells us that the linear relationship really is telling us something about the relationship between x and y. Now let's look at a second example, again an example that I just created. And here again, it looks like the data is pretty linear. That is, there's a linear relationship between x and y. And again, we can put in the line of best fit, and here it is. And it appears to describe the data fairly well. But if you look closely, you might already see a little bit of something unsettling. That is, it looks like the data points are above the line at the beginning and end at the left and right sides, and they're below the line in the middle for the most part. And again, we can see this much more clearly if we graph the residuals. So here's a graph of the residuals. And we can see now that it's fine that the points aren't all on the line and some are above and some are below. But what's concerning here is that when x is small or x is large, the y's appear to be, for the most part, larger, that is above the line. So the residuals are positive. Whereas when x is somewhere in the middle of the values, then the residuals tend to be negative, which means the y values tend to be below the line. So there's sort of a trend here. The residuals shouldn't have any trend anymore if it's truly a linear relationship, and yet they have a trend. They go from larger to smaller to larger again. So that's okay, but it means that in this case, the linear relationship is not describing the whole story. And indeed, I created this example by putting in a quadratic relationship between y and x. So that's why we got this distinctive pattern that isn't captured by the linear relationship. Now let's look at a third example. In this one, again, it looks like the dots are pretty much following a linear relationship. And again, we can put in the line of best fit, and it looks like it describes the data fairly well. But again, if you look closely, you might see a bit of a trend in that for smaller x values, the y values appear to be very close to the line, whereas for larger x values, the y values appear to be farther from the line. And indeed, we can see this again by doing a graph of the residual values. And here it is, and we can see that the residuals tend to be quite small, whether positive or negative, when x is very small. But as x gets larger, these residuals are either quite large or quite small. So again, that's not such a bad thing, and it still might be useful to have the line of best fit, but it also tells us that there's more to the story, and we can't just describe the relationship between y and x by a purely linear relationship. Now let's consider a final example. Namely, let's consider that example of the life expectancy of various countries and territories around the world as a function of their GDP per capita. Now we've seen this graph before, and we fit the line of best fit like this. And on the one hand, it looks like this line does capture a lot of the relationship, and indeed we found that the corresponding r squared value was a little more than 0.4, which is fairly good. But at the same time, just by looking at the graph, we can see it's not really linear shaped. It's got this funny curve or arc in it, and the linear relationship really isn't capturing the whole story. We can also see this if we graph the residuals, and here's a graph with the residuals, and we can see now again it's fine that some are below the line and some are above the line, but we see a very striking pattern. The countries with the smallest GDP per capita are mostly below the line, and then they kind of all go above the line, and then the really rich ones go below the line again. So this is certainly not a case where we have a great linear fit because the residuals don't show any trend. Here's a case where the residuals show a lot of trend. So in a case like this, if we wanted to improve the situation, one thing we could try to do is transform the variables. The most common transformation, and often a very useful one, is to take a logarithm. So hopefully we all remember logarithms. They're often done as natural logs, that is in the base e, but that scares some people, so let's just do them as base 10. And let's remember that if the log base 10 of a equals b, that means that 10 to the power of b equals a. So it's sort of an inverse of taking exponential, or of multiplying lots of 10s together. So now suppose we take the logarithm of, in this case, the GDP per capita, since that varies to such extreme values. You could take a logarithm of the life expectancy instead, or you could take a logarithm of both, or you could use other transformations like squares and square roots and so on. There's all kinds of things you could do. But for now, let's say, well, the GDP per capita varies to such extreme values that let's take a logarithm to kind of smooth things out. So we'll replace the GDP by the logarithm to the base 10 of the GDP. Now if we graph life expectancy in years as a function of the logarithm of the GDP per capita, then the graph looks like this. And we can see now that again there's dots all over the place. It's not a very simple relationship, but it does kind of look a little more linear. Once again, we can use the usual formulas to get the line of best fit, and here it is. And it appears to describe the data fairly well, maybe a little better than it did before. Indeed, we can check the r squared, the coefficient of determination, and in this case it's equal to about 0.658, which is even higher, a fair bit higher than the 0.4 that we had before. So we say that's good. Once we took a logarithm of the GDP per capita, then the linear relationship appears to describe it even better than it did before. But we can also look at the residuals again. So here's a graph of the residuals, again, when we're looking at the life expectancy as a function of the logarithm base 10 of the GDP per capita. And in this case, well, I wouldn't say it's without trends. That is, you can see that still the poorest countries tend to be below the line. The medium countries tend to be above the line. A few of the richer countries tend to be below the line again. So there's a little bit of a trend going on, but I would say it's far less pronounced than the trend was before. And I would say this is a much better fit. So we can say that the life expectancy seems to fit fairly well as a linear relationship with the logarithm of the GDP per capita. Now, once we do a transformation like that, we have to be able to understand how to interpret it. In this case, the slope was equal to about 14.93. But what does that mean? Well, that means if the logarithm of the GDP per capita increases by 1, then it tends to be that the life expectancy increases by about 14.93 years. But if the logarithm base 10 of the GDP increases by 1, that's the same as the GDP per capita being multiplied by a factor of 10. So what we can really say from this is that every time the GDP per capita is multiplied by a factor of 10, then the life expectancy in years is increased by about 14.93 years on average. Or the other way around, if the GDP per capita is divided by 10, then the life expectancy is decreased by about 14.93 years. Or for that matter, if the GDP per capita were multiplied by 100, then that's like multiplying by 10 and then multiplying by another 10. So the life expectancy would increase by about 14.93 plus 14.93 years. So in this way, we've discovered a relationship between the GDP per capita and the life expectancy in years, but it's not really a linear relationship in that way. It's a linear relationship between the logarithm of the GDP per capita and the life expectancy. So we'll see fairly often that transforming variables can sometimes make the relationships more clear and indeed make a linear relationship be a better way of describing the relationship. So that's good, but we do have to be careful to interpret the final equation in a way that makes sense in light of the transformation that we've performed. So in this way, we see that when you're considering a linear relationship, you should do things like look at the graph. You should think about whether the residuals appear to have trends, which is bad, or they appear to be free of trends, which is good, and means the linear relationship really does describe the relationship. And you should also think whether there's ways to transform the data in order to make the relationship linear and therefore a more accurate description.
Linear regression, our tutorial. You started a new topic this week, linear regression, and it is by far my favorite topic. We have quite a few tools we can use in R that will make finding the line of best fit very easy. The example we will focus on will be for the skeletal remains dataset. This is a new dataset that contains quantitative BMI measurements for each skeleton, and we will investigate the linear relationship between the age difference using the de Ganji method and the BMI of a skeleton. Again, we will set our working directory, read in the data, and attach the variable names. Let's start with a scatter plot of the data. Recall that with the plot command, we can obtain the scatter plot, making sure that the first entry is the independent or predictor variable BMI, and the second entry is the dependent or response variable DG difference. By just looking at the scatter plot, it's hard to try to explain the linear relationship. We need to obtain the line of best fit to be able to do that. For linear regression, we will use the command lm, which stands for linear model. The general form for lm is response tilde predictor. For us, it will be DG difference tilde BMI quant. The lm command will give us the line of best fit, that is the values for the intercept b0 and slope b1. So we can say that the line that best describes the linear trend of this data is y is equal to negative 23.3 plus 0.41x. We will need to save this linear model we have created to be able to use it later on, so we will save it under an appropriate name, linreg. If we want to visualize this line, we can recreate the scatterplot with the plot command as above, and add the line of best fit with the command abline, which takes as an argument the linear model we saved, linreg. In Lecture 7.2, you were also introduced to the coefficient of determination, or R squared, and the residuals. The residuals can be obtained from the linear model saved, linreg, $residuals. This gives us the residual at each of the 400 observations. You might be interested to plot these residuals, or even find their mean, to convince yourself that it is approximately 0. Probably the most useful command for a linear model is the summary command. If we ask for the summary of linreg, we obtain an output rich with information. Let's go through it step by step. We are reminded of the linear regression formula, which created this output. Below, we have summary statistics for the residuals. Next, we are given the coefficient estimates and test statistics, which you discussed in Lecture 7.3. For the intercept and the slope of the regression line, we are given the estimates B0 and B1, the standard errors of B0 and B1, and a test statistic and associated p-value for the two-sided hypothesis test of whether the coefficient is equal to 0 or not. Some of the bottom statistics might also be of interest to us. We have the standard deviation of the residuals and the degrees of freedom used in the tests. Recall that was n-2. And we also have the coefficient of determination, r squared. I hope you find the commands you learned here useful. Try them for yourself with the life expectancy dataset. Residual Analysis and Transformations, our tutorial. With the introduction of linear regression, we also learned a few tools that measured how well a linear relationship describes the actual relationship between two quantitative variables. Some of these tools included the coefficient of determination, r squared, or hypothesis testing for whether the slope equals to 0 or not. The new method you discussed today was an investigation into the residuals. For this tutorial, we will focus on the life expectancy dataset that includes the GDP per capita for each country. Let's set our working directory and read in this dataset. We will give each column their appropriate names, starting with the first column country, then life expectancy or life EXP, then GDP and HIV. We will attach these variable names and view the first few observations with the head command to make sure that our labeling was done properly. We are interested in life expectancy as a linear function of GDP, so we will begin with the command lm to obtain the line of best fit, or the regression equation. Recall that the form for an LM equation is predictor tilde response, so we will enter life exp tilde GDP. Now we can plot the data in a scatter plot with the predictor variable GDP as the first entry and the response variable life exp as the second, and plot the line of best fit, which is saved under linreg, with the command abline. The relationship between life expectancy and GDP doesn't seem to be described very well by the line of best fit, since there are many measurements far from the line. This definitely warrants an investigation into the residuals of this linear model. We can save the residuals from our linear regression under the variable name resids, and plot them against the predictor variable GDP to see if we observe any trends. For reference, you can plot a vertical line at 0 with the command abline, h, which stands for horizontal, equal to 0. We definitely see a trend in the residuals. For low and high values of GDP, we see mostly negative residuals, and for average values of GDP, mostly positive residuals. In the lecture, Jeff also discussed the possibility that a transformation of variables might be able to correct certain trends in the residuals. He examined the effect of transforming GDP by taking its logarithm base 10. Let's define a new variable, log GDP, which we will set equal to log 10 of GDP. Then we will obtain again the line of best fit with log GDP as the response. The scatter plot with the line of best fit now looks better. Let's check the residuals. We can save the residuals of this new line of best fit, linreg log, under resids log, and plot them against log GDP, the predictor. Even the graph of residuals seems to be better, therefore implying a better fit of a linear model to the transformed data. Checking a plot of residuals is a very important step in model fitting, and it can possibly lead to a transformation of variables. Keep that in mind the next time you do your next analysis.
Hello, and welcome to our capstone lectures. We've learned a number of different methods for summarizing data, including graphical displays and summary statistics, for understanding the natural variability in data and how to quantify it, for how to use probability models to understand the inherent randomness. We've learned how to investigate relationships among variables in data, and we've learned methods for inferring what we can about a population or about parameters in a theoretical world model. The purpose of the next few lectures is to apply what we've learned to a particular scientific investigation. The particular study that we're going to look at is the Canadian trial of carbohydrates and diabetes, which was concerned with how diet can be used to manage type 2 diabetes, with a particular focus on carbohydrates and the type of carbohydrate consumed. One of the first things that we said at the beginning of the course in our lectures is that in carrying out statistical work, it is essential to understand the context. The process of statistical inquiry is very much about the interplay between statistical methods and the subject matter for which the data were collected. And it's extremely important to always keep that context in mind while we're working. We're now going to take a look at the ideal sequence of steps in carrying out an investigation using statistical methods. The first is the formulation of clear, focused research questions, or perhaps one question. In order for the rest of the study to be done well, it's important to have a clear focus at the beginning. If research questions evolve with the study, as sometimes happens, it's then necessary to confirm them with future studies and new data. Studies using statistics are typically carried out for one of two reasons, either to build a model for making predictions or to enhance understanding by investigating where relationships among variables occur and what the nature of those relationships is. When the goal is the second of these, understanding relationships, it's important to specify one primary purpose or research question, usually by choosing one outcome variable that is of primary interest. In contrast, in data mining or machine learning, the goal is usually building predictive models from large amounts of data, often without an explicit research question. Data mining work tends to be more algorithmic than based on probability models and statistical properties, which is the type of work that we've done in this course. Once we've formulated clear research questions, the next steps are the following. We need to carefully design and implement a study to acquire relevant data that will help us answer our research questions. Once we've got that data, we'll need to clean it. We'll need to carry out analyses, which typically include both preliminary analyses and then formal final analyses. And finally, we'll need to interpret and present our results. In this video, we're focusing on the first step, formulating a clear research question. Since understanding the context is essential, our goal now is to understand the context of the study that we're going to be looking at. Let's start with carbohydrates. Carbohydrates are found in many foods, including fruits and vegetables, grains, dairy products, and sugary sweets. Your body uses carbohydrates to make glucose, which gives you energy. You may have heard of good carbs and bad carbs, with bad carbs being associated with refined white flour and added sugar, and good carbs associated with foods that are rich in fiber. In the study we're considering, carbohydrates were separated into two categories by their glycemic index, which is a measurement of how the glucose in blood responds after eating a carbohydrate-rich food. After eating a high GI food, blood glucose levels reach a sharp, quick peak and then have a fast decline. Low GI foods, in contrast, raise blood glucose levels lower and more slowly. The glycemic index of any food is affected by many things, including the type of starch, the fat and acid content of the food, and how it is processed and cooked. Foods that are easier to digest and are more highly processed tend to have higher GI ratings. For example, white bread has a higher glycemic index than pumpernickel bread. Because low GI foods are slower to digest and absorb, and they have smaller fluctuations in blood glucose associated with their consumption, there are many health benefits associated with eating low glycemic index foods. In particular, they help control blood glucose levels, which is of particular importance to diabetics, and they may in fact reduce the risk of type 2 diabetes. Eating low GI foods helps control appetite, and thus might have benefits for weight control. And they help control cholesterol levels and thus reduce the risk of heart disease. The study that we're looking at as our case study was designed to assess the effects of type of dietary carbohydrate, specifically low glycemic index versus high glycemic index foods. So we're classifying carbohydrates by what happens to blood glucose after they're consumed. And this study is particularly interested in subjects who have type 2 diabetes. So let's look a bit more at the connection between glucose and diabetes. Your body needs glucose to give itself energy. But to make this process happen, glucose needs insulin to provide a channel to cells through what are called insulin receptors. Insulin is produced in the pancreas. If a person's pancreas doesn't produce any insulin, then that person has type 1 diabetes. And the only treatment then is to take insulin. Now, if a person's pancreas does produce insulin, but there's not enough or the insulin receptors aren't working, so they don't create that channel for the glucose to get to the cells, then that person has type 2 diabetes. In type 2 diabetes, glucose builds up in the blood instead of being used for energy in the cells. And it's been shown that over time, having high blood glucose levels can lead to blindness, kidney problems, and other health problems, in particular heart disease, which is the cause of death for 80% of people with diabetes. And people with diabetes often tend to have more severe heart disease and develop it at a younger age than the general population. Which brings us back to the purpose of our study, the Canadian Trial of Dietary Carbohydrates in Diabetes, or CCD for short. So remember, the main purpose of CCD was to compare in subjects with type 2 diabetes the effect of dietary carbohydrates. The actual study compared 3 different diets, but we're going to focus on just 2. We'll come back to the third briefly later. We'll compare subjects who ate a high carbohydrate, high glycemic index diet with subjects who also ate a high carbohydrate diet, but with low glycemic index foods. And we want to see if there are any benefits to consuming the slow-release, low GI, low glycemic index foods. The CCD study followed subjects for 1 year in order to be able to assess the long-term effects. 1 year is an extremely long-term study for a nutrition study, which was one of the novel aspects of this one. Remember that our first step in the process of statistical inquiry was to formulate clear, focused research questions. So, are we there yet? If you answered no to the question, you're correct. We know that we want to compare people on a high GI versus a low GI diet. We know that we're particularly interested in people with type 2 diabetes. But we haven't yet indicated what we're comparing or how we'll define the benefits of a particular diet. There are 2 main ways in which we hope that improved diet will benefit people with type 2 diabetes. The first is better control of their diabetes, and the second is lower risk factors for heart disease. For the CCD study, the first of these, control of diabetes, was identified as the primary outcome or the main purpose of the study. Naturally, there is more than one way this could be measured, and the investigators chose HbA1c. HbA1c, or glycated hemoglobin is another name for it, measures the average amount of glucose in a person's blood over the last 3 months. The fact that it gives this long-term picture instead of a snapshot in time is why it is a preferred method of measuring how much a diabetic's disease is under control. Diabetics have higher levels of HbA1c than healthy people, and higher levels of HbA1c indicate less blood glucose control. So now we have a primary objective: to compare, in subjects with type 2 diabetes treated with diet alone, the effects of 2 diets. The first, high carbohydrate, high GI, and the second, high carbohydrate, low glycemic index, on blood HbA1c concentrations. I've slipped in here that the study is only going to look at type 2 diabetics who are treated with diet alone, so not taking any medication for their diabetes. We'll come back to this point later. It is expensive to carry out studies, especially on humans, so most studies consider many objectives in addition to their primary interest. These considerations are considered secondary objectives. For the CCD study, the secondary objectives included weight, side effects of the diets, other measurements related to diabetes management, and measurements of the risk of heart disease. The risk factors for heart disease that were considered included things like various measurements of cholesterol. We're going to look at one of these secondary measurements, and that's one of the risk factors of heart disease, and it is C-reactive protein. C-reactive protein, or CRP for short, is a protein in the blood, and high values indicate that there is some inflammation or swelling somewhere in the body. If there is no obvious source of swelling, say from an injury, it is often the case that the inflammation is caused by constricted arteries, so elevated levels of CRP are associated with greater risk of heart attack or stroke. At least one study has shown that CRP level more accurately predicts heart disease than cholesterol levels. The study also collected some basic information about the participating subjects, including sex, age, and BMI. We've seen BMI, or body mass index, as both an ordinal variable when it's been classified as underweight, normal, overweight, and so on, and we've seen it as a quantitative variable which can be calculated from height and weight. We're going to be working with the numeric value here. So to summarize, we're looking at the Canadian trial of dietary carbohydrates and diabetes, or CCD, in a little bit of a simplified version. We're interested in comparing subjects with type 2 diabetes on two different diets, a high GI diet and a low GI diet. Our primary objective is to compare HbA1c between these two diet groups. As a secondary objective, we're interested in comparing levels of C-reactive protein between these two dietary groups. So our response variables are our primary variable of interest, HbA1c, and also CRP of the secondary interest. Our main explanatory variable is diet, whether the subject ate a high GI or a low GI diet. And we have some other possible explanatory variables that we know about our subject, in particular sex, age, and BMI. In the next video, we'll talk about some design issues associated with planning this study. Welcome back. In this lecture, we're going to continue with the case study introduced in our previous video. Now we're going to talk about how to design a study in order to collect the data that we need in order to answer the questions that we're interested in investigating. To remind you where we are from the last lecture, we're looking at a slightly simplified version of the Canadian trial of dietary carbohydrates and diabetes, or CCD. The primary objective, or our main research question, is, does HbA1c, which is a measure of diabetic control, differ between subjects who consume a high glycemic index versus a low glycemic index diet, where our subjects all have type 2 diabetes and are being treated by diet alone, so no medication. As a secondary investigation, we're also interested in the risk of heart disease. So we'll also compare the level of C-reactive protein, or CRP, which is a marker of the risk of heart disease, between our two diet groups. And we'll be collecting the following measurements on our subjects: their level of HbA1c and of CRP, and for explanatory variables, the diet that they're on, high GI or low GI, and their sex, age, and BMI, or body mass index. We're working through this sequence of steps. In the last lecture, we concentrated on understanding the scientific interests so that we could formulate clear research questions. In this lecture, we're focusing on step 2, designing and implementing a study to acquire relevant data. We won't actually carry out the implementation. That's already been done, and we'll start working with the resulting data, which is steps 3 through 5, in the next lecture. In this lecture, we'll talk about the design issues. By carefully designing a study, we hope to create a situation in which we can make the strongest conclusions possible that will help us understand our research questions. Careful design means that we will be able to generalize our conclusions to a population of interest. It means we'll avoid any systematic error or bias in our measurements or conclusions. It will help us reduce the non-systematic error caused by the natural variability in measurements so that we can get more precise estimates and have more power in our inferential procedures. And it will help us ensure that the sample size is appropriate so that we're not wasting any time or resources by planning a study with insufficient power to see what we want, or a much larger sample size than we actually need. Our first consideration in our study design is what type of study we should carry out. An observational study would allow us to observe subjects in their natural setting, including the diet and lifestyle that they normally lead. This would be interesting. However, with an observational study, we won't know if there are confounding variables or common causes that lead to both changes in consumption of dietary carbohydrates and changes in diabetic control. So we'll choose to carry out an experiment so that we'll be able to attribute to diet any differences that we might see in HbA1c or C-reactive protein. Recall that the key feature of an experiment is that treatments are imposed on our experimental units. Since our experimental units are people, they first need to give informed consent and agree to follow the diet they are asked to. In the CCD study, subjects were provided with some key foods, which were some carbohydrate-rich foods that they were to eat with each meal, and they met with a dietitian who advised them on how to incorporate these foods into their diet in a manner to avoid weight gain. For some of the subjects, these key foods were high glycemic index, and for the others, they were low glycemic index. To summarize this experiment, we have experimental units who are the participating people with type 2 diabetes, and we have one factor, diet, with two levels, high and low GI, and these are our two treatments. Remember that the principles of experimental design are control, randomization, and replication. And we'll now talk about how each of these was implemented in the CCD study. The first principle of design is to control what we can. In studies such as CCD, one of the ways this is done is through specification of inclusion and exclusion criteria for the subjects to be studied. Remember that our primary objective stated that we would study people with type 2 diabetes being treated by diet alone. This statement already indicates control in two ways. By only looking at diabetics, we're protecting ourselves from the wide variation of HbA1c levels in the population at large. There will still be variation in HbA1c among our subjects, but it's hopefully less, giving us more precise estimates. And this will also help us focus our conclusions. And by only considering diabetics being treated by diet and no medication, we're eliminating having to consider the effect of some subjects on medication and others not. There were several other inclusion-exclusion criteria for subjects to be enrolled in the CCD study. These included age. We were looking for subjects between 35 and 75 years old. Subjects needed to have a body mass index between 25 and 40 kilograms per meter cubed, which are typical values for people with type 2 diabetes. And their HbA1c level, which would be elevated because they were diabetics, still had to be low enough so that they could continue to be treated just by diet. Some of the exclusion criteria, or reasons that subjects would not be enrolled in the study, included if they were taking diabetes-related medication, if they'd had a serious recent medical event such as a heart attack or major surgery, if they had intolerance to any of the study key foods, so then they wouldn't be able to follow the diet, or if they were going on an extended holiday during the year of the study, which perhaps would make it difficult for them to stay on their diet treatment. By controlling all of these factors, we hope to have much less variability in our measurements from subject to subject, and thus much more precision in our estimates. But it also means that our findings will only apply to people who meet these criteria. Another way to control for variation is to use blocking. Recall that blocks are groups of relatively homogeneous experimental units. And by comparing treatments within blocks, we're reducing the effect of that variation that exists between blocks. And that should give us more power for our comparisons. We could have done something like this in the CCD study by using a crossover study. In a crossover study, we would have had the subjects follow one diet for a while and then have them switch and follow the other diet, with the order randomly determined. This would give us match pairs data and would allow us to compare the dietary treatments within subjects, reducing the effects of the variability between subjects. However, part of what made CCD a novel study is that subjects stayed on their dietary treatments for 1 year, a long term for a nutrition study, in order to assess long-term effects. So in this situation, a crossover study isn't practical. The next principle of experimental design is the use of randomization to avoid bias. Recall that we can use randomization in 2 ways: in the selection of experimental units to participate in the study, and in the assignment of treatments to experimental units. If we've done the first of these, that is, our experimental units are a random sample from some population, then we'll be able to generalize our results to that population. If we randomly assign treatments to experimental units, then we'll be able to make causal conclusions. In the CCD study, subjects were enrolled from 5 clinical centers across Canada. Eligible patients at each of those centers, who met the inclusion and exclusion criteria, were given information about the study and asked if they would be willing to participate. This is typical of how people are recruited to medical studies. The subjects are then not randomly chosen from a population. So we'll have to be cautious about generalizing results beyond the subjects who are being studied. Randomization was used in the treatment assignment. The recruited subjects were randomly assigned to follow either the high GI or the low GI diet. Another way to avoid bias is to use blinding. But for this study, it was decided that it was impossible to conceal from the subjects and from their healthcare providers what the subjects were supposed to be eating, so blinding wasn't used. And the final principle of design, use replication. If a result holds for 1 or 2 subjects, it's not very interesting. We need to see how our treatments work on a large number of subjects to have convincing results. So this leads us to the question, how many subjects should we recruit for our study? Or to put that in more statistical terms, how many observations are needed so that an effect can be detected? That is, that we are likely to get a statistically significant result for a difference between the treatments that we're interested in. This is the sample size question in terms of a testing situation rather than a confidence interval situation. For the CCD study, we wanted to say that the effect that one diet has on HbA1c is statistically significantly different than the effect that the other diet has. So we want to carry out a statistical test. Sample size calculations are related to how powerful we want the test to be. That is, how high we want the probability to be that we reject the null hypothesis when in fact it is false. In order to do the sample size calculation, we first need to know what kind of test we'll be carrying out. We're comparing HbA1c, which is a quantitative variable, between 2 groups. And we'll investigate whether the mean value is the same in the 2 groups. So we'll use a 2-sample t-test with a 2-sided alternative hypothesis, since it's of interest whether either diet has a lower HbA1c mean than the other diet. From our previous study of power, we know that power changes with sample size. To flip that around, we'll calculate the sample size we need to get the power we want. For the CCD study, sample size was calculated to have a power of 80%. 80 to 90% are typical values used in planning studies. Power also changes with the difference between the null hypothesis value of the parameter and a particular value under the alternative hypothesis. In this case, that translates to the difference in the means of HbA1c for the 2 diets that we think is clinically interesting, so we want it to be statistically significant. For CCD, a difference between the diets and the mean of HbA1c of 0.004 was thought to be interesting from a clinical perspective. Power, and thus sample size, also changes with standard deviation, so we need an estimate of the standard deviation of the difference in the HbA1c means. Based on previous studies, this was estimated to be 0.0066. And power varies with the significance level, or the cutoff for how small is small for a p-value, which then sets our chance of making a type 1 error. And this is often set at 0.05, which we'll use here. Once we've decided on these quantities, we can use statistical software to calculate the required sample size, which I did, and I got that we need 44 subjects per treatment group. Now we expect that some of the subjects will drop out of this lengthy study, so we'll recruit an extra 20%. And 120% of 44 is 53, so we'll need 106 subjects in total. To recap, we've made a number of design decisions. We'll carry out an experiment. We'll recruit about 106 subjects who have type 2 diabetes, being treated only by diet, and who meet our inclusion and exclusion criteria. We'll randomly assign about half of the subjects to a high-carb, high-GI diet, and the other half to a high-carb, low-GI diet. We'll take some basic measurements on each subject, including sex, age, and BMI. We'll have them follow their diet for a year, and then we'll measure their HbA1c concentrations to assess diabetic control, which is our primary interest, and we'll measure their level of C-reactive protein to assess the risk of heart disease. And then we'll compare these measurements between our two diet groups. In the next video, we'll fast forward a year to when we have the data and see what we can learn from it. In the last two lectures, we took a scientific question and we refined it into a research question that we can answer by collecting and analyzing some data, and we made some decisions about the design of the data collection. So now let's pretend that a year has passed and we've got our data. Let's take a look at it. Let's start with a quick reminder of where we are. We're looking at the Canadian Trial of Dietary Carbohydrates and Diabetes. We're looking at people with type 2 diabetes, and we're giving them a high carbohydrate diet. Some of them have been assigned to follow a diet with high glycemic index foods, and the rest will be taking a diet with low glycemic index foods. Our primary objective is to see the effects of these diets on blood HbA1c concentrations, which again is a measure of diabetic control. As a secondary objective, we're interested in the risk of heart disease, so we'll look at the level of C-reactive protein in the blood. In addition to diet as an explanatory variable, we'll also take a look at sex, age, and BMI of the subjects. And we're working through these steps, the process of statistical inquiry. In this video, we're going to take our first look at the data. We'll be covering both step 3, where we'll use this first look to see if there are any problems in the data, and part of step 4, some of the preliminary analyses. Here are the first few lines of our data. Although you can't see them all on this screen, there are data values here for 103 subjects. So there are 103 lines of data in our data file. You may recall from the last lecture that we said we needed to recruit 106 subjects. But we expected a number of them, about 20%, to drop out, which would leave us with only about 88 subjects. But we have 103. The actual study is a little more complicated than what we're presenting here, and it needed to recruit a few more subjects than we calculated in the last lecture. Now we're working with the actual data and the actual number of subjects for whom data were collected. So now let's take a look at the data. Note that sex is coded F for females and M for males. Then we have the subjects' ages and BMIs. These were measured at the beginning of the study. Diet is coded L for the low glycemic index diet and H for the high glycemic index diet. The columns HbA1c and CRP are the values at the end of the study. So these are the values after 1 year on the treatment diet. Some of these other variables you might not have been expecting to see. The variable fail is Y or N for yes or no, and it's an indicator of treatment failure. The yeses are subjects who met the inclusion criteria for the study, but then they needed to drop out because their medical advice changed and they were put on medication to control their diabetes. And you might recall that one of our inclusion criteria was to only study diabetics who were being treated by diet alone. These subjects who are considered failures all have relatively large values of HbA1c, but the decision to drop them out was based on more than just that, so they're not just the highest values that we see in our data. An interesting question is whether or not the number of subjects who were treatment failures existed equally between the two dietary treatments. And we'll come back to that later. Something else to note is that for our outcome variables, HbA1c and CRP, we also have baseline values. That is, these are measurements taken at the start of the study, just before the subjects started on their dietary treatments. And we'll talk later about dealing with these. We'll start by looking at our variables one at a time. The purpose of this is to identify any obvious errors in the data and identify features such as possibly outliers or skewness that may affect the choice of the analyses that we carry out. Let's start with our categorical variables: diet, treatment failure, and sex. We'll just look at tables of frequency and relative frequency for these variables, since each of them has just two categories. For diet, we can see that our randomization process resulted in slightly more subjects, 53%, receiving the low GI diet. Only 5 of our 103 subjects were considered to be treatment failures, that is, they needed to withdraw because they went on medication. And for sex, we see our first potential problem. Some of the males were inadvertently coded with a lowercase m. But we can fix that, and then we can see that the recruitment resulted in 58% males and 42% females. Now we can take a look at our quantitative variables. They are age, BMI, HbA1c, measured at the end and at baseline, and CRP, also measured at the end and at baseline. Starting with age, we can see that there's something funny going on here. There's a huge outlier, which is an age close to 1,000, and clearly a mistake. Flipping through all our quantitative variables, we see the same phenomenon for BMI and HbA1c at the end of the study, although not for HbA1c at baseline. And here it is for CRP, both at the end of the study and at baseline. A closer look at the data shows that there are several values entered as 999. These are actually missing observations. For some reason, the measurements for these quantities on these particular subjects were either lost or unable to be measured. The indicators for missing values are different for different statistical software packages. So sometimes people code them with impossible values and leave it to the analyst to adjust them to what they should be for the software that they're using. And we'll need to do that before we can continue. Here are the counts of the number of missing values for each of our variables. If the missingness happens completely at random, then, although it limits our ability to use the observations in our analyses, we don't have to worry about them biasing our results. But if the fact that they're missing tells us something about what the values would have been had they been observed, perhaps say HbA1c is missing because it is large, then we call those missing values informative, and having them in our data would bias our results. For example, our estimate of the mean of HbA1c would be smaller than it should be, because we're missing those large values. There are advanced methods to deal with missing values that are informative, and there are also methods for imputing estimates of missing values. For the actual CCD study analysis, some of these advanced methods were used. But for us, a quick count of the missing values in our outcome variables at the end of the study shows that the missing values occur in about equal numbers in the two diet groups. And we'll assume that they aren't informative, and we'll just carry out our analyses using the observations that we have. So now we've cleaned our data by fixing some problems with the coding of sex and by replacing the 999s with the appropriate missing value indicator. Now that we've got rid of those 999s, let's go back and take another look at the quantitative variables. Looking first of all at age, our subjects ranged from 40 years old to 74. Our inclusion criterion for age was 35 to 75 years, so we didn't recruit any subjects quite as young as our lower limit. The distribution of BMI is a little bit right-skewed. Our inclusion-exclusion criterion for BMI was 25 to 40 kilograms per meter cubed, and we have subjects just outside that range, probably because their BMI changed after they were initially screened for this study. Moving on to our primary outcome variable, HbA1c, we can see that it has a fairly symmetric distribution, and you should be able to see that symmetry in the 5-number summary as well as the histogram and box plot. In this course, we've learned inferential procedures based on the normal distribution, and that seems like a reasonable model for HbA1c. And now we can take a look at the distribution of HbA1c at baseline, which is also fairly symmetric. Of course, we're not really interested in HbA1c at baseline, but what we're interested in is how the subjects changed during the year on their study diets. Here are the box plots of HbA1c at baseline and at the end of the study, side by side. On average, HbA1c may be slightly higher at the end of the study, which is not what we wanted. But there's lots of overlap in the boxes, so we don't expect this to be statistically significant. That said, there's a fundamental problem with this plot. The same subjects have an observation at both baseline and the end of the study, but the plot doesn't match them. For matched data like these, you may recall that we can look at the difference, in this case the change from baseline. Here are the differences in HbA1c, calculated as the value at the end of the study minus the baseline value. The lowest values are negative, but since the first quartile is positive, we know that more than 3/4 of the subjects had higher HbA1c at the end than at the beginning of the study, with a few very large positive changes. An even more useful representation is to look at these changes in HbA1c by diet. It seems that the highest values are for the low GI diet, and the median and the mean are also slightly higher for the low GI diet. But again, there's lots of overlap in the box plots, so these differences may not be statistically significant. Looking now at our outcome of secondary interest, CRP, we can see that it's very right-skewed. In the box plot, the long right tail in this distribution shows up as a trail of observations beyond the upper fence. Right-skewed distributions often happen in cases like this for variables such as CRP, which are bounded below by 0, but have the potential to be very high. At baseline, CRP has a similar right-skewed distribution, clear in the histogram and the box plot and the 5-number summary. There is one observation that is quite far out in the tail. But this can happen with right-skewed distributions, so rather than calling this an outlier, it's more likely that it's a consequence of the shape of the distribution. In the regression lectures, we saw how a logarithm transformation can be useful in creating a linear relationship. Because of the shape of the logarithm function, logarithmic transformations bring in long right tails. So they're also useful in situations such as this one. Again, we'll use the base 10 logarithm. And here are the plots and summary statistics of CRP at the end of the study once the base 10 logarithm has been taken. You'll note that it's much more symmetric, and as a result, we should be much more confident using inferential procedures based on the normal distribution. This is also the case for CRP at baseline. The logarithmic transformation changes what was a very right-skewed distribution to one that is symmetric and bell-shaped. Working some more with the logarithm of CRP, and as we did for HbA1c, our other outcome variable, we can combine the baseline and end-of-study measurements of CRP by taking the differences. So we'll take a look at the difference or change from baseline in the log of CRP. Taking you back to some basic facts about logarithms, the difference of two logarithms is the log of the ratio. So the difference between the log of CRP at the end of the study and the log of CRP at baseline is the log of CRP at the end divided by CRP at baseline. So this difference in the log measures the log of the ratio. If CRP at the end of the study is equal to CRP at baseline, so then there's no change in CRP from baseline over the course of the study, then the ratio is 1. And you may recall that the log of 1 is 0, which of course makes sense. The difference should be 0 if there's no change. Our box plots here are showing the differences of the log of CRP by diet. And for this variable, there does seem to be a difference between the two diets. Note that the median and the mean are negative for the low GI diet and positive for the high GI diet, although quite small. This indicates that, on average, CRP seemed to drop for subjects on the low GI diet, but not for the high GI diet. Lower CRP is good. It means less inflammation. So here we seem to have an indication that the low glycemic index diet is having a beneficial effect that we don't see in the high glycemic index diet. And we'll want to see if that is statistically significant. One more thing to note before we leave these plots. There is both a large and a small outlier for the change in the log of CRP for the low GI diet. Later on, we'll investigate the effects of these two observations. And as the final step in our initial look at the data, let's see how the other subject characteristics that we've measured, that is sex, age, and BMI, are related to our outcome variables. Looking first at HbA1c, and we'll keep looking at how it changed from baseline. The values for males seem slightly higher than the values for females, but this doesn't look to be significant because the box plots overlap so much. For age, since it's quantitative, we'll look at a scatter plot, and there doesn't seem to be any indication of a relationship. For BMI, it appears that it may be the case that subjects with higher BMIs have larger changes in HbA1c, and we'll need to come back to that. And for our other outcome variable, the change in the log of CRP, other than the outliers, the values are very similar for females and males, and there doesn't appear to be a relationship with age, nor with BMI. So now we've made a lot of progress. We have clean data, we've made a decision to work with the log transformed CRP, and we know a few things to watch for, in particular a couple of outliers and the possible relationship between HbA1c and BMI. In the next video, we'll focus on our primary and secondary objectives, and we'll carry out formal inferential procedures to see if any of the differences that we've observed here in our preliminary analyses are statistically significant. In this video, we'll carry on with our analyses of the data from the Canadian trial of dietary carbohydrates and diabetes. We've taken a good look at the data now, and we fixed some problems, and we have a good idea about where some relationships may exist. Now we're going to move on to formal inferences so that we can more formally answer our research questions. So looking back at our steps of the process of statistical inquiry, we've made it to the formal analyses. And in this video, we'll carry out some formal tests and interpret the results, covering steps 4 and 5. You'll note that we've mixed step 4 in 2 videos, this one and the last one. We did this because, although we've outlined the statistical process as a sequence of steps, in practice it is often an iterative process, where what you learn from formal analyses causes you to look at the data in new ways, which might be considered preliminary analyses, and then these inform new formal analyses that should be carried out, and so on. Let's start with our primary objective, to compare HbA1c between our 2 diet groups. In our preliminary analyses, we decided to look at the change in HbA1c from baseline to the end of the study, to see if that differed between the low GI and the high GI diet. And you may recall that we noted that the largest observations were in the low GI group. As well, the mean was a little bit higher for the low GI group. But we wondered if that was significant, because there's so much overlap between the 2 boxes in the box plot. So now let's carry out a statistical test. Change in HbA1c is a quantitative variable, and we want to compare 2 groups, the low GI group and the high GI diet group. So we'll test whether the means are the same for the 2 groups. The first step in any statistical test is to state the hypotheses. So what we'll test is our null hypothesis that there's no difference in the means between the 2 groups versus our alternative that there is a difference. Our alternative is a not equal to, or a 2-sided alternative, because we have no reason to test whether one group is higher or lower than the other diet group. And just to define our notation, mu sub h will stand for the mean of the change in HbA1c for the high GI group, and mu with the subscript L will be the mean change in HbA1c for the low GI group. Our 2 treatment groups, the high GI and the low GI groups, include different people. So this is a 2 independent samples case. And to test whether the means in the 2 groups are equal, we can use the 2 independent samples t-test. We have 2 versions of this test. One in which we pool the variances because we assume that the variances are equal in the 2 groups, and the other when we don't make this assumption, or the unequal variance case. We don't really have any reason to make this extra assumption, so we won't. Although looking at the standard deviation of the 2 groups, they're fairly close. And in situations such as this, the 2 versions of the t-test typically give the same result. Here's the formula for the test statistic for the 2 independent samples t-test, not assuming that the variances are equal. We have all these numbers here that we need to calculate this, except for the sample sizes. Because of the missing values caused by dropouts in the study, we don't have observations for everyone that was recruited, and we have the change in HbA1c for 41 subjects on the high GI diet and 49 on the low GI diet. So plugging in the mean of the high GI group, 0.0038, and the mean of the low GI group, 0.0051, the difference in the means is 0 since we're assuming that they're equal, and dividing by the square root of the variance of the high GI group divided by its sample size plus the variance of the low GI group divided by its sample size, and we get the value of the test statistic, which is about -1. There's lots of round-off error here, so I won't bother giving it more precisely. The Welsh-Satterthwaite approximation for the degrees of freedom is about 88, so we need to calculate our p-value from a t-distribution with 88 degrees of freedom. We can draw this t-distribution. It looks something like this, and we can put on this plot our test statistic of -1. Because we're carrying out a two-sided test, values that are more extreme than what we got include values that are both less than -1 and greater than +1, since those are equally as far from 0. And our p-value is the shaded area in the plot. And using some statistical software, the p-value is about 0.3. 0.3 is a fairly large p-value, so we conclude that our data are consistent with the null hypothesis. And there's no evidence of a difference in the mean change in HbA1c between the high GI and the low GI groups. To give a very complete conclusion, in addition to saying that there's no difference, we could give an estimate of the mean change in each group, and, even better, give a confidence interval for the means of these changes, to give a plausible range of values for them. The formula for a confidence interval for the mean is this, and we have everything we need except for the t-critical values, which for 95% confidence intervals are 2.02 for the high GI group, where we had a sample size of 41, so 40 degrees of freedom, and 2.01 for the low GI group, where we have 48 degrees of freedom. And you can verify that the confidence intervals are these. Note that the confidence intervals overlap quite a bit. This is to be expected since we didn't see a statistically significant difference between the two groups. Let's move on to our secondary objective now, which was to investigate whether the change in CRP differed between the two diets. We decided that we should look at the log of CRP because of its strong right skew. And we noted that the mean change in CRP was quite negative for the low GI group, indicating that their CRP levels dropped in comparison to the high GI group. So now it's time to test whether that's statistically significant. Again, the log of CRP is a quantitative variable, so we can use a two independent samples t-test to test whether or not the means are equal in the two diet groups, and again we'll work with the unequal variances case of that test. So our null hypothesis is that the means are equal in the high and low GI groups, and the alternative is that they're not equal. We have 41 observations in the high GI group and 49 in the low GI group. For this variable, I won't go through all the details of the calculation, but here's what you need to know so you can calculate it yourself, and you should verify that you get the same answers as what we have here. The Welsh-Satterthwaite approximation to the degrees of freedom is about 83.7. When we calculate the test statistic for the two independent samples t-test, we get 2.3. And that gives us a p-value of about 0.02. A small p-value now, so we can conclude that we have evidence that the mean change in the log of CRP differs between the two diet groups. To make that conclusion a little bit more complete, again let's look at the confidence interval for the mean change in the log of CRP for each of the diet groups. Note that for the high GI group, it includes 0. So we can't conclude that there was any change in CRP at all for that group. In contrast, for the low GI group, we have a confidence interval that only includes negative values. So it appears that, indeed, CRP dropped on average for the low GI group. And again, that's a good thing. Lower CRP means less inflammation. So this seems to be a beneficial effect of the low glycemic index diet. Something worth noting is there is a little bit of overlap between these confidence intervals. There seems to be a common fallacy that in order to have statistical significance in the two-sample case, the confidence intervals for the two groups cannot overlap. But that's not true. If the confidence intervals didn't overlap at all, the p-value would be extremely small. But you can still have some overlap in the confidence intervals and have a small enough p-value that you declare the means of the two groups statistically significantly different, as we have here. You may recall from the previous lecture, when we first looked at this box plot of the change in log of CRP between the high GI and the low GI diet, that we noted two outliers, a very large outlier and a very small outlier, both in the low GI diet group. And you may be wondering what effect these outliers have on our analyses. Here are some statistics with the outliers in the data and with these two outliers removed. You'll notice that the mean of the low GI group doesn't change very much, even though means are not resistant to outliers. This is because the large outlier and the low outlier in essence balance each other out. The test statistic is a little bit larger when we don't have the outliers in the data. This happens because without the outliers, the variability in the low GI group is less. And as a result, with the lower variability, we have a little bit more power, so we're more able to detect differences between the groups, and we have a smaller p-value as a result. You may also wonder what would have happened if we hadn't taken this log transformation of CRP. After all, we're carrying out a t-test. And t-tests are extremely robust against departures from the condition of needing normally distributed data. In this case, the p-value would have been 0.12. And we would have made the opposite conclusion. We would have concluded that there was no difference in the means between the diets. So although the t-test is robust, it doesn't work in every situation, and it's important to take a look at the data first. Now let's go back to something else we said we would return to in our data. There were treatment failures. 5 people had to leave the study because they needed to go on medication to control their diabetes. There were still measurements taken on these people before they left, so they weren't necessarily missing values. But we may still be worried about whether or not our treatments contributed to this treatment failure. So let's look at the failures by diet group. Of the 5 failures, we can see that 1 was in the high GI group, and the remaining 4 were in the low GI group. Or looking at this another way, 2.1% of the subjects in the high GI group had a treatment failure, while 7.3%, over 3 times as many, had a treatment failure in the low GI group. So is this an indication that we might have a difference between the two diet groups in treatment failures? Unfortunately, we can't carry out a statistical test to compare these proportions between these two groups using the machinery that we've learned in this class. The problem is that the two-sample test of proportions is not robust enough. Recall that this two-sample test for proportions relies on the central limit theorem. And in a previous lecture, we saw that the central limit theorem needs very large sample sizes for estimating proportions when the actual proportion is close to the limits of 0 or 1. That's the case here. We only have 2 or 7% of failures in each group. So we need larger sample sizes than 48 or 55 in order to have proportions that are approximately normally distributed so that we can use the tests we learned. So what can we say? Is this a surprising difference between the two groups? Think of it this way. Suppose we knew there was going to be 5 treatment failures, and we see that they're distributed between the diets as 1 and 4. If there was no difference between the diets, you'd expect 50-50 chance that these treatment failures would be in either diet. If we flipped a coin 5 times, Would you be surprised if you only got one head? That's the situation we have here, and because we have such a small number of treatment failures, we can't say if this difference between the two diet groups is meaningful. It could just be due to chance. Another potential issue we saw in our preliminary data analysis was a relationship between the change in HbA1c and BMI. If there is indeed a relationship between these variables, including BMI in a statistical model can help explain some of the unexplained variation. This would allow us to get more precise estimates of what we're interested in, which is the effect of diet. This is another example of control. But this would be using a statistical model to control for the effects of another variable. In order to do this, you need multiple regression models, which allow you to have multiple predictor variables. Unfortunately, we're not covering this in this course, but my motivation in telling you this is to encourage you to keep studying statistics. Here are some other issues that came up in the CCD study, our study of the effect of carbohydrates in diabetes, for which some methods that you might learn in more advanced statistics courses would be useful. The CCD study actually had 3 diet treatment groups, not 2. In order to compare more than 2 means, you need a procedure called analysis of variance. The CCD study also had many secondary outcomes, not just CRP. These included measures of cholesterol such as HDL and LDL, and also included fasting glucose and blood pressure and weight and other variables. Whenever we carry out multiple statistical tests, there's a good chance that we might make a type 1 error. That is, we might find a statistically significant result just by chance. There are different ways to protect yourself against a type 1 error. And again, we're going to have to leave that for your next course. Here's one more issue about the CCD study that you may have guessed. The subjects weren't just measured at baseline, and then left for a year and then measured again. Data were collected on the CCD study subjects multiple times during the year. One of the reasons for doing this was to assess whether the pattern of change in the outcome variables changed over time. To see what I mean by this, imagine one diet in which there was a change right at the beginning of the study, but then it leveled off. But a different diet had a gradual change. They might both end up in the same place, but not in the same way. And it would be interesting to study this. One way to do this is using longitudinal data analysis. Again, a topic for a more advanced statistics course. But even with the elementary methods that we've learned so far, we were able to show the main findings of the study. Here's the title from the main paper published from the study in the American Journal of Clinical Nutrition. You can see that differences among the diets in CRP was found, but not differences in HbA1c or glycated hemoglobin. And that's exactly what we found. Moreover, the CCD study was an experiment. So any changes among the diet groups that we saw can actually be attributed to the diet. We can say that dietary changes do cause changes in CRP. We hope this gives you a taste of the study from the beginning to the end and the importance of statistics in carrying out the study well at every step. And we hope it also gives you some motivation and encouragement to study more statistics.
It's 'cause I took a move. Skeletons drove me round the bend, but now I call them my old friend. If you showed me a vaccine I could not confuse the mean, then I found the right class to attend. 1, 2, alpha, beta, well I'm making sense of data, and it's not a fluke, it's 'cause I took a move. I was the worst of every nation at understanding a relation. Now I've learned that correlation does not imply causation. I cringed at probability, those coins and dice and N and P. But a hypothesis test always seems to work the best when I use a distribution T. 1, 2, alpha, beta, well I'm making sense of data, and it's not a fluke, it's 'cause I took a move. So now I'm feeling really fine. I've studied inference online. I think my favorite lesson was linear regression, sorting out that slope and sine. 1, 2, alpha, beta, well I'm making sense of data, and it's not a fluke, it's 'cause I took a move. I took a move. It wasn't a fluke. I must be a kook. Now make me a duke, 'cause I took a move. Mooka, mooka, mook, mook. Mooka, mooka, mook, mook.
Case Study R Tutorial. We are nearing the end of the course, and as a final exercise in our last week, we are looking at a case study, the Canadian trial of dietary carbohydrates in diabetes. In the first video lecture, Allison introduced to us the study and a few keywords and concepts that allowed us to better understand the purpose of the study. In the second lecture, you saw how to design such a study to acquire the data needed to answer the research questions. One of the questions raised in this particular lecture video was how large of a sample would we need to be able to obtain statistically significant results? Recall that we wish to calculate the sample size required for a 2-sample t-test with a power of 0.8, a difference between treatment means of 0.004, with an estimated standard deviation of the differences of 0.0066 at a 0.05 significance level. To calculate this, we will need to first install the Power package with the install.packages command, and then load the package with the command library. The command we will want to use is power.t.test. This command is very useful in that it can calculate power given the parameters, or it can determine parameters given the power. We will use it to determine the sample size, so we will enter all of the information that was given. We will start with the required power of 0.8. The second argument, d, is the effect size, calculated as the difference divided by the estimated standard deviation of the difference we are interested in. So 0.004 divided by 0.0066. We will specify that it is a two-sample t-test with a two-sided alternative hypothesis at a significance level of 0.05. The output restates all of the parameters entered, which you should quickly glance over for any errors. And at the very top we see that the sample size required is approximately 44 subjects. The note at the bottom does state that the sample size is the required count for each group, not in total. In the third lecture, when you got a first look at the data collected, you noticed a few problems that needed to be fixed before the data can be analyzed. Let's first read in the data and attach the variable names. The first problem encountered was that some of the males were coded with a capital M and some with a small m. If we just type in the variable sex, we see all of the observations and at the very end the levels. Here we notice the problem. To fix this, we can say that for any of the observations in sex, if sex equals to little m, in quotes because it is a name, we will set it to capital M. With the command table, we can make sure that the right change was made. Now there are no subjects for which sex equals to little m, so we can drop that level with the drop levels command. The second problem you came across was that there were quite a few missing observations, but they were all coded with 999 instead of NA, which is the default coding in R. To fix this problem, we will go through each of the variables: age, BMI, HbA1c and HbA1c baseline, CRP and CRP baseline, and for any observation that is coded with 999, we will set it equal to NA. Since our focus is on how the subjects changed over the year with respect to the outcome variables, we will create two new variables, HbA1c diff and CRP diff, and we will set them equal to the difference between the baseline measurement and the end of the study measurement. And our final step will be to do a log transformation on the CRP measurements, due to the fact that they have a very right-skewed distribution. We can define log CRP and log CRP baseline, and then take their difference to obtain log CRP diff. We have examined the data for problems, and we have fixed those problems easily using R. And with the new variables we have calculated, we are ready to carry out the formal analysis required to answer the research questions posed. We have covered all of the commands needed to analyze this data in previous R tutorials. So flip through your notes or review a previous tutorial. All of the tools you need are right at your fingertips. Good luck!